buy for a first radio because what do you think, Scott? I just
Yeah,
wanted to
well,
add that
you
because
can't program it very easily from the front
it's
panel.
it's impossible to
No, it's
program
not
like that.
impossible, but it's really hard to get stuff into memory. It's
Really,
easy.
really hard. And
It's
when you
easy to
started,
program one of the VFOs, but it's really hard to get going past that without software.
yeah, and
Yeah,
when
I'm
you
with
but the
you.
Like
software,
so
the software is pretty easy, so I
and
don't
Right,
it's
think
all
it's
right,
free.
too bad.
right.
So
But for
like
someone,
in our local in our local club, a lot of people have them. Like the older one, the UV32, or the new one, DMR32. This
mhm,
is like in our club a pretty popular radio.
oh, everybody has one. Every
right.
single
Yeah.
ham has
I've
one. I
got
I've
think
a
it's a
I've
terrible radio
AR5RM,
for a
and
first.
it works pretty good. I've been having no problems programming it. I'm
right,
Yeah,
using
okay
short.
then.
right.
I use short
I've
programming.
had 5 or 6 of them. I've broken 2, and I've given 3 or 4 away, just because I'm like, hey, here, have a radio.
Well, I have to
I mean,
say,
as
maybe it's because of where I live, but I've had no issues. But then I live rural, so like you said, if I were to take it into the city, and actually I'm going to try it because of what you said, take it to Anchorage and see what how that works.
Well, again, a lot of it depends on how you're going to use it. I mean, the other thing is that like the quality control is not it's not really there. It's just really
hmm,
not. You know, they
Well, I'm
they
only
make
using mine on GMRS at
they
the moment.
that's better. They make a GMRS model that actually is better for whatever reason. Um, so
and yesterday you mentioned like the bathroom. The most problem is that they don't have a filter. So like
yeah,
if you break it down, can you install an external filter on it?
I
Make
what
that sense?
yes, but what's the point?
Okay.
I mean,
Yeah, for sure.
sure, but what's the point?
Well, if
So
you were in a city with one, I would think it would make it better.
you just go buy something that has it built in. Honestly, I mean, it is what it is. It was designed as a $20 radio. It is a $20 radio. If you accept the fact that it's a $20 radio, it's
Mhm.
fine. If you ever wanted it to be more than that, you're going to be unhappy.
Yeah.
That's why I don't mind, like, okay, I've got a few. Hey, you're going to be, if you just got your license, all right, well, here, have a radio. I've done that. Like, I just give them away.
It's exactly what happened to me, and I haven't been able to use it at all.
Well, you kind of live out in the middle of nowhere too, right?
Yes, I
Yeah.
do.
So, well, all right,
And even
y'all,
in,
you guys ready to get started?
Yes, sir.
Okay.
Absolutely.
Well, Scott, I'm
Uh-huh.
just putting myself in here if that's okay with you.
Sure.
Greetings, by the way. Happy holidays.
Thank you. Sam. All right, so I mentioned yesterday when I sent out the note that we are somewhere around page 57 of the Technician book. The goal is to get done with the Technician book by about 1 o'clock. So the amazingly yesterday I kind of freeformed it, and I looked back through everything in the first 57 pages, and we covered everything to my knowledge. I think thinking back, we didn't quite do batteries, but maybe we did. Everybody, what's the voltage of a car battery? How many volts?
12 volt.
12
12
volts. Okay, excellent. Is it rechargeable or not?
Yeah.
It's
Yeah.
rechargeable. You
Yes,
can
okay.
jumpstart it.
Okay, how about some batteries that are not rechargeable?
The ones you buy in the store, usually, unless you buy specifically rechargeable batteries.
Right. So what makes a battery rechargeable or not?
It charges.
Yeah, no.
The
What makes
material that
chemistry.
it's made out of.
That's right, it's the chemistry. A battery is a chemical storage of electricity. Some of the chemistries are reversible and some are not. So if it's a reversible chemistry like lithium ion or lithium iron phosphate or lead acid, that's what's in a car battery. Um, nickel
Nickel
metal
iron.
hydride, nickel metal hydride. Those are reversible chemistries, which makes them rechargeable. Like a silver battery or a lithium metal battery, those are one time. Alkaline, that's a one time. So here's another question. What happens if a storage battery in your car, for instance, like your car battery, gets really, really discharged?
You just recharge it. For the
Yeah,
one in the car.
carefully. Why do you have to
Never.
be careful about it?
It emits hydrogen gas when it is charging,
That's
and you
right.
risk an explosion if you aren't
That's
careful.
right. When you discharge or overcharge a lead acid battery, you get hydrolysis, and that makes hydrogen gas. So, you ever notice that when you hook up a jumper cable to something, the jumper cable will sometimes, depending on where you made the contact, will make a little spark? If you've ever
Yeah.
seen what happened to the Hindenburg, hydrogen gas and a spark don't go well together.
Yeah.
Unlike the Hindenburg, which just caught fire and burned, what can happen is you can get a small explosion at the terminal of the battery. And what's a lead acid battery full of?
Acid.
Sulfuric
It's
acid.
full of sulfuric acid, which can then make the battery go, and you get a shower of sulfuric acid. That happened to somebody I know. So always be very, very careful when you're recharging a battery that is mostly dead. And in fact, I never make the last connection at the battery itself, at the dead battery. I always make it over on a ground post somewhere on the frame of the car, so that if there is a spark, it's nowhere near where the battery is. Okay. Another one is when you hook up a battery, when you hook up a radio inside a car, and I think we're going to be covering this today, if I'm not mistaken. But if you look at the electrical system in a car, you might notice that there's only one wire on a lot of things, like light bulbs. That saves money. There's just basically a power line, a switched power line that goes out to a headlight, for instance. There's no second wire. Where's the second wire that goes back to the battery?
The car frame itself.
It's the whole frame of the car. Right. So the question is, if you have a radio that uses 22 amps at 12 volts, is that car frame designed to give you very, very low resistance at very low resistance and is able to carry a 22 amp current? I don't know. I have no idea. Depends on how the welding robots felt. So it's recommended to go directly back to the battery instead of going through the car frame. So the way that car frames are designed, it's not really suitable for most return paths for your
Well, what
equipment.
happens in that case, Scott? Does
You
it just dissipate and you lose the
it-
energy?
Maybe it doesn't work.
Oh,
Maybe it doesn't work at all. Or maybe when you transmit, the power draw goes up, the current goes up, and the voltage drop goes up, and now instead of 12 volts, you have 9 volts on your radio. What happens if you get voltage that low feeding a piece of equipment that requires 12?
It doesn't work.
It shuts off. Yeah, so you key the mic, and the radio turns off. So, yeah, there's all kinds of stuff. So, what is that an application of? Whose law? Ohm's law. So I tell this in every class I teach. 90%, even in my job, 90% of problems are answered by Ohm's law. That's high resistance, that's a loose ground wire, that's a loose anything. If it's a poor connection, the answer is that the problem is Ohm's law. It's 90% of all the problems you will ever see. You go back to basics. There's a loose connection. There's something that isn't screwed down tight enough, or something like that. So, all right. So let's get going with today's stuff. And today's stuff, we're going to be talking about modulation, and we talked about modulation a little bit yesterday. So what we have to do to understand modulation is answer the question, what is modulation? What is modulation? Somebody tell me.
It's the process of adding information to a radio wave.
Yes, very good. Okay. So modulation is we're going to start with a radio wave that looks like this. So that's in the time domain. And then we're going to have a frequency domain, and this goes from 0 to infinity frequency. And we're going to have the frequency right here, and we have a little spike, which has nothing around it. We just know that this frequency makes it oscillate around and around and around, and it shows up right here on this Fenner frequency. So starting yesterday, we were discussing things that you can do to make this wave look interesting and put information on it. What were some of those things?
Phase shift.
Yep, you can do a phase shift. You can take it and shift it like this. That would be a phase shift. And I can suddenly shift it another way and do this. And that's another phase shift. So I can do a phase shift by a given amount of angle at a given time, and that means something. Okay, what's another something you can do with it?
Change the amplitude.
Change the amplitude. Yep. Okay. You can make it bigger or smaller. So if
Amplifier?
if I could do this with it. All right. That would be changing the amplitude, essentially changing the size. Okay. What are some other things I can do with it?
Amplifier?
Box.
Amplifier, it doesn't. I mean, it makes it bigger, but
Hi.
Change the frequency itself.
change the frequency. I can alter the frequency either on the fly or in general. I can do this with it. That changes that. Okay, what else? Some other things I can do. Somebody said amplitude. Now, just changing the amplitude as a whole doesn't do anything, but if I can do this with it, so that the amplitude gets bigger and smaller, that can mean something. Okay, so things that we were changing so far. We were changing
The
amplitude.
phase.
We did phase.
Oh, sorry. I thought you were rewriting the list.
Amplitude, phase, frequency. We can also just turn it on and off. So that would be presence and absence. Okay, so by doing that, what we do is we alter what it looks like. So if we modulate it by altering what it looks like, how do we take the information back out when it gets to the other end? If modulating is putting information on it, what do we do on the other end?
Unmodulate it and
Well,
read what we changed.
yes, and that word is called demodulating. So we modulate it and then we demodulate it. That actually makes a word. Modulate, demodulate. That makes a modem. That's what a modem is. It's a modulator demodulator. So what happens here is that we now have this frequency, and by the virtue of putting information on it, we create sidebands. Those could look like that. They can look like this. They can look like any number of different things. They can spread out in this direction, any kind of different shapes and sizes. Okay, this right here is typically what FM looks like, and also phase modulation. Phase modulation can also be used for FM. We can also do this thing called frequency shift keying, which we take it and we do this with it. And we move it to multiple different frequencies and make little different spikes. Amplitude modulation looks like this, where we have these sidebands around a central cone. Interestingly, because this center piece, we call that the carrier frequency, doesn't contain any information, it just shows that it's there. It's basically just a marker. It provides the energy for demodulating an AM signal. If we can recreate that in our receiver, we actually don't need to transmit that. If we don't need to transmit something, we save energy. We also have in an AM signal the fact that the sidebands, left and right, or upper and lower, are mirror images of each other, which means that on top of that, we do not have to transmit both of them. We only have to transmit one to get all the information across. That's known as single sideband because it's only one sideband. This is the upper sideband, and this is the lower sideband. The one that we use is determined by the frequency that we're on. If our frequency is 10 megahertz or above, we use upper sideband. If it's below 10 megahertz, we use lower sideband. And that comes back from the days when it was generated in an analog fashion. And the oscillators that were used made it easier to use lower sideband below 10 megahertz and upper sideband above. Yep.
Are sidebands essentially naturally occurring, or are they something that is defined, like we're using these frequencies and these ones are the sidebands around it?
They are created by the modulation process. They actually come out of the mathematics of modulation.
So it emerges out. It's not something where someone says we're going to use this frequency and we're going to use this one next to it for our information.
Correct. And what ends up happening is it looks like this. So let's say here's my carrier frequency. So here's 0 and here's infinity. And here's my frequency of my carrier. If I have a modulating frequency of, let's say, so here's what it looks like in the time domain. That's a very, very high frequency. If I have a modulating frequency for amplitude modulation, which basically creates an envelope that looks like this, it's typically going to be much, much slower. What will happen is that my overall wave will now look like this. Notice it gets bigger and smaller. So I have my carrier wave, which is now the little orange wave in the middle, but it's made bigger and smaller by a modulating wave, which is of a much lower frequency, typically in the audio range. What will happen when I do that is that if it's a pure tone that's doing it, I will get this. I will actually see individual sidebands that are basically just one pure tone away. So if this
and that just occurs because of the mathematics of the waves?
Yep. If I have a 1 kilohertz modulating tone, I will get a frequency shift of 1 kilohertz.
So you could observe this on an oscilloscope?
Spectrum analyzer.
Spectrum analyzer. Okay.
Spectrum analyzer. So that brings up a beautiful question. Okay, so since you can see that on a spectrum analyzer, the question then becomes, well, where do you get a spectrum analyzer? Well, spectrum analyzers historically were really, 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 really expensive. However, due to the magic of digital signal processing, can everybody see this?
Yes.
Okay, so this is called a waterfall display. This is a spectrum display. Notice we have frequency on this case of 14025 to 14065 roughly. This is showing the frequency spectrum of everything for a wide range of frequencies, and I can zoom out and you can see it even bigger. This is the magic of digital signal processing. So there was a mathematician whose name was Fourier. You may have heard of a Fourier transform, maybe not, but Fourier came up with a scheme by which you could take you could take an analog time-based waveform and do something to the waveform and create a spectral analysis of what was inside it. This is the basis for a lot of modulation and demodulation, and the ability to put a spectrum on the screen like this. This is actually done very, very, very quickly in software now. And for instance, in doing so, we can do stuff like this. Not only can it put up a picture on the screen, but we can also demodulate it. This is just a software-defined receiver in Utah. There are hundreds and hundreds of these around the world with antennas that are local around the world. So for us, a lot of them are very far away. We can use these to look and see what is coming in from the airwaves from other parts of the world. For instance, this is in Utah. This is this is about 800 miles from Oregon. From anywhere in the world, you can listen to this. I can also go to an SDR that's in the Netherlands, for instance, and take a listen to the signals that are coming into the Netherlands from all over the world. I have used this, for instance, to listen to my own signal.
Could you use this to see what bands that had the most traffic on them?
Absolutely. So I mean, right now, this is in Utah, and okay, so what we're going to do is pop this open. So this, what are we listening to right now? That's Morse code. Depending on whether or not it's slow enough, you can see that it's actually turning on and off, right? You can actually see the on and off times. But I will ask you something interesting. If Morse code is just basically turning a signal on and off, which it is, like this one, for instance, or this one. But you notice around it, there's like this halo.
Yeah.
Wouldn't you expect that it would just be turning on and off? But every time it turns on and off, there's this halo.
Isn't that
weird?
mean it's ending?
But isn't that weird?
It's weird. What causes it?
What causes that? That is called information theory. That is mathematics. Because the act of turning something on and off means that it is doing what? What's it carrying?
Well, wouldn't it just be the signal getting stronger and weaker as you're turning on and off?
Nope. What is
Wouldn't
that?
it be the carrier wave and the sidebands coming on and off together?
Yeah, but think about it. What are the sidebands? What are the sidebands from just turning something on and off?
Waste energy?
No. The sidebands are the fact that it's the knowledge that it's actually turning on and off. The fact that it turns on and off, if we look at it from a mathematical viewpoint, let me mute that. Oh, that's it. So can everybody see this? Which share is coming up right now? You've got my waveform. Okay, good. So here's my question. So here's a signal. There's my carrier, and I'm turning it on and off. Right? Everyone sees that? Okay, so it's going on and off. There's what the carrier looks like. It's a constant amplitude, but it's completely shutting off and turning back on, right? As it does that, what is this sudden transition from there being something to there being nothing? What shape is that? It's not a trick question. What
Flat
shape
line?
is that?
Flat line?
What shape is this?
Flat line?
Like DC? I mean, it's just...
Yeah. It's actually
Square
a square wave. A square wave contains all kinds of harmonics, all kinds of high frequencies. So the act of turning it on and off, depending on how steeply it turns on and off, generates sidebands. It actually generates frequencies that you can then visualize, even though this is where it gets really, really messed up in your head. And I mean, the first time I saw it, even having gone through information theory in college, the first time I saw this, I was like, wait, what am I seeing? What we are actually seeing is mathematics in action. The fact that anything that carries information has bandwidth. The information is the fact that it's turning on and off. And that is causing the signal to, even though there's just that one tone that we hear, the act of it turning on and off generates bandwidth, which is why it spreads out.
So Scott, can you put it in terms of like
Huh.
music? Like, is that the harmonics for fifths and thirds and
It could be,
like that?
yeah. But the harmonics that are generated in music are generated. They're overtones, right?
Right.
This is called this is information theory. This is mathematics in action. Like if somebody were to just if somebody were to just turn on a carrier and it goes and it never changes, it would have no bandwidth at all. As soon as it starts to turn on and off, it spreads out left and right.
In the music analogy, I also play instruments. I think of that additional information that we see there, kind of like the breath of the orchestra before the note strikes.
Yeah. Well, I mean, what makes a flute sound like a flute instead of just sine waves? I mean, a pure sine wave is a very boring note, right? The fact that there's overtones is what makes a flute sound like a flute. And it makes it sound different than a clarinet.
Because of resonance.
Because there are multiple harmonics in there. It has like, why does my voice sound different from somebody else's who's speaking with the same pitch? It contains different things. Okay, this is another form of modulation. What would you call this form of modulation? Notice on the screen it kind of looks like a player piano, right?
Amplitude?
Yeah,
No?
definitely.
Well, I mean, it's all amplitude modulation of some kind, but this is frequency shift. Because you can actually see the frequency bouncing around left and right. This is a digital signal, and the frequency shift that you're actually seeing and hearing represents information that's being sent. Digital information. How about this one?
Is that like a carrier?
That is not. It's a modulated carrier. That's called frequency shift. That's called phase shift keying, also known as PSK. Now, interestingly, if I can capture that, let me grab a snip of it, and I can zoom in on that.
Can you explain a little bit about PSK and what those?
I'm about
all those
to.
things are?
Yeah. Okay. So I'm about to, because that's an important part of this class. Okay. So I'm going to share, hopefully. You know, I remember trying to teach this stuff before there was very difficult. Okay, so can everybody see this picture?
Yes.
Yep.
Okay, so we were just listening to this. Do you notice at the upper part of this bright patch, it kind of goes left and right? There's a haze around it.
Mm-hmm.
Going downward is time moving forward. At the end of it, you could hear boop, and it stopped modulating. It was just an unmodulated carrier at the end. What do you see right there, right where my cursor is? Notice how it gets really narrow?
Yeah, and then you have a bit of a sideband right there.
Yeah, but that was an unmodulated carrier, and then it started up again with a modulated carrier down at the bottom. That is physically what happens. That was actually phase shift keying, or PSK. And what it does is it spontaneously, let me see if I can find it again. Hopefully there's somebody doing it. I can't guarantee though. Can't can't force anybody to operate any particular mode in the real world. So, and I don't hear anyone. So we may not find it. So those are digital signals again. So the modulating scheme is the pattern that it follows in order to do it. So what we heard was phase shift keying. It was actually altering the phase. Every time there's a phase shift, it indicates a 1 or a 0. You can change by 180 degrees. You can change by 90 degrees. You can change by 270. You can change by 45 degrees. You have 8 different multiples of 45 degrees. So you can actually encode multiple bits at a time. This right here is known as FT8. This is a frequency shift keying mode where it changes to one of 8 different tones. Notice it doesn't take up much space, but each one of those vertical stripes that you see is a different signal, and the software will decode all of them at the same time. This is called FT4. It's a wider mode, but there are only 4 tones for each of those vertical stripes.
So, Scott, are you carrying more information or less information?
Depends on the more or less than what. The more information you carry, the wider the signal becomes.
Okay, okay.
So let's take a look at something like this, for instance. Any idea what this is called?
Good day, everybody.
What mode are we listening to now?
Sideband?
That would be single sideband. Okay, so now let's take a look at this single sideband signal. What is the width of our single sideband signal? 14,300 to 14,303.
Who's the Kilo Foxtrot 6 in San Diego?
That is 3 kilohertz wide. It takes up 3,000 hertz of bandwidth.
Does
Right,
FT8 carry more information than FT4? What's the difference?
Similar, but FT4 only takes half as long. FT8 has slightly more information and more redundancy. FT4 is a very fast mode. Okay, notice I did not change this bandwidth here, this yellow block. It is set for 3 kilohertz. How many signals are we receiving simultaneously in that same area? I can't even count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 20, 25, 30 signals in the same amount of space that we were listening to one SSB signal.
So that would be because voice requires a broader band to carry more information.
There's considerably more information in voice.
Versus a digital, which is much more clean.
No, but digital. In other words, like if you think about voice actually has a lot of information in it. Yeah. One way to represent this, kind of think about this, is what happens if I only listen to this much of the voice? Anyone understand that?
Yes, I get it.
No. Can you understand what he's saying?
It sounds muffled, like
because you're missing information.
That's right, because there's a lot of missing information.
That IBM used to get people.
So that is why, and I also want to point out that he's doing a fabulous job here. He's right at the upper edge of the band, and all of his signal is staying within the band.
I just don't wear it.
So that is excellent. He's doing a very good job following the rules. The band ends at 14,350, and his signal is entirely within the band. So that is doing an excellent job of following the rules. That's something that we're going to cover too. Okay, so modulation. So now we start to looking at modulation and bandwidth. And so here's our frequency spectrum. And we have 0 to infinity. And let's say that we have our carrier frequency. CW, Morse code, takes up about 150 hertz. PSK 31, which is a digital mode, this takes up 31 hertz. That means that you can put 5 of them inside one CW signal. It's 5 times more efficient of use of bands. Let's see, if I were trying to do a single sideband signal, so here's single sideband, that's 3000 hertz or 3 kilohertz. If I took a look at AM, amplitude modulation is a combination of both sidebands and also a carrier. So this would be AM, and that's 6 kilohertz. FM, which is frequency modulation, would look about like this. That's weird. Info? Narrowband FM, that's about 15 kilohertz. So already you can see that different modulation techniques take up a lot different area of the spectrum. So this would be NTSC, which is fast scan television. This takes up 6 megahertz. Not kilohertz, megahertz. So given the amount of space that each of these take up, you can figure out why you will find certain things in certain places. For instance, a 6 megahertz bandwidth signal you will never find on the high frequency bands, because how much room is there down there total? There's only 27 megahertz total. There's not enough room to put those in, to put a signal like that. You will not find a signal this wide anywhere on the ham bands below 420 megahertz because there's no space for it. This is the same stuff that we have when we do commercial TV. So channel 2 and channel 3 and channel 4, channel 2 covers 54 to 60 megahertz. Channel 3 is 60 to 66, then 66 to 72, 72 to 78, and then 78 to 84 if I'm not mistaken. And there's some other stuff in there. And did I get that right? 62. Yeah, that's channel 2, 3, 4, 5, and 6. There may be another gap in there somewhere. But you can see that those low band VHF channels took up a lot of space. They still do. So that's also why the 6 meter radios would very often interfere with channel 2 and 3, because they're very close in frequency. So
What is it interfuse with 2 and 3?
Well, channels 2 and 3, they're down in the 50 megahertz, 60 megahertz range. So when you were on the 6 meter band, 6 meters is from 50 to 54. It was very easy to interfere with those low VHF TV channels. So if I have a CW signal that is 150 hertz wide, and I were to build a filter, this is about practical use. So here's my CW signal, and it's 150 hertz wide. And I wanted to filter out everything else. I could do this and build a passband that was about here. Typically, for Morse code, we would do a 500 hertz narrow filter, and it would all be there. If we had an upper sideband signal, lower sideband signal, this is 3000 hertz wide roughly. Our filter instead would look something like this. We could get away with like a 2400 hertz filter, which eliminates a lot of the outside interference. So this is an appropriate single sideband filter, and this is an appropriate CW filter. That's actually on the exam. Very often, in order to make a filter, what are the components of a filter again, everybody? Let's see if you remember from
Capacitor
yesterday.
and inductor.
Capacitor
Right.
and inductor.
Capacitors and inductors. Unfortunately, it requires a lot of capacitors and inductors to make a filter that looks like this, with very, very sharp walls. So we need something that has an even tighter resonance, because a circuit with capacitors and inductors, when we start talking about filters, we have a passband, we have something called half power points. How many decibels is half power? Let's see if you guys remember that from yesterday.
3.
Okay, so we call these our 3 dB points in our filter. So these are called skirts of the filter. It's basically, you could have a filter that has skirts that look like this. But that also means that the 3D bandwidth is going to be pretty wide compared to what you wanted. Between the half power points. So a filter with narrow skirts, it's actually very difficult to build using just capacitors and inductors. So any idea what we might use for that? Anybody old school?
Transistors?
Nope. It's a piece of rock in between two plates. What is that piece of rock?
Quartz.
Yes, that is quartz. And what is this kind of filter called?
It's a crystal.
That is a crystal filter. Yes, we use crystals because they are rock and they don't change a whole lot based on temperature or anything like that. So they're very, very stable. We use those for filters, we use those for oscillators, we use them for a lot of different things. If you look inside your computer, you will very often find a little metal box that looks about like this, and it says like 9.16 megahertz on it. That's a timing crystal that basically provides the clock for your computer, because it's nice and stable. If you have a wall clock, it's got a quartz crystal in it to keep track, to keep time. They're also the basis for very narrow filters. Okay, so let's see. Let's go back to the book.
What does the quartz do? I guess I don't understand.
Vibrates.
How that
It
works.
vibrates. It's a piezoelectric thing. It vibrates at a fixed frequency. When given energy, it vibrates. And it's a very predictable frequency. So if it's predictable, that makes it stable. If it's stable, that means that it is repeatable, which means it's very consistent.
Does the quartz vibrate always at a specific frequency, or do different crystals vibrate different?
Anyone know how crystal filters get made?
I don't know, but I would assume they vibrate according to their size and shape.
Yep. They trim them down and they make them vibrate at different frequencies. Exactly. Yep. Okay. Yeah, it's basically a vibrating piece of rock. Okay. VHF and UHF voice repeaters are usually FM or PM, FM frequency or phase. VHF packet is digital over voice, so that's frequency or phase modulation. Amplitude modulation, single sideband is a form of it. We normally use single sideband because, unlike FM has this nasty thing called the capture effect. If you have two FM signals on the same frequency, they will wipe each other out, or one will definitely defeat the other one, called the capture effect. So it is impossible to hear multiple signals at the same time on FM. For 10 meters, we normally use upper sideband because 10 meters is right around 30 megahertz. it is above 10 megahertz. That is the cutoff point between lower and upper sideband. A single sideband, SSB, is about 3 kilohertz. FM is about between 10 and 15 kilohertz. So we can stuff more single sideband signals in the same space as FM. One advantage of FM is because most noise is of an amplitude modulated type. FM is very, very quiet as far as noise goes. NTSC is fast scan TV, 6 megahertz bandwidth. That's why we don't find it anywhere low in the low bands. CW is continuous wave, aka Morse code. We use Morse code over continuous wave. So we use Morse code to modulate our carrier. Morse code has a bandwidth of about 150 hertz. An electronic keyer is used to send Morse code without having to go and press a key up and down. Digital communications. Okay, digital just means ones and zeros. Well, so here's a question for you. Let's say that I am looking at some value between 1 and 0 and I get 0.6. Is that probably a 1 or a 0?
1.
That's
1.
right. That right there is why digital communications are better than analog in a lot of ways. If I get a 0.4, what does that mean?
0.
That was probably a 0. That's right. So if there was any noise, I can still guess with a reasonable degree of certainty whether it was a 1 or a 0. If it's an analog signal and I got a 0.6, it's a 0.6. Right? It's not a 0 or a 1, it's a 0.6. What if it was a 0.8 and I got it in as 0.6? That's distortion. Analog signals are easily distorted compared to digital. Digital signals are very resilient. That's why we're using digital now. That's why we use digital television. That's why we use digital audio, etc., etc. The other thing is, once we have ones and zeros, and everything is ones and zeros, we can do all kinds of cool stuff with it. So for instance, if I have a signal that is just ones and zeros, and I'm sending a word, and I have a scheme by which I send, let's say, 5 bits at a time, 0, 1, 0, 0, 1. And I have a scheme that says I'm going to take the sum of all of those. If it's an odd number, I'm going to add another 1. If it's an even number of ones, I'm going to add another 0. What do I have right there?
Empty.
I have 2 of them, so I add a 0. For this one, if I have 1, 1, 0, 1, 0, what do I add at the end?
A 1.
A 1. Okay, so these words then go through the noisy channel. That would be basically the world. And it comes out on the other end. And somebody receives these 2 words, and they get 0, 1, 0, 1, 1, 0, and 1, 1, 1, 1, 0, 1. How many of them are there? How many ones are there in each one?
Odd number.
This one has 3 and this one has 5. Well, by my scheme, I said that I'm never going to transmit a word that has an odd number. This state is bad and this state is bad. And I instantly know that those pieces of information are bad. And I can say they're both garbage, and I send a signal back to here that says they're both garbage, please resend it. That is the power of error detection. That is only made possible by the fact that I can do this with digital communications, ones and zeros. That is why digital communications work so well. This is known as parity. You can add more parity bits. You can add 3 parity bits if you want. You can add complete copy of the entire thing that you sent. And if they don't match, then it was bad. It slows down your overall data rate, but it increases your accuracy. So at that point, you would send back, if there's a packet of information, you would send back a NAC packet, which means basically no acknowledge, which means I didn't get it. Its data's corrupted, send it again. Okay, in packet radio transmissions, you have a checksum. The checksum is basically that extra bit. A header that contains the call sign of a station to which it's being sent. We're looking at it on a global scale. And automatic repeat request. That basically means the data was bad, I need you to send it again. Digital communications mode, well, packet radio, FT8, those are digital. What's IEEE 802.11? Anyone?
Ethernet?
Wi-Fi.
We're using it right now. That's Wi-Fi. Yep. Okay.
Say that
ARQ.
again.
IEEE 802.11 is the scheme by which Wi-Fi works.
Oh.
That's the data encryption scheme, or the data conversion scheme for Wi-Fi. So when you see 802.11 N, B, or G, that's what you're using right now. APRS is a combination of radio and GPS to put information that's sent from point to point on a computer screen. Notice tactical data communications with a map.
I don't see the questions. I see your board.
Oh, well, that's silly. Stop share. There we go. Okay. APRS is automated packet reporting system. That's basically packet radio on a map. So GPS data, text messages, weather data. It can also be like you put it on a balloon, the balloon's traveling through the air. It can be velocity, altitude, barometric pressure, temperature, etc. PSK is phase shift keying. DMR is digital mobile radio. So instead of analog signals, this converts signals to voice, and one FM channel that would normally carry one voice signal can now carry 2 time multiplexed digital signals, making twice as good a use of the bandwidth. And yes, what happens when you do that? What do you think happens to the quality of the signal when you make it take less space?
It's not as clear?
It's not as clear. That's right. You lose some of the fidelity. But it's just voice. You can figure out what they're saying. WSJTX. This is the software package that contains FT8 and FT4. We use it for weak signal. We use it for mapping of our signals. It has a meteor scatter mode, and it also has a moon bounce mode. Moon bounce is a very, very, very slow weak signal mode. FT8 is a digital mode for low signal to noise operation. Mesh is sort of like Meshtastic. It's essentially a self-healing network. And notice what it uses: 2.4, 5.8, and 10 gigahertz. Most of those mesh frequencies are right next to ham bands. There's also something called ARDN, which is the Amateur Radio Emergency Data Network, which is at right next to, again, the mesh frequencies. And the difference being that if you're operating on, let's say, Meshtastic, you're limited in antennas, you're limited in power. You're allowed to encrypt, but you're limited in your coverage. If you move those over to amateur frequencies, because ham radio is something that allows us to build our own antennas and have different power levels, you can run it through an amplifier and also run it through a high gain antenna. You run it through a high gain antenna, your single link might cover 10 miles instead of across the street. Safety. Okay, we are largely made of salt water. As we are largely made of salt water, our skin is an insulator. However, it is possible to puncture the skin, and once you do that, you are in the saltwater bath. At that point, electricity has a really easy path to follow. So, in doing so, all of our signaling from cell to cell, from our brain to our heart, etc., that's all done electrically through very, very low voltage, low current signals. If you introduce a high voltage, high current signal, and when I say high current, 10 to 20 milliamps is enough to disrupt your body. It's not a lot, but compared to the microamps that are flowing through the body normally, it is a big deal. It can make your muscles contract. You get a nice shock. You grab on, you can't let go. You can also destroy cells. You can also heat your tissue and get a burn. Looking at your wires, the black wire, we have at 120 volts, we have black, white, and green. Black is the hot wire, white is the neutral. The neutral is the return line. Usually in most systems it is grounded. The green wire is your safety ground. It is a good idea to have 3-wire signals or 3-wire plugs on all your equipment so that you have a safety ground. The purpose of a fuse is to prevent an overload. If you do get a current overload, it will trip, and either a fuse or a circuit breaker will trip and cut out the hot conductor, in which case you have no more source power. Should never replace a fuse with a bigger fuse or a penny in your fuse box, because it will allow more current to flow, which can burn your house down. If you turn off a power supplies have filter capacitors. If those filter capacitors don't have a bleeder resistor across them, you will store a lot of voltage across the capacitor, and you can get a nasty shock if you stick your finger inside. 12-volt storage battery can blow up, showering you with sulfuric acid. And you can actually, if you outgas, you get outgassing or overheating. Basically, if you have hydrogen gas, that's a bad thing. Antennas and tower safety. Every year there are hams, even very experienced ones, who kind of forget what they're doing when they're moving antennas around and manage to touch power lines. What is the typical voltage of a power line outside of your house? Like out on the street? How many volts?
12,000 volts.
12,000, 13,000, 30,000 volts, right? You don't get any extra chances. So the rule of thumb is that you want to put up an antenna. Any piece of the antenna that, if it falls, has to be at least 10 feet from a power line, period. Don't ever use a utility pole. There's high voltage up there. When an antenna is transmitting, it is transmitting potentially at very high voltages. If you touch the antenna, you can get a puncture wound at very high temperature right through your skin. It's called an RF burn. I've had them. They're quite painful. When climbing an antenna tower, make sure that you're tied off. Never climb by yourself. And make sure that you're trained in doing so. Always wear a hard hat. If you have a ground crew, you should always have a ground crew, because if you get stung by a hornet and you are allergic, you will be unconscious, hanging from the tower, and no one will be there to help you. The other thing is that ground crew, make sure that they're wearing safety gear so that if you are carrying tools, since you're going up on a tower in the first place to work on something, you're undoubtedly carrying tools. What's going to happen to those?
They could fall.
They're going to fall. Especially if it's really cold, you're wearing heavy gloves, you're going to drop something. You don't want to clock somebody down below in the head with a wrench that you dropped. If you have a crank-up tower, you need to only climb it when it's retracted, or if you have locking devices in place, the manufacturer will specify those. A turnbuckle. Okay, so a guide tower is unstable by itself. Essentially, you will use multiple guy ropes to put tension on it to make sure that it doesn't fall in any one direction. To keep the tension on there, we use turnbuckles to basically tighten up each guy wire. Those tend to vibrate in the wind, which tends to loosen them up. So we put a wire through those turnbuckles to keep them from turning. Grounding requirements, we follow local electrical code, whatever that happens to be. There is an entire science of grounding and bonding, which is a very good idea. Lightning does not follow rules that we enjoy, right? Lightning does certain things. Lightning does not like to go around corners. Lightning does not like to go around tight bends. Lightning will follow any path that it can, including jumping from an electrical wire to the ground in order to get to ground. So you want to, if you're trying to prevent lightning from destroying your system and from hurting anyone, you provide lightning with as comfortable as a path as it can take to get to ground. So that means big fat wires. It means a spike driven way into the ground. If you have a tower with 3 legs, you're going to end up with 3 ground rods, one for each ground rod, one for each leg of the tower, and then you're going to ground them all to each other to make sure that any lightning that hits, when it decides to take the path of least resistance, finds the path of least resistance that you have given it into the ground.
So 8 foot, literally an 8-foot piece.
An 8-foot piece of copper-clad steel. Pounded
That you
into
have
the ground.
to try to get into the ground. Okay.
Yep. Pounded into the ground.
Yeah, not here, but yeah.
Well, sometimes it means breaking through rocks.
Exactly.
Yeah, but you can do it. You use a one of those little, you lift a weight and go bam and let it fall on it, and that knocks it in a couple inches, like a post driver.
Yeah, here you have to, if you want to dig a 6-inch hole, you have to dig a 12 to 18-inch hole, put it down, and then fill it in.
Oh, yeah. Well, you're going into permafrost, right?
No, it's the rocks here.
Is it rocks? Okay.
Yeah, the guy that drilled my well, he ended up breaking 2 bits, putting a well in 80 some odd feet. So yes.
Yeah, but there are people who are good at doing that. Maybe you don't want to do it yourself. So avoid sharp bends. Okay, so why should you never solder any grounding conductors?
The heat of lightning would melt
it. It heats up, it'll
That's
melt.
right.
And
That's right. As soon as you get hit by lightning, it gets hot enough that the solder will just melt. So welding or mechanical connections. Okay, RF radiation. Yes, radio frequency is radiation. It is electromagnetic radiation. It is basically photons. They contain energy. They have wavelengths. Above visible light, you get into ultraviolet and X-rays. Ultraviolet exposure and X-rays can cause cancer, right? The reason that they can cause cancer is because those photons have enough energy when they strike DNA to basically do damage to the DNA, which causes mutations. Occasionally, one of those mutations will turn into a cancer cell, and then you end up with cancer. You can also just end up with the cell dying, for instance. Radio waves do not have that ability, just like infrared. Infrared can cause heating. Radio waves can cause heating, but they don't have enough energy to actually do any damage to cells on a cellular, molecular level. That doesn't mean that radio waves are completely safe, though. Does anyone know how a microwave oven works? Anyone?
Activates the water molecules.
Yeah, it agitates.
Yeah. Okay, so a microwave oven is a 1,000 watt radio transmitter inside a box. And at 2.4 gigahertz, which has a wavelength of about 12 centimeters. So what that means is that essentially you have about 1,000 watts of RF energy inside your microwave oven. You put your cup of water in it. It turns out that 2.4 gigahertz is about the resonant frequency of water molecules, which means that if there are water molecules to be found, that energy will be transferred to them, which causes them to vibrate. Vibration is movement, movement is heat, and guess what? You get hot water, which is actually a brilliant way of doing this. So what that also means, though, is does anyone ever experience it when they turn their microwave on, their Wi-Fi goes out? I hope not, but I have had it happen. And the reason that happens is if there's a little bit of microwave leakage coming out of the oven, it will interfere with your Wi-Fi because they're basically on the same frequency band. So here's another question with regard to that. So let's take a look at, I don't know why I can't get this to work today. Let me unshare that and do a share over here. So let us say that we now have microwaves and we're going to draw a microwave. That's a wave. And then we're also going to have light, which is like a super high frequency. Your microwave oven has a door which has a bunch of holes through it. People have probably noticed this, which you can then see through. How come you don't get blasted with microwaves, but you can still see through the oven door?
Isn't it point to point?
No.
Waves can't get through the wavelength.
That's right. The wavelength of the radio waves is long enough that those holes are basically non-existent. But for light waves, those holes are gigantic. So light waves can pass through, radio waves can't. Essentially, you have a Faraday cage, as you said, for the radio waves, and you basically have a porous set of, porous door for the light. So you can see the light coming through, but you can't get it, but you don't get any radio waves out. Okay. Next. Okay, notice this FCCOET Bulletin 65. There is this big mathematical calculation of what makes safe radio. How much power at what kind of distance. Out on the web, because that is really the best way to do it other than walking around with a calibrated field strength meter, which is basically just measuring RF energy. It is not a simple task to actually go through the calculations. So what somebody has done is, if you look up an RF exposure calculator, it will find, oh, look at that. Somebody already did the work. Average power at the antenna, that means time averaged. So let's say you have a 100-watt transmitter, but you're only operating 10% of the time. That means you have an average power output of 10 watts. So we're just going to assume that. Notice here, this says dBi. Enter 2.2 for dipoles and 2.2 for antennas rated in dBd. We were talking about dB yesterday, right? Everybody remember that?
Yes.
Okay. dB is compared to a dipole. dBi is compared to an isotropic radiator, which is an imaginary antenna which has the same amount of power in all directions of a sphere. So if you had the energy and it was distributed in all directions, that would be an isotropic radiator, which does not exist. But some antennas, to make them look better, are actually rated in dBi. So if you have 1 dBi gain, that's actually a pretty terrible antenna. It's worse than a dipole. So we're just going to assume a dipole. So we'll enter 2.2. We're going to be 2 meters away, and we're going to be at 50 megahertz. And is it safe? Yes or no? When you build a station, this is what you go through. A controlled environment, controlled environment means that I put a fence around it, or it's on my property and people can't just walk up to it. An uncontrolled environment is what we do at our museum station. We have people walking into and out of the building all the time. We can't control everybody. There's an antenna on the roof. Is it safe for the people down below in the museum? So we go through this process. We run the calculations. Anytime you replace or repair something, you go through the process again. You run through. You print out your results. You post them somewhere, and everybody's happy. This is actually a requirement of creating a station. Okay. Exposure limit. Why do exposure limits vary with frequency? The human body absorbs more energy at some frequencies than others. It turns out that 50 megahertz is your worst case scenario as far as human body absorbing energy. I guess we're closest to resonance at that point. One thing you can do if people are being exposed to radiation and it's unsafe, you can cut down your duty cycle. You can also relocate your antennas. You transmit less time. You can put up fencing if you're able to keep people away. If you've ever seen an AM transmitting tower, it could be out in a park or something, and there's like a fence 30 feet, like a round fence 30 feet around the tower that says keep away, high voltage, it's because they don't want anybody in the field any closer than 30 feet. Station setup and operating controls. Okay, so this comes back to whose law?
Ohm's law.
Why are short heavy gauge wires used for transceivers DC power connection? Most transceivers run on 12 volts DC these days so that you can run them off of a battery. It also means you don't have to carry a full-time power supply inside the radio, which makes them smaller and it makes them lighter. So, Ohm's law. Why do we use short heavy gauge wires? To reduce voltage drop. Because the longer the wires and the narrower they are, the higher the resistance. By Ohm's law, what's Ohm's law? E equals I times R, and P is equal to I times E. So if you have a lot of resistance, you'll end up losing power, which heats the wires, and you'll end up losing voltage, which might make your equipment not work. So let's talk about efficiency.
Sure.
So efficiency is simply let me erase. And that's in percent, is power out divided by power in times 100. Okay, so if I have a radio and I've measured it and it has 13.8 volts at 10 amps, what is my power that I'm consuming? Ohm's law says P equals I times E, which is 138 watts. At 138 watts, I am generating 50 watts of RF. My input is 138 watts of DC. So what would my efficiency be? Approximately. What do I get? Anyone with a calculator handy?
36%.
I would go for that. All right, so I have about a 36% conversion of energy from DC to RF. Most transmitters will have a power into the transistor compared to out of about a 50% efficiency. So where does the other power go?
Heat.
Heat. What else? Does the transmitter have lights? Does it have a display? Probably. Does it have a fan that's running? A fan runs on electric power. Everything runs on electricity. So that all feeds into it. And that's why to run a 50 watt transmitter, we typically have at least a 10 amp power supply. And if you look in the book, I think the answer is something similar to that. Let's see what the book says. Okay, they say 13.8 volts at 12 amps. So I would say at least 10. The answer in here is 12. Excuse me. Okay, computer.
I got 10 for my 50 watts. It never worked. I needed 14 for the 50 watt.
There you go.
H2 and the ICOM.
There you go. So what's a way to get away with a smaller power supply, everyone?
Well, turn the power down.
You turn the power down. Yeah, exactly. You run 25 watts, it only uses half the power. Okay, what signals are used in a computer to radio interface for digital mode operation? Receive audio, transmit audio, and transmitter keying. Basically, the computer is responsible for generating and interpreting the audio. So you have to have ways of sending audio information to and from. Most computers will have a microphone input and a speaker output. Some of them will even have a sound card built in. Some radios even have a sound card built in. so that the computer can just basically take audio signals and move them back and forth.
So this may sound like a stupid question, but how do you hook your radio to a computer? How does that work in your set in
Do you
setting
have a
that?
microphone jack on the radio?
Yes.
Okay. Do you have a headphone jack on the radio? I'm sure you do. A speaker plug?
Yes.
Yeah. Okay. So what you do is you wire up the speaker. Audio comes out of the speaker jack that would normally go to the speaker, right? You wire that to the microphone in on the computer. And the speaker out of the computer, you wire to the microphone plug on the radio. And
Okay.
then you have a ground circuit that grounds the push to talk button. And when the computer does that, it switches the radio from receive to transmit, and then it sends audio to it. And then when it wants to receive, it releases that, and it interprets the audio coming out of the speaker in the computer, in the radio. Essentially, it's doing the job of you pushing the push to talk button and listening to someone and speaking. The computer is now doing the job. A lot of the newer radios will actually have a sound card built in so that the computer basically just connects to the sound card in the radio and takes over the radio at that point. If you have an older radio without a sound card, you essentially have to design and build the sound card.
Okay, that's what I was going to ask. Okay.
Yeah, you basically will build a wiring harness. Or you can buy something like a SignalLink USB, which is an external sound card, which when you plug into your computer takes over the sound card, and then you build a wiring harness from the sound card to the radio.
All right, thank you.
Mm-hmm. Okay.
My Kenwood's older.
Yep. I actually, I can relate. When I had my Kenwood 520S, I actually built a wiring harness so that I could run 1200 baud or 300 baud packet over HF with it. I built my own wiring harness and connected it to my packet TNC. It worked great. It was slow, but it worked great. Okay, so now we're talking about ferrites. Okay. So you will see in the next, the next couple of sections, we will continually talk. Many of the questions have this word in them. What is distortion? Come on, this is an interactive class. What's distortion?
Inaccurate demodulation,
or just inaccurate something. This is hard right now because you probably have a hard time hearing what I'm hearing. Or if I put my mouth way up to the microphone and start yelling into it, my signal might be distorted because you can no longer pick up the whole thing. It's over-modulating. Distortion is something on the signal that isn't supposed to be there that reduces its intelligibility. There are so many ways to distort a signal. Let's say that it's supposed to be this big. And I have over-modulated it, and my signal looks this big. And it gets to the other end, and it can only get up to this level. It can only receive signals up to that size. What happens to all of this stuff up above and down below?
Gets lost?
It gets lost. Lost signals that would contain information about my voice. In other words, I am now distorted because some of the signal got lost. What if I was talking into a radio and my radio was expecting my voice to look like this? And instead, I got it really close to my mouth and it's doing this. And the amplifier is only looking for signals in this range. What happens to all that stuff above and below?
Dissipates into the ether.
It just disappears. And then I'm left with a clipped signal. I'm overdriving it. What happens if I have a signal that actually makes it to the other side and it looks like this and it's perfectly fine, except that there's another nearby signal that looks like this? And my receiver picks up both of them and adds them together. And this one is noise. What will happen to my voice when it tries to pick it apart?
Garbled.
Yeah, it's all garbled, right? So that noise can come from any number of different places. This section is about figuring out where that comes from. So the first thing we're going to do is discuss a wire carrying a current. It's going to be carrying an AC current back and forth, back and forth, back and forth. So that's our current. Any wire that is carrying a current is generating what?
Electromagnetic fields.
In particular, which one? Current generates what?
Magnetic field.
Magnetic fields. Okay. So current generates magnetic fields. What happens if I place another wire right here? And here's
You'll
the magnetic
induce
fields.
a current from the magnetic field.
Yes, I will induce a current in the magnetic field, and this other wire, because any wire will function as what? Any wire is an antenna.
Conductor.
An antenna. It will it will induce a magnetic field and a current to flow back and forth in that other wire, which is some smaller copy of the signal that is on the first wire. This is known as crosstalk in practical terms. If these are microphones, what happens? If these are if these are wires carrying audio signals, what happens to them? They bleed into each other. Right? So there's a couple of things that we can do to prevent this from happening. Number one, here's our center conductor, and here's our shield.
Coax cable shielded.
And we do this, and we ground it. So if we have a signal that is on the center conductor and it's generating magnetic fields, what happens to the magnetic fields when they get out here? They get to the shield, they might induce a current. Where does the current go?
To the ground.
To the ground, which means that if there's another wire over here, how much of the magnetic field is going to be there?
Nothing.
Nothing. We've protected it. That's why we use shielded cables. It makes sure that we don't get crosstalk. If we want to really be safe, we would do this and shield both of them. Then they're really safe from each other. Okay, so here's another one. Let's say we have a piece of cable that is coming down from an antenna, and it looks like this. All right. Okay, so here's our cable coming down from our antenna. It's hooked up to our box. And all right, so there is something in RF, and RF stands for what?
Radio frequency.
Radio frequency. This is a very high form of alternating current. Okay, so there's a nasty feature of alternating current when it comes to conductors. If we were to draw a piece of wire that looks like this, here's the cross section, and we pass DC current through it, it would fill the entire space with an even density of current. If we, instead of doing AC, we went to DC, the current density would start to look like this. Where's the current flowing?
This is AC?
This is AC.
Around the edge.
Around the edge. This is something called the skin effect. And this is caused by electromagnetics and how conductors react to current flowing in alternating current. AC travels around the edges. The higher the frequency, the closer it travels to the edge. So this has some unwanted effects. If we are at a really high frequency AC and we have a conductor, what will end up happening is that here's your conductor. Virtually all of your current flows around the outside. It can fill up such a small space that now we're going to take a look at our coaxial cable here and ask a question. How many conducting surfaces are there on a piece of coaxial cable? Here's the center conductor. What is this outside made of right here? What is that outside conductor made of? No, that's the insulator. What's the outside conductor made of? It's copper.
Braid wires?
It's copper. It's
Depends
braided
on-
copper. Typically braided copper. All right. What's braided copper? Copper's
Lots
what?
of little wires.
Copper's a bunch of wires. That's right. Okay. So it's a conductor. All right. What did we just say about the skin effect? The skin effect. What did we just say about the skin effect?
It
So
goes
it's gonna be-
outside.
Yeah. Well, it goes on the surface, right? So I'm going to ask that question again. How many surfaces are there?
Unbraided?
Yeah.
Be a lot, right?
There's one. And then there's two. And then
Inside
there's
and
three.
outside of the
Inside
shielding.
and outside, they can carry different current. So the inside and the center conductor, this is a matched pair because that's a closed world. But how about number 3? That's on the outside. This is something called this can carry something called common mode noise. Inside the coaxial cable is a closed system, right? Ideally, there's no leakage. But what can happen is then you can have a separate current, a completely separate current flowing on the outside of that cable. So let's say that I build an antenna and it looks like this. And here's my cable, and my cable looks like this. Okay, and I have power going up to the antenna that looks like this on the inside. I have a matched system where I have inside and outside. It's a closed system internally. But what is that outside piece of the outside shield, the outside piece of wire? What is being generated by that antenna? What is the whole point of an antenna?
Send out radio waves.
Send out radio waves, exactly. So send out radio waves. That coaxial cable is doing what? It is sitting in the electric field, isn't it? It's sitting in those electromagnetic fields. And it is essentially a piece of wire. So what is it doing?
Acting as an antenna.
It's acting as an antenna, and it is picking up some of the signal that's being sent and sending it back into what?
The radio.
Into your radio. And where is the outside of the cable connected to? The body of the radio, also known as the chassis.
Right.
So all of a sudden, what do you have collecting on your radio? On the body, on the metal case.
Electrical charge.
Yeah, you have RF getting into the radio itself.
Does this happen on the handheld radios also?
Heck yeah. So this is depends on the cable, but yeah, this is just what happens in the world. I mean, this is what RF energy does. So now you have, let's say, RF energy right here. And let's say that connected to the radio, you have a microphone. What happens if the shield of the radio conducts RF energy into the microphone? When you speak into it, what will happen? What would be your guess?
Distortion.
You'd get distortion. What happens if, let's say, that your microphone is actually carrying 50 volts on its surface and you lean forward and the microphone is made of metal and you transmit and you lean forward and hit it with your lip?
Shock.
Done that. Been there. Very, very surprising. But that is an example of common mode interference. Basically, your cable becoming an antenna and bringing back RF into your station, onto your equipment. So we have a way to prevent this from happening. So, because there's always a solution, right? Okay, so what we have is something that looks like a donut. You may have seen one of these before. They could look like this. It has right? It could be a hole all the way through, etc., etc. Typically, it's going to go all the way through. All right. So this is usually made of iron and manganese and let's see, iron, manganese, and nickel, and a few other different materials. These are all very special because they're ferromagnetic materials. Ferromagnetic means that they are typically going to be able to sustain a very, very large magnetic field inside them. So, every current generates what kind of field? Come on, everybody. Every current makes what kind of field? Yes, okay. So, as the unwanted current is flowing on the outside of that cable, it will be generating a magnetic field, and all of a sudden it encounters this thing which is made of like iron powder, all baked in a shape of a donut. And the magnetic field says, ooh, I like it in here. The magnetic field gets concentrated in here. And as it goes around and around, this is designed so that it is going to basically circulate and burn it off as heat. If it burns off the magnetic field as heat, how much current is left on the other side that made it in the first place? Exactly. So what has this thing done? It has taken the unwanted current indirectly and destroyed the current by absorbing all the energy from the magnetic field. These are known as ferrites.
Will those ferrites affect your actual transmit power at all, by chance?
Is the inside connected to the outside at all?
It should not be, no.
It is not. It has no impact on it whatsoever.
Got it.
They are
so do you have one of
completely
these?
isolated.
Do you recommend putting one of these on your system?
If you have a piece of cable and you're getting problems with radio frequency interference, this is one of the fixes.
Got it. Thank you.
So, can anybody point out somewhere nearby where they might find one of these things? And can maybe
my printer cable.
On your printer cable, laptop cord. Where else? Some cell phone chargers.
You went on a USB cable.
USB, yes. My USB cable on my radio was picking up RFI and causing my computer to lock up. I ended up putting 5 ferrites on my USB cable, and that created enough attenuation so that I could use my USB cable with my computer and my radio.
Wow.
Yep. Ferrites are your friend. And fortunately, Ferrites, in addition to being the basis for a lot of transformers, I'm going to go to a company called Ferrite. You can guess what they largely make. Anyone guess what they make?
Ferrite.
They make ferrites, yes. So they are the largest manufacturer of ferrites in the world. And notice there's engineering kits and there's all kinds of different shapes. Here's oh, look at that! Cores for common mode chokes. And notice there's all kinds of graphs and charts and number of turns and different types of materials. Different types of materials respond differently for different frequencies. What do you know? There's material 75, material 52, material 43, 31. They all have different frequency response. They all have different attenuations. And you can get them in all kinds of different shapes and sizes. You can wrap a cable around it multiple times. You can get a long one that you can just pass a cable through. Another thing you can do is, depending on what your problem looks like, you might just be able to take your coax cable and do this with it.
How do you know which one you need?
You try it.
I was going to say, how did you figure out that you needed a ferrite? How did you diagnose that
Because
on
my
your
computer
USB
kept
cable?
rebooting. My computer kept shutting down. So you can take your cable and do this with it.
Okay, but how would your computer shutting down? I don't understand the logic to that.
When I transmitted, my computer shut down.
Oh, when you transmit it.
Yeah.
Okay.
You can take a piece of cable and just wrap it like that. What is that? I mean, what? That's a coil, isn't it? That's
Scott,
an
I just
inductor.
dropped a note into the group talking about that.
Oh, there you go. Yep. So at the feed point to your station, a lot of people will just do that with the cable. Wrap it around a plastic coffee can. When we were on Wallace Island, one of the guys in the group was having a problem and on 160 meters. So he took a lawn chair that looked like this, right? So it's got 4 legs, and he took the cable and did this with it, and then fed that to the antenna. Do you think it worked?
Must have.
It did, yeah, because it's a coil.
Just coiling your coax will work.
It can, depending on the problem that you have. The nice thing about having a ferrite core is that it is much more efficient at doing it. But this works.
Can also create problems too, though, right?
Hmm?
Having a big coil of coax, right?
Oh yeah, it took a lot of cable, but you know.
So my question is, would it behoove me to simply put a couple of chokes covering the range of frequencies on it just to begin with?
If you need it. I mean, I rarely need it. You'll know if you need it. It can never really hurt. All right, everybody, how about a 5-minute break?
Okay.
Weekend, ugly balloon. You want to choke your RF common current. Stick around. We'll show you how it's done. You will need about 4.6 meters of coax cable. I used RG58. 2 connectors of your preferred choosing, and 50 mil outer diameter.
Whoever's playing that YouTube video, please turn off your mic. Please mute.
Okay, dear audience. Well, if you like choking as much as I do, you
Are you stuck indoors? You want outdoors? I can let you back outdoors. And should be paying attention to man, not poor kitty. Poor kitty. Not getting mommy's attention.
Hello, hello, hello. Hope everybody had a nice bio break. Buddy in one of my last classes called it a bio break. A bio break, and I thought that was great. It was a bio break.
God, how was your holidays?
Oh, so far so good.
Good to hear. And
Yeah.
it's 4 p.m. Eastern, right? 1 p.m. Pacific.
Which thing are we talking about?
The
When we
general.
start to roll into the general, yeah. But now you can see why I kind of hope that people would show up early.
Yeah.
Because there's a lot of stuff that I cover.
No, there absolutely is. I was just typing to the group that when I took this, it helped so much
Yeah.
for my technician exam.
Yeah. So.
And then I put it out to my radio club too, so you might have
Cool.
heard from some others.
Excellent. You're obviously in New York.
Yeah.
Where in New York are you?
Long Island.
Long Island?
Yep.
Which-
I was in Pennsylvania when you gave the class.
Okay, but where on Long Island are you?
Long Beach.
Long Beach. Okay. My cousins are from Plainview.
Oh, that's like 45 minutes from me.
Yeah. My dad used to work in Huntington.
Oh, nice.
And then Riverhead.
Ah,
He
yes.
commuted for like 4 months from Queens, like Fresh Meadows, Flushing, to Riverhead for 4 months.
Well, at
He
least
said-
it was hopefully a reverse commute.
It was largely, yeah. It was still a very long drive, but
Yeah.
and when you got to Suffolk County, it was easy. So
Yeah. My radio club I just joined is in Yaphank, out by Riverhead.
Yaphank. Yep.
Yep. So it's an hour and 15-minute drives for meetings.
Oh, geez.
All right, I'm going to bounce around, but 4
All right.
p.m.
Well, yeah, I would say so.
All right, perfect. Thank you,
Cool.
Scott. Enjoy,
Yep.
everyone. This is a great class.
I appreciate that.
Of course.
All right, here we go, everybody. We're going back to where we was with regard to chokes and filters and stuff like that. Okay. Everybody back from break? I hope.
Yep.
Okay, I heard one person. One person speaks for everyone. So, okay. So, a ferrite choke is a way of filtering out high frequencies and allowing low frequencies to pass. There are lots of ways. Essentially, a ferrite choke becomes a kind of a filter. You can use a capacitor as a filter. When the phone company used to own all the phones and everything was wired, if you had a ham nearby and they interfered with the phone lines, they would come out and they would, for free, put a filter on your wired telephone. It was a low-pass filter so that it would block all the RF from getting out. So, notice this is another question with regard to that skin effect. Why do we like flat copper strap as opposed to cable when we're doing bonding at RF? Why do we like flat copper strap? Where does current flow at RF? Inside or on the surface?
Surface.
Okay, which has more surface area? Something that is round or something that's been pounded flat?
Flat.
There you go. So flat copper strap is better for grounding.
Is that what you use when you're doing the grounding for your antenna? The bonding, I should say. It says bond the legs together.
I don't think it matters at that point. You just want to use because that's for lightning. Okay, so this is a good opportunity to discuss the difference between grounding and ground and RF ground, and they're really different things. Okay, and it really comes down to an understanding of what the difference is between voltages, right? All right, so what is the frequency of DC? What frequency is DC?
Nothing.
Zero. Okay, let me see if my pencil is working. My pencil is not working, and I don't know why. All right, it says it works, but it seems to not be. So I'm going to take a little break from that, if I can. Okay, so I'm going to try one more time. Yeah, okay, there we go. All right, so DC is 0 hertz. Okay, what frequency is power? Wall power.
Hertz. But if you look on a frequency counter, it says 2.
Yeah, it's 60 hertz.
Why, when you put the frequency counter next to the AC power, does it do that? Unless it's a long.
AC is 60 hertz. Okay,
Yeah.
what frequency is RF? That's typically in the megahertz. These are 3 completely different beasts. So, AC and DC in here, we usually consider those to be power. And those are grounded in one way. And this is RF. RF is RF. I mean, it's a totally different beast. It behaves very differently. So while I go ahead and I shut down my iPad and restart it again because it's behaving weird, I'm going to ask this question: what is the wavelength of AC power at 60 hertz? What is the wavelength of AC power? Come on, somebody get this. at 60 hertz. How fast does light travel? $300 million divided by 60? 5 million meters. Or 5,000 kilometers. Or LA to New York City. That is the wavelength of AC power. The entire width of the United States. What is the wavelength of the 10-meter band?
10 meters.
10 meters, okay. For 10 meters, it's 10 meters. What is the difference between 10 meters and 5,000 kilometers? It is a completely different beast. Okay, so now what we're going to do is we're going to draw, here's our equipment, and here's our ground rod driven into the ground. And we are going to have a cable length of, let's say, 30 meters long. We're going to use our house wiring. Okay. How long is AC power's wavelength? Remember what we just put on the screen?
5,000 kilometers.
5,000 kilometers or 5 million meters. Essentially, at AC power, this is 0. That cable has no length compared to AC power. How about compared to a 10-meter signal? $30 meters is pretty darn long, isn't it? 30 meters is pretty darn long, right? Okay, we only know one thing, that 0 volts occurs right where that spike goes into the ground. Does everyone agree with that?
Yes.
So, do we also agree that every piece of wire is an antenna?
Yes.
Yes. Okay. Do we not agree that we can actually have waves forming so that the voltage on that is 0 at ground? Can we not have waves that look like this on that ground line?
No, dude, I'm a star.
Can we not have it so that we have 0 volts at the ground line where it goes into the ground and other voltages on that line as it would go away?
Yes.
Sure. Okay, so what if we have 50 volts right here? Can we still have 0 volts right here? Yeah. Does anybody see a problem? We have a ground, right? Our system is, quote, grounded. Does that mean that our equipment is not at a different RF voltage? It's at 0 volts when it comes to power, but we might still have 50 volts of RF on it.
Is it short?
No, you get a shock. You get a shock. So what does that mean that we really want to do with this ground line? Depending on the frequency that we're using, 30 meters is too long. We want to make this as short as possible. And just to keep in mind that ground is not the same as ground. Depending on the frequency you're using, ground can be different things. It can behave differently.
I'm a little bit. That's my coax cable.
No. That's your safety ground that is protecting you from getting an electric shock.
Yeah,
in other words, when you plug your equipment into the ground, when you plug your equipment into the wall socket, there's a ground, right?
Yes.
Right? What is the purpose of that ground?
To ground your case or whatever.
That's right.
Like on a washing machine or
right.
Or
to keep you from getting a shock.
Right.
Right? Okay. That assumes what frequency is power?
The
60 hertz. It's 60 hertz. Right?
Oh.
It has a wavelength of 3,000 miles long. So let's say you live on the 10th story of an apartment building, and the cable has to travel 200 feet before it goes into the ground. What is 200 feet compared to 3,000 miles?
Nothing.
Nothing. Essentially, for power, ground is the same everywhere in your building. But what does that also mean? If you are 200 feet away from ground, right? That's 65 meters. And you have a wire that is 200 feet long, and and you're transmitting on the 10-meter band. What is that piece of wire going to pick up?
The transmission of
That's right.
that.
And it's actually going to cause it. The only thing that has to be true is that where it is connected into the earth, by definition, it is being held at 0 volts, which means as you move away from it, it is carrying waves. And what is the wavelength of those waves? 10 meters. Right?
Right.
Right? Which basically means that by the time you make it back to your equipment is at safety ground for power, but it is not at RF ground. They are totally different things.
Yeah.
So just keep in mind that the frequency determines whether or not your system is actually grounded. And
so then you not only, because you haven't hooked this radio up yet, so you're saying that from the back of that Kenwood, I would have my coax cable that's going to my antenna, and I would also have a ground.
Going to earth ground.
Going to earth.
Yep. You would take all your components and you would connect them to like a ground bus, a common point, and then you'd take that and drive it into a stake in the ground to try to get everything at the same voltage. And hopefully the wire's short enough that you won't have stray RF floating around in the shack.
My cable's gonna end up being approximately 25 feet.
You'll be good, most likely. That's not bad at all. But if you start getting like really far away, you'll see stuff. I mean, I actually got that RF burn on my lip on a station that I had grounded, but it was 50 feet to ground. There was still RF voltage on the case because I was far enough away from ground that at RF, ground wasn't ground anymore. Trippy, right?
Yeah.
RF is a different beast. It behaves differently. You have to treat it differently. Okay, distortion. If you tune an FM receiver above or below a signal's frequency, it'll be distorted. If you transmit with too much gain, it'll be distorted. You notice a common theme here. If you have too much, if you have signals coming in from nearby, the signal can get distorted. If you're being interfered with by another nearby transmitter, your signals can be distorted. If your handheld battery is going low, your signal can be distorted. If you are over deviating or over modulating, that means you're talking too loud into your radio and you're overdoing it. The amplifier is being overloaded and you'll sound distorted. So you can reduce the audio gain. If you move away from the microphone, that does the same thing. Most transceivers, a transceiver is a transmitter and a receiver, have a keypad. Most of them have a VFO or variable frequency oscillator knob that used to be connected to a variable capacitor. Now it's usually connected to a little microprocessor through an encoder that allows you to change the frequency. Most transceivers also have memory channels now. Unlike your Kenwood 520, which does not, you basically have, that is actually connected to an actual air variable capacitor when you tune the tuning knob. An FM transceiver has a scanning function. You program all your different frequencies into memories. You hit scan and it scans through them all very quickly. The squelch function, we can very easily demonstrate what squelch does using our, assuming I still have it open, which I hope I do, which is the northern one. There we go. Hopefully everybody can hear. Going to turn on the squelch. That's squelch. When there's nothing to listen to, it mutes the receiver. If there's a signal there, when there's nothing to listen to, it mutes the receiver. That's what squelch does. Some people like squelch, some people hate squelch. What it means is that if there's a weak signal there, you won't hear it. So if you're trying to listen to weak signals, you would take the squelch and you would turn it all the way off. Okay. So that's squelch. Repeater offset. Okay, so an FM transmitter that is transmitting into a repeater. This is a good idea to talk about what a repeater is. A repeater is a combination of a transmitter and a receiver built into a single box with a controller in between them. The purpose of a repeater is, quite literally, to take a signal that is coming in from somewhere and retransmit it on a different frequency, essentially repeating it so everybody in the world can hear it. The point of that is that if you are, let's say here's a mountain, pink mountain, with a repeater on top. Inside here you have a receiver and a transmitter and a controller. So people from everywhere will be transmitting on a frequency. Depending on where they are, they'll be transmitting on the receiver frequency up here. When that signal is received, that signal is then sent to the controller. The controller says, is this a worthy signal of retransmitting? If the answer is yes, then it sends it to the transmitter and it gets retransmitted on the repeater's published frequency so that everyone in the area that is line of sight from that system can hear it. Essentially making this person down here sound as though they are up here on top of this mountain, which is a great benefit because, as it turns out, these two people probably can't hear each other directly. So we have these great towers in Oregon, for instance, known as mountaintops. Mountaintops are wonderful 3,000 foot, 5,000 foot antenna towers. You put a repeater on top of it, and everyone sounds like they're on top of the mountain. The other nice thing is that you could be 100 miles away, and if you have a 2-watt handheld transmitter, you could be able to talk to somebody who's on another 2-watt transmitter 100 miles away using this repeater. The offset is the differential in frequency between the receiver and the transmitter. On the 2-meter band, it's 600 kilohertz offset.
Is there usually a range of frequencies for this repeater, or is it one frequency?
It operates on one frequency. There are repeater pairs that have been set up, and they're basically allocated by a central organization in that particular geographic region. Davis.
Scott, we're in the Willamette Valley.
Yep.
Where are the repeaters that you're hitting?
Coast Range, and a lot of them are in the Coast Range. A lot of them are up in the Cascades, which gives them an enormous range.
Is there ever conflicts with like multiple people trying to use the repeater at the same time?
Yeah, you figure it out. Basically, there people for a single repeater. I mean, that's called a double when that happens, and there's no point doing it because nobody wins. So people usually behave very well. One time that you do get into some issues sometimes is if you have multiple repeaters that are tied together so that their audio is pumped into multiple different ones on adjacent mountaintops. And two people can sometimes, transmit and you get like a mixing of the audio being sent out of both repeaters at once. So your radio is then programmed with the offset, and the offset determines whether you transmit above or below the repeater's published frequency. Our repeater here in Eugene for the club is 146.72 megahertz, and it's a published offset of negative 600 kilohertz. So that means that it listens to 146.12 megahertz. When you transmit, if you have the offset programmed correctly, your handheld radio or mobile radio will automatically shift down 600 kilohertz and transmit on the correct frequency. The other thing about it is that there are two other keys that have to be sent, potentially. There's CTCSS and there's DCS. These are basically literally keys to open up the repeater system. One is a subaudible squelch tone and the other one is a digital coded squelch. The reason for doing that is to reduce the chance of interference and unwanted signals getting into the repeater system.
Scott, when you use this repeater, how far can you go? Who can you talk to?
Well, let's say that we have a repeater on Prairie Peak. Prairie Peak is at 3,500 feet in the Coast Range. It's line of sight all the way up to Portland, all the way down to just north of Medford, 50 miles out into the ocean, and across the Willamette Valley up to the peak of the Cascades. So if there's somebody in that entire area with a decent antenna who is also line of sight, anybody within mutual line of sight to the repeater can talk to each other. Which means from Eugene, I'm using a handheld radio and I'm talking to somebody who's in their car driving up in like Longview, Washington. And they have a nice shot down the valley from Longview all the way down to our mountaintop. I can talk with my handheld radio to somebody up there driving around in Longview.
Mm-hmm.
Or I can talk to somebody right next door. Or we can all talk to each other by taking turns.
So when I want to use the repeater, I'm going to transmit on the 146.72.
No, the published frequency of a repeater is the frequency that it transmits on. That is the published frequency. So for instance, if I go to
So we would transmit to your repeater on 146.12. Is that right?
Right. So if I go to a site called Repeater Book, Repeater Book is the online directory of repeaters. And let me go share Repeater Book. Okay, so here's Repeater Book. And let's go to, I'll log in. I can log in. Yes, I'm human. So let us first pick, somebody give me a state that you're in. Not Oregon.
Alaska.
Okay, let's go to Alaska. Okay, that was not it. Call sign, frequency, etc., location. Okay, so there we go. There's repeaters in Alaska. And where are you?
I'm in Talkeetna.
Talkeetna? Okay. And let's see what there is in Talkeetna. Let me plug in Talkeetna. And nothing comes up. Give me another town nearby.
Wasilla.
Ooh, I know there's going to be something in Wasilla. Okay, so there are different repeaters in Wasilla. They may have remote locations. Notice some say D-Star. Those are digital repeaters. Fusion is another form of digital communications. FM is simply FM. DMR is another form of digital communications. So these are all different, kind of like VHS and Beta. They're competing technologies. But let's just pick this one. Let's go to NL7S. Okay, so here's the published repeater information, 147.15. That is the repeater's published transmit frequency. Notice it has a plus offset, which means the uplink is 600 kilohertz above. There's also an uplink tone. That's a CTCSS tone in hertz, which basically says that if you do not have that tone programmed in, you don't have the right key and you won't access the repeater properly. So all the information for using it is there. It's an open system, which means anyone can use it. And it is on air, which means that at last check, it was functioning. And some of them will also give you coverage areas as well. I don't know if this one does, but some of them will actually give you what coverage area looks like.
And so when I connect to it, I'm connecting with the idea of just reaching out to see who else is on, or a specific person.
Yep. Or if you know somebody else is on at a certain time, or somebody's running a net, everybody shows up at the same time, and everyone knows to be there.
Okay. Thank you.
Mm-hmm.
Scott, is that repeater that you're on? This is John. I'm in Florida, so I'm not familiar with your area very well. But is it on Echolink as well? Do you have
okay, so Echolink we're going to get to. Echolink is we're going to get to digital communications in a minute.
Okay.
Okay, so that's repeater offset. Then there's something called a talk group on a digital repeater. Talk group, code plug. These are terms that specifically relate to digital communications. A talk group is a way for digital repeater users to communicate with each other while not interfering with the other group on a repeater, because they actually share the time. They split it in half, so it goes A, B, A, B, A, B, A, B. You program your radio with the group's ID or code. One interesting thing about a digital repeater is that because it uses digital audio, let's say a repeater is connected to the internet, which happens a lot. If the signal that's coming in is already digital, how hard is it to send that over the internet to somewhere else?
I don't know.
Very easy. Very easy. Right? It's just basically an Ethernet connection. If you have an internet connection and it's going over Ethernet, you just basically take those audio packets and you ship them off somewhere. So you could have two people in completely different cities that are using repeaters over RF, using digital communications, and the repeaters are linked together using the internet. You could also have somebody who has an internet hotspot in their house that's connected to the internet. It's receiving their digital handheld radio and essentially acting as a single user internet repeater. And those people can then talk to each other as if there's nothing in between them, where the backbone communications is being done over the internet. It's a lot of hybrid technology there. If you're on a group of stations on a digital voice system, you enter the group's ID code. DMR is digital mobile radio. It uses something called repeater color code. Essentially, it's blue or purple or whatever it happens to be, and that just identifies a particular repeater. If you're using D-Star, D-Star is interesting because it actually transmits your call sign in a digital format, and when you talk into the radio, it pops up on the other end. The other person who's listening will actually see your call sign pop up with your voice. Okay, so filtering, single sideband, 2,400 hertz. We also have something called a clarifier. So receiver incremental tuning is something that we do when we're doing single sideband. And the easiest way to demonstrate it is by going back to our handy dandy, always there. Nope. We're going to open this up. Okay. Oh, look at that. Perfect. Can everybody hear that?
Yeah.
Or in this case, not hear that, right? Okay, so does everybody agree that that voice does not sound perfect like that?
Mm-hmm.
Okay, why doesn't that voice sound perfect? Because, right,
On
well,
the
no.
bandwidth?
No, the bandwidth is fine. I'm not zeroed into the right frequency. Basically, the signal looks like this. But I have placed the center frequency, which is that little knob on the left, in the wrong place. I haven't done a very good job tuning it in. So receiver incremental tuning allows me to tune it in properly while not changing my transmitter frequency. Let's say that my transmitter and my receiver, for whatever reason, are slightly off frequency. This allows me to dial somebody in without moving and screwing it up on the other end. Okay, let's see. And that's known as RIT, or a clarifier. PTT is simply push to talk. A transceiver, okay, now we're into some definitions and we're starting to get into the quick part of the class, believe it or not. Hard to believe, but here we go. A transceiver combines a transmitter and a receiver. A transverter combines a transmitter or a receiver and a converter. Essentially, it uses something called a mixer, which is a frequency combining device, to take signals from one band and move them to another band. So a mixer is a device that looks like this. Let me draw it here. The schematic picture looks like this, where you have input 1, input 2, and output. But it works in the frequency domain. This is a non-linear device, and what it does is, let's say you have 10 megahertz coming in and you have, let's say, 18 megahertz over here. What this generates on the output is the sums and differences and multiples. So you'll get 10 and you'll get 18 and you'll get 20 and you'll get 36, and sums and differences. So you'll get 8 and you'll get 28 and 2 times 1. And I mean, basically what you end up with is you get the original frequencies, that's 10 and that's 18, and then you'll also get combinations. So you get 1 at 8, 1 at 20, 1 at 10, 1 at 28, 1 at 36. Okay, so you get this whole mess of stuff. Well, let's say that 28 is this one right here, and that's the one that you want. What would you build in order to capture that and block all the others? Everyone, it starts with the letter F.
Filter.
A filter. Yes, you would do a filter that looks like this to block out all the other ones that you don't want. And because this is a band, you want this to be a band. You want to pass it. So that's a band pass filter, or a BPF. You would build a band pass filter that is designed for 28 megahertz. What do you design this band pass filter out of?
Capacitor and inductor.
Capacitors and inductors. Ta-da! If you're designing a transverter, that's exactly what you do. That is the heart of a transverter. You have a mixer and a bandpass filter. That allows you to move one frequency to another. Where else do we use this device called a mixer? We use this in our receivers. We can down convert. We can do product detection. Has anyone ever heard of something called a superhet? Like a super heterodyne? Has anyone ever heard that term before?
Never heard that.
Never. Okay, a heterodyne is an oscillating frequency. A super heterodyne is when you take one frequency and combine it with a different frequency and make a higher frequency. And then you can do all your filtering at that higher frequency. If you see something called a superhet receiver, that's what it's doing.
So is it like multiplexing, or?
No.
Okay.
It's just moving it to a different frequency so that you can have like fixed filtering at that different frequency.
Okay.
And if you want to tune it, what you do is, because what is actually, let's say that it's the let's say instead of input 1, I replace this with this. What's coming in off of that antenna? What frequencies are coming in?
All of them.
All of them, right? If I combine that with just one, right? I will take that and I will have a whole mess of stuff. But let's say that I want to pick this one frequency at 17.2. And I combine that with 18. I'm going to erase this mess. All right. See, this is why we get to digress, but digression is good. Okay.
So by oversimplifying this, are you basically just rerouting that frequency, combining and rerouting it?
Putting it somewhere else. So, okay. So let's say that I want to see that 17.2 megahertz. What will be the sum of those two?
35.2.
35.2. Okay. So, if I build a filter now that is centered at 35.2 megahertz, what will be the output of all of this? 35.2 megahertz.
35.2 megahertz.
Which is a moved version of this 17.2 that I wanted to listen to. What if instead I wanted to listen, instead of 17.2, I wanted to listen to 17.1? Can I do anything with this filter? No, because I built it for 35.2. What would I do to change how I listen?
You would have to modify the filter.
Change input 2 so that you.
I would change input 2 to 18.1. I would tune this frequency. This has a name. This is called my local oscillator. I am tuning my local oscillator so that now the signal that's coming out is what I'm listening to at 17.1. And I've done that by changing this 18.0 to 18.1.
So was there significance in you? Was there significance with you combining those two frequencies to come up with that 35.2? Or was this just an arbitrary?
Yeah. No, I mean, I just picked the frequencies out of the blue. What if I wanted to listen to 17.0? What if I wanted to listen to 17.0? What would I have to tune?
18.1 down.
I would have to change it to what?
18.2.
So that my sum was still 35.2. So by changing the frequency on my local oscillator, I change what it is that I'm listening to.
I guess what I was asking though is, did it have to be the sum of those two, or could you pick any arbitrary frequency to place that on?
I could pick any place. I could pick anywhere, so long as there wasn't like any compelling reason not to.
Okay.
I mean, that's the great thing about RF design. You know, if you pick a frequency and you stick to it, you give yourself enough range. That's why we often shift up in frequency as opposed to down. That's why we do super heterodyne, because we have more space available, we have more flexibility. That's why we up convert. Sometimes we down convert. When we're actually doing product detection, we actually down convert so that it goes to 455 kilohertz, and then we do product detection and we pull the audio out of it.
And what is product detection again?
That is when you use something called a beat frequency oscillator and you recover audio.
Okay.
You demodulate it and recover the audio so you can listen to it. All this stuff is super cool. This is how this is how all your transceiver, all your radios work. This is about literally every radio you have, for the most part, unless it's a DSP radio. That's a little bit different. Okay, what device increases the transmitted output power? An RF power amplifier. Okay, this SSB CW FM switch on a VHF power amplifier. Okay, what is at the core of a thing called an amplifier? Let's see if everybody remembers from yesterday. What device is at the core of an amplifier?
Transistor?
A transistor. Okay. So if I have a transistor, do people remember what the transistor curve looks like? Input, output, it looks like this. So here's my input and my output, and I have my linear range. And here's my cutoff. And here's my saturation. Remember what these ranges are used for? Cutoff and saturation? 0 and 1. What do we use those for? What things use 0 and 1?
Digital.
Digital, yeah,
Digital.
okay. So the linear range is used for analog. If I want nice, clean replication of signals, I use analog. Well, what is single sideband? Single sideband is very analog. So when I want to do single sideband, this selects this range of operation for that transistor. How about when I want to do FM? FM looks like this. It just changes the frequency. Does it matter what the amplitude is? Nope. Morse code, it goes like this. Does it matter what the amplitude is? Anyone?
No.
No. So Morse code and FM can actually use the digital settings, which makes them more efficient when it comes to amplifying. Single sideband, not so much. Single sideband, you can't get away with it, or else you'll have a lot of distortion. And that's why you have that way of switching things. It changes the bias point. It changes the operating mode of the transistor. Okay, the ability to detect a signal is sensitivity. The ability to pick something out is called selectivity. If everybody is yelling at you at the same time and you can't pick anyone out, you don't have very good selectivity. An RF preamplifier, you would install this between the antenna and the receiver. Okay, so I know that we're maybe getting short on time, but I'm sorry, but I don't care because I feel like this is important. Does everybody remember what decibels are? From yesterday? Okay, so let's say I have a signal coming in that is minus 135 dBm. And I have a receiver that can copy successfully down to minus 140 dBm. It's a really, really good receiver. And I have an antenna that has 0 dB of gain, which means it's just unity. It doesn't do anything good. And I have 10 dB of loss in my cable. What will my signal strength be when it makes it down to the radio? It starts at minus 135 and drops down by 10. How much signal is there?
Minus 145.
Will I hear anything?
Yeah.
I will not.
No.
No, I will not. Okay, so what if I were to be a little bit creative and say I'm going to install a preamplifier and I'm going to put it way down here at my station. My preamplifier has a minimum signal that it can operate on of a minus 142 dBm. Will that help me?
No.
No, because how big is the signal when it gets there?
Negative 145.
That's right. Okay. So even if this thing has a gain of 10 dB, it doesn't do any good because it can't work on something that isn't there in the first place. So where is the proper place for me to put that?
By the antenna.
Put it up by the antenna because it has not had the loss from the cable yet. So this operates down to minus 142 dBm. How big is the signal here? Minus 135. It gets through a plus 10 decibel gain amplifier that puts it at minus 125. When it gets down past the minus 10, it's at minus 135. And guess what? Can I hear my signal now?
Yes.
This is how cable TV systems work. This is why you will install or the cable company will install a preamplifier all the way out at the cable end, the cable company's end, boosting the signal before it has to encounter its losses before it gets to your house, and why it doesn't do any good to put the amplifier at your home. So, what are the hazards of doing so? What does it take to run that amplifier? Remembering that it's now up on your tower.
Heat.
It requires
There's also
power. Yeah, it requires power, and what else?
Shelter from the elements.
Shelter from the elements. So whatever it is, it has to be waterproof. It has to be inside a waterproof box. So where's it going to find power? You have to run a separate power cable up to it. So here's your power cable. And it has to be inside a waterproof box. So that's why, it can be kind of expensive to do it. But if let's say you're doing moon bounce or something like that, where your signals are ridiculously weak, that's why people who do moon bounce often put mast-mounted preamplifiers up there on their towers. Does the power cable become an antenna? Yes. What would you put on that power cable to make sure it doesn't bring back any signal?
Ferrite.
A ferrite, exactly. You'd wrap it with a ferrite. See, you guys are picking this up so quick. Okay, a mixer converts a signal from one frequency to another. An oscillator, we talked about yesterday, makes a signal at a specific frequency. Modulation, we know all about. Symptoms, causes, cures of common transmitter and receiver problems. Radio frequency interference. Fundamental overload. Fundamental overload means that there's a nearby signal that is just so big, it has nothing to do with what you're doing, but it is just so big it's obliterating your receiver. This was, in my case growing up, this was the 10,000 watt AM station a mile from my house. I could hear it on every radio.
Listen, when I was at Clear Channel and I ran that 50,000 watt AM station, when you walked into that transmitter building, you could just feel yourself growing a tail.
Yeah.
I mean, like nothing, even like a digital camera wouldn't even work in there.
So let's do some quick math. Let's say you have a transmitter that is operating at 50 kW. And all the harmonics have to be at least minus 50 dB down. What is minus 50 dB? That's 1 divided by 1 with 5 zeros, or 0.00001. But it's times 50,000 watts. So we go 1, 2, 3, 4, 5. So you could still have, well, let's see, 1, 2, 3, 4, 5. Nope. 0.5 watts. Even on a completely unrelated frequency, you are still legally allowed to be putting out a half a watt. Well, has anyone ever listened to a half a watt handheld radio? Line of sight? That works pretty darn well, doesn't it? So let's say that I have a completely unrelated frequency. That 50,000 watt transmitter can still be putting out half a watt, which could be heard for a couple of miles. Fundamental overload. It just basically, there's enough signal there to just completely wipe things out no matter what. Spurious emissions are emissions on frequencies that are completely unrelated. A harmonic is an integer multiple of a frequency. So let's say you have a transmitter that's operating on 1 megahertz. You'll also be putting out harmonics on 2, 3, 4, 5, 6, 7, 8, 9. They will hopefully get smaller as you get further away from that fundamental. They'll get smaller in amplitude. Okay, if your neighbor says that you're interfering with their TV or radio, first thing you do, make sure that your signal is not interfering with your stuff. If you find that it's not interfering with your stuff, it probably has something to do with their stuff. So there's another thing that we need to talk about called Part 15. Does anyone know what Part 15 is? Okay, Part 15 is the FCC regulations that cover things like this, or your laptop computer, or your cell phone. Part 15 is unintentional radiators. The ham radio bands are covered by Part 97. Part 15 devices they are not allowed to interfere with any licensed devices, and they must accept all interference from any licensed device. So, ham radio is interfering with somebody's TV. Whose fault is it?
The operators.
Who? Which operator?
The ham operator.
It is not. Who's got the license?
Oh, I thought you were saying the other section 15.
No, 15 is everything else. Section 15 devices cannot interfere with a licensed service and must accept all interference from licensed services. So
if there's nothing wrong with your equipment and everything's properly installed, it's their problem.
It's their problem. Now, does that mean you shouldn't help? No. It just means it's their problem. Now, because you are experienced and knowledgeable about things like filtering and ferrites, you might be able to help out. And it's probably a good idea to be neighborly and do that. If you don't want to push it, you can say, okay, fine, I won't transmit between the hours of 5 and 6. So you can watch Jeopardy or something. But you do not have to do that. The licensed service is always right.
In the UK, part of your television bill is a licensing fee. So does that change that?
I don't know. Let's see. To resolve non-fiber optic cable TV, that is brought up because fiber optic is light and is unaffected by radio. However, non-fiber optic uses our old school cable signals. Those connectors have a way of getting loose. Since they get loose, if they get loose, they get leaky. Signal go in, signal go out through the leak. Tighten all the connectors first. An AM or FM radio may receive an amateur radio signal. I used to get through my parents' stereo. They could tell whenever I was on because they could hear me in the speakers, even if the stereo wasn't turned on. So basically, the receiver is unable to reject strong signals. I was transmitting with 75 watts in their house. Fundamental overload basically means that there's too much signal at a particular frequency. What would you use to block it?
Filter.
A filter. You can filter your signal, and you could filter their signal. Which of the following can reduce overload of a VHF transceiver by a nearby commercial FM station? A band reject filter will block their frequency. So, a band reject filter is a filter that's also known as a notch, which looks like a complete passband except for one frequency that is cut out. The reason that we do that, it can look like this. It allows
so that kind of filter would go on their coax connections, or
that would go in your cable. There would actually be like, here's your cable, here's the filter, and here's your receiver.
So you don't interfere with their station or with their frequency.
So you can prevent them from interfering with you. Because are they licensed also?
Yes.
Yeah, they are. So, then you're both licensed. So at that point, you would basically build a filter where this is the spot where their station is.
Scott, who wins in that case? Is it does the radio station, beat the ham operator, or like who wins?
I mean, at that point, you're both in the right. So, they're not doing anything wrong, and you're not doing anything wrong. So your job basically then is to just fix it. There's nothing that they can do on their side to prevent that.
Okay.
I mean, they have to transmit 50 kW. That's what their license says. So, that's what they're going to do. Okay, if you something in your neighbor's home is causing you interference, what do? You put in a filter, make sure your station's working right, tell them that they're interfering with you. All right, so this is a real world example. This is something called RFI, or radio frequency interference. It can be unintentional, like a power line, a transformer up on the power line is noisy. It could be a switching power supply on a new LED circuit that you just bought for lighting. It could be any number of different things. Okay, so I'm going to very briefly draw this picture, and this is a picture of, oh shoot. This is a picture of somebody's house with all the wiring inside it. Here we go. All right, so here's their house, and here's a chimney, and here's the power coming in, and it goes to this circuit, and to up here, and to here, and to here, and there's an attic lamp, and there's another circuit that goes here, and another one that goes here, and a whole bunch of outlets that go here, and something that goes there, and there's a washing machine, and okay, so what do you see inside that house? What are all those things?
Whole bunch of antennas.
Whole bunch of antennas, that's right. Okay. And at power, no big deal. But at RF, big deal. So let's say that one of these things is connected to something that generates RF, and it sends RF through all this wiring. What will it do?
Transmit a signal.
It'll transmit a signal. Yeah. One of my neighbors, about a half a mile away from me, had a cell phone. It had a cordless phone extender. They had this phone system that connected to the phone line that was coming into the house. And let me do this in a different color. Here's the phone line coming into their house, and it plugged into the wall. What it would do is it would connect any other box that was connected to anywhere in the wall, and this box up here was connected to a phone, so that people up in this room could use this phone line down here. And what did they use as the connector for it?
The house
wiring. Yeah, okay. Well, it turned out that this operated at 3.525 megahertz. And if we take a look at, I assume our frequency spectrum chart is still up there. Let's see. There we go. What do you notice on 80 meters? What is the frequency range at 80 meters? What do you see right in the middle of it?
3.525.
3.525. Yeah. Okay. This was an unlicensed device that was transmitting at about, I don't know, a tenth of a watt to get from that phone to the other phone. But it was using the entire house as wiring. And I am a half a mile away. These signals are then transmitted throughout the entire neighborhood. At which point I was listening on 3.525, and there's this FM modulated signal, super loud, and it sounded like somebody's phone call. And I asked my wife to listen to it, and I walked around the neighborhood, and I'm like, I think it's coming from here. I had a portable receiver, and I had her listen to it again. We looked up the address, and she said, "Oh, I know who that is." And so we called them. As I was listening, I said, "Yeah, that's it." And I went over there, and I told her that she was transmitting her telephone calls all around the neighborhood on the air. She was mortified that was happening. All her private phone calls were going out over the air like that. And she pulled the thing out of the wall and said, "Here, I never want to see this again." So she said, "Just do something with this." I'm like, "Okay, I can do that." I gave it to a friend of mine who works with radio frequency interference mitigation. He was very happy to have it as an example of what to not do. Okay, let's see. If you receive a report that your audio signal through an FM repeater is distorted, your batteries could be low, you could be off frequency, you could be in a bad spot. When they say a bad spot, this is a good opportunity, and I know that time is a little bit short, but we still have to do it. Okay, so we have let's say we have a spot, and here's signal A and signal B. On the 2-meter band, what is our approximate wavelength? Everyone? The first place you end up is probably going to be 2 meters. What's our approximate wavelength on 2 meters? I just gave you the answer.
2 meters.
2 meters, okay. So from crest to crest, this is going to be 2 meters. Okay, so let's say that there is another thing. Let's say a truck parked over here. And this same signal is being transmitted in a bunch of different directions, which it undoubtedly is, but it's going like this as well and bouncing off of this truck and ending up in the same place. And this right here, this signal has to travel 1 meter extra in order to get there. So I have this signal, and this other one, which traveled an extra meter, had to go like this. What happens when I add those two together?
0.
I get 0. They cancel each other out. This is called destructive interference. If they happen to add, that would be constructive interference. And what is the wavelength that I'm working with here? What's that wavelength? 2 meters, which is about 6 feet. So what would happen if I moved over, let's say, a foot? 2 feet. I could move from a spot where this is happening to a spot where they're adding together. When they say a bad spot, this right here would be a perfect example of a bad spot. If you have a digital signal when that's happening, your signal is going to be obliterated. You're going to have all kinds of data loss. The answer could be that you just have to move a foot or 2 feet to the side. And as soon as you have a handheld radio in your hand, you will experience this if you're listening to a repeater or somebody else on a repeater. There is a good spot. You move over a little bit and you're in a bad spot. You try to pick the good spot. Hope that it's not a truck that's moving, in which case your signal will be bouncing back and forth. There's also something called picket fencing, which is when you move rapidly when you're driving a car from areas of constructive to destructive interference. And this can happen 5 times a second. Blah, 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 if you're going fast enough.
So I see that with my mesh-tastic stuff a lot. Even though they're small, little, tiny radios, but I see take 3 steps in the house the other direction, and all of a sudden stuff starts flowing.
Those are at 900 megahertz, if I'm not mistaken. You look at the wavelength of 900 megahertz, it's about 33 centimeters, which is about 14 inches, 13 inches. So you move a foot one way or the other, and it changes things completely, doesn't it?
It's really mind-blowing how these little things can push a signal so far on such little battery. But everything you've explained today, yesterday kind of makes it all make sense. But it's definitely incredible.
Yep.
Is mesh-tastic the idea of people being able to talk to each other? And I guess it depends on the phone. I thought it was through the phone, but evidently
it's RF.
Ben, it's not. So
they're basically little radio devices that you can connect to with Bluetooth, but they're long range, low power, little radio devices.
LoRaWAN.
Yeah.
So to be part of the mesh network, you buy one of those little devices, specific devices.
Yep, that's all it's to it. And you can talk to it with your phone over Bluetooth, but you don't necessarily need your phone. It's just your phone's how you interface with the little radio.
And each one of them has an amateur mode because they're right next to a ham band that ups the power and allows you to switch to. It takes away the encryption because you can't encrypt, but it also ups the power.
Yeah.
So. Okay. Using basic test instruments and soldering. Does anybody here have a Harbor Freight nearby?
Yes.
Does anyone here have a $3 Harbor Freight multimeter?
Yeah.
Yeah, I do too. I think I got mine for free actually.
Yeah, coupon.
Yeah. Okay, so multimeter is a device that measures volts, ohms, and amps along with a lot of other things. Multimeters are a great, wonderful device because they have the ability to measure lots of different things and they don't have to cost a lot. A Harbor Freight multimeter, and I bring up Harbor Freight not because it's bad, but because, again, like a Baofeng radio, it has its place. I have a Harbor Freight multimeter in my junk toolbox. If it gets broken, I'm okay with that. For work, I also have a Fluke 87 Model 5, which costs $500. The reason I have that is because sometimes I will measure very high voltages. I would not dare measure 500 or 600 volts with my Harbor Freight meter. I would very easily do it with my Fluke. I know that it's been designed and tested for that. The other thing is that a Harbor Freight multimeter will not give you a true RMS reading. This is something that we're going to cover in the general class, so I'm not going to do it right now. But RMS is root mean square, and it basically is the equivalent voltage that an AC signal would have in order to make the same amount of power as a signal that was DC. So 120 volts AC RMS is the same as 120 volts DC as far as power goes. A true RMS reading voltmeter knows the difference between a sine wave and a square wave. A non-true true RMS reading meter does not know the difference, and it will give you a wrong reading. My Fluke will give me the right reading. The Harbor Freight meter will not give you the right reading. Okay, a voltmeter, volts are potential. So electric potential, electromotive force, that's volts. You use a voltmeter. To measure applied voltage, you put the voltmeter in parallel with the device. When using a multimeter, if you try to measure voltage when using the resistance setting, you can blow up your meter. If you put your voltmeter in series with your circuit, you can blow up your meter very easily. When measuring high voltages with a meter, make sure the meter and leads are rated for it. How do you measure resistance? You do something in parallel. You disconnect the device from the circuit. If you have a capacitor, we covered this yesterday. If you're measuring the resistance of a capacitor, it will start at zero resistance and go up to infinity because it's trying to measure the it's trying to measure the current flow. An ohm meter actually has a battery in it, and what it does is it puts a voltage into a circuit and measures the current. Because it has voltage and current, it uses Ohm's law to tell you what the resistance is. An ammeter goes in series with the thing that you're measuring. It measures current in amps. You never use acid core solder, and a cold solder joint is something that you never want to see. If you're doing soldering, you want a solder joint to be shiny and look like a little volcano where you don't have any hole in the center, so you don't really want to see that crater. A cold solder joint is a mechanical joint with a bad electrical joint, and it will undoubtedly fail at the worst possible time. Okay, operating. First thing you're going to do is probably get a handheld radio. So let's talk about FM. A station that retransmits a signal of another station is known as a repeater. A repeater is an automatic station that is automatically retransmitting things. Repeaters, auxiliary stations, and space stations are capable of automatically retransmitting signals. A space station is anything 30 miles or 50 kilometers above the surface of the Earth. So that is the definition of the beginning of space. An auxiliary station is basically like a store and forward or a one-way transmitting station that could be taking your audio and sending it somewhere else to be retransmitted. A linked repeater network, we have one in Oregon. The Peak Radio Association, I believe, has 50 repeaters tied together. They basically share the audio so that if one person accesses one repeater, they are retransmitted on all the repeaters. All the sound coming from all the repeaters is combined into one signal, which is then sent out over everything. 2 meter offset is plus or minus 600 kilohertz. The 70 centimeter offset is plus or minus 5 megahertz. CTCSS is that key that has to be there on certain repeaters to access the signal, for the repeater to access the controller. It's a continuous tone carrier squelch system. It's a continuous tone, quite literally. If you have the wrong tone and it's listening for one, or the wrong digital coded squelch, or the wrong offset, nobody will hear you, and you'll just basically be yelling into the microphone, and no one will hear you, and you'll get really frustrated. Reverse, basically, you normally would listen on the repeater's frequency, and you would transmit on the repeater's input. You can hit the reverse button on a handheld radio, and what that will do is it will temporarily swap those frequencies so you can listen on the input. Why would you do that? If you want to listen to other people and how their signal sounds, maybe you can say, oh, I heard you on the input and your signal is really loud, but you probably don't have the tone set correctly. If the tone is not set correctly, the repeater won't hear you. If you're transmitting, if you're distorted on voice peaks, you're probably talking too loud. The easiest way to deal with that is to back away from the microphone. More common than that, however, is the fact that people are not loud enough, and they sound kind of like this if they're really nervous and don't have a lot of experience, and you can barely hear what they're saying. What do we tell them to do?
Speak up.
Speak up. Be loud. Outside voice. Get close to the microphone. Okay, if you know the other station call sign, KD7 EWK N7JI. KL4IZ, KL4IZ, N7JI.
This is KL4IZ.
There you go. Okay, so you send the other station's call and then give your own. And then if you want to say that you're monitoring, you just say this is N7JI listening, N7JI monitoring. If you're transmitting and receiving on the same frequency, you're doing something called simplex. What is the point of simplex? Simplex is, let's say that you and your neighbor have a morning meeting every day. There's no point tying up a repeater, and you live way out in the middle of nowhere, and you don't expect anybody else to be hearing you. You don't want to tie up the resource that's a repeater, so you just get on a simplex frequency and use it. You and somebody else are within a quarter mile of each other on the highway, and you're driving up and down the road. You just want to have communications. You can do that. National simplex calling frequency is 146.52 megahertz. Everybody who has a handheld or mobile radio, if they program it, they typically will always program this frequency in. Anywhere you're going, pretty much in the United States and Canada, somebody will be listening to that frequency. CQ, okay, now we're talking about high frequency operation. High frequency is 3 to 30 megahertz. CQ means I'm looking for somebody to talk to. Before calling CQ, you listen for, you check your frequency, make sure you have privileges there. Then you listen and listen and listen and ask if the frequency is being used. Because it's entirely possible that high frequency signals and propagation, you won't necessarily hear both ends of a conversation. In fact, you could be 5 miles from somebody else and not hear them. The signal is bouncing right over your head. You could hear a station 1,000 miles away, but not hear the guy who's 5 miles from you.
So then how would you know if you call and say, is anybody using this? You wouldn't be able to hear them answer.
That's right. The other station that is listening to that first station would hear you and say, yeah, the frequency is in use. Even though you can't hear anyone, the frequency is still in use because the other station is in the process of using it. Okay, how do you respond to a CQ? You give the other station's call sign and then your own. It's always the other station and then your own. And this is not a hard and fast rule, but you don't do it. If you don't want to sound like a newbie, you should never do, if you don't want to sound like a newbie, never do this. You get on a repeater and call CQ. Do not do that. It's not wrong, but then everybody will know that you are inexperienced. Because the whole idea of a repeater is that if you call CQ, it means you don't have any idea who's listening. If you're on a repeater frequency, you have some idea that there's a station there. The station is the repeater. So on a repeater, you just say your call sign and listening, or my call sign and monitoring. So N7JI listening. It just means if there's anyone here on this repeater to talk to, I'm here.
Okay.
So I just saved you a whole bunch of embarrassment. So you can sound like a pro right from the beginning. It's just one of those things you don't do. Okay, when making an on-the-air test transmission, you have to identify it. That's going to come up over and over and over from now on. There are Q signals that we use. You will hear QSB, that means I have fading. QSY means I'm changing frequency. QRM means I have interference. Oh, QSL. QSL means I confirm or correct. Sometimes you'll say QRZ. Remember the name of that website, QRZ? It means who's calling. It's a way to look somebody up. So you ask QRZ, that means who's calling me. Interesting thing about Q signals, the reason that Q signals are used is because in telegraphy, if you think about it, there aren't that many words that begin with Q. So Q signals were created as a shorthand method for asking and answering questions. So QTH question mark, that means where do you live? QSY question mark, that means do you want to change frequencies? An answer of QSY period means yes, I want to change frequencies. So every one of these is a question as well as an answer. A band plan is, okay, so this is a good time to talk about this. Okay, so everybody see this band plan right here? For the most part, if you look at the FCC rules, you will see no mention of this stuff as far as like where you're allowed to do phone and where you're allowed to do Morse code and who's allowed to use what frequencies and what kind of use they're used for and where digital is used for and where image is used for. And up here, which ones are simplex and which ones are duplex repeaters and which ones are for TV and stuff like that. The FCC really, for the most part, does not want anything to do with us. They don't want anything to do with us because we don't pay them any money. So there's no money for, there's no money for enforcement of anything. There's no money for checking things out to see if somebody's interfering with somebody else unless the air traffic control system is involved. So basically the FCC, the basic rule of thumb is, let's say we're looking at the 2 meter band, right? What are the goalposts, the left and right goalposts on the 2 meter band? What's the left goalpost?
144.
And what's the right goalpost?
148.
The rule is your entire signal must fall between those goalposts. You are not allowed to go outside. Unless there's like specific rules that say you can only use this mode and it's codified in law, the rule basically is your entire signal must fall between that side and that side. That's really, for the most part, all they care about. Because outside of this band, outside of these goalposts, whose band is it? It's not ours anymore. It belongs to somebody else, right? If we go outside the band, we're encroaching on somebody else's space. So, in order to keep the peace, however, let's say we have this 2 meter band. Notice that it's separated out into weak signal and simplex and images and stuff like that. These are band plans that are set up to essentially make sure that people don't interfere with each other's ability to use the band in practical ways. And even within that, within each state, there are differences. So let's look at, for instance, the ORRC, which is the Oregon Region Relay Council, ORRC. Notice there's this band plan for 2 meters. And it is even more specific than the other band plan that we looked at. It has specifically repeater inputs, repeater outputs, OSCAR, which is satellite, APRS is packet, APRS digital, EME, which is Morse code, weak signal. EME is specifically moon bounce. EME, weak signal single sideband for people who want to do moon bounce, propagation beacons, etc., etc. These are selected by a group of hams that have been elected to basically set this up so that everyone in Oregon can understand how to keep the peace. So every region has their own group of volunteers who are elected by people who are allowed to run repeaters, for instance, because they have the right license class and they have equipment, to basically go ahead and create a way to keep the peace. That's a band plan. So it's not typically codified in law. It's written as an agreement so that people don't interfere with each other. Okay, there's a band plan. Let's see. If we have 2 people operating on the same frequency, nobody owns a frequency. It doesn't even matter if you've been there for the last 20 minutes. Band conditions change, propagation changes. All of a sudden, the band that you were on is no longer working because somebody else is super loud on it. They did not just pop up out of nowhere. They didn't just come out of nothing. They are probably there because the conditions changed, or they just didn't hear you because conditions changed. So we're all in this together. Just work on it, figure it out, somebody move. Okay, public service and MCOM. ARES is the Amateur Radio Emergency Service, very similar to RACES, which is the Radio Amateur Civil Emergency Service. The word civil means that the government, local government agencies are involved. ARES is a volunteer thing. RACES is also a volunteer thing, but RACES is actually talked about in Part 97 of the FCC rules. ARES is not. But they are both groups of people, equipment, and frequencies that are used for providing emergency communications. RACES specifically is for civil defense. But they're very similar. You can be a member of both. If I'm running a net is short for network. A net is an on-air thing that is called to order by somebody who is the net control. The net control is basically the traffic cop. A net exists for people to get on a common frequency and pass information known as traffic from person to person. So the person who is the net control station is the traffic cop for everybody else who is on the frequency. So the general rule of thumb is don't speak unless spoken to, unless there's an emergency. Sometimes they'll take roll call. Sometimes they'll just say, does anyone else have any information? Is there any traffic? Please pass your traffic. Traffic is formal messages that go across a network. So, traffic handling, there are actually, when you get on the air and you get into radio, there are traffic handling nets. One of the things that we are supposed to do is be able to help out in times of emergencies. If you are intending to help out in times of emergency, and you are not good at taking messages exactly as you heard them and writing them down and passing them off to somebody else, and you make typos, that would not be accurate. For instance, let's say that you have somebody whose name is Patrick Johnson, and you wrote it as Patrick Johnston, and the message is Patrick Johnston is in the hospital, and you send the message along, that would be a totally different person, wouldn't it? So Accurate message passing is very important. If we have for instance, a message to be handed from person to person, and I wanted to make sure that Tomislav was spelled correctly, I would spell it Tango Oscar Mike India Sierra Lima Alpha Victor. If there's any question that there might be a spelling mistake or something, I want to send it again. If I am not sure that the message was received correctly, I want to ask for it again. There's something called a check. A check is a number of words in a message. If the check does not match what I wrote down, that means something got lost or somebody made a mistake. Please repeat it so I can get it right. The preamble is essentially the address on the outside of your letter, on the outside of your envelope. It tells everybody how to get the message to the intended recipient. When do FCC rules not apply? The answer is never.
Never.
Never. The only time that you can basically go outside those rules is in these cases. You will see these on a half dozen questions in here. Immediate safety of human life or protection of property. If those words show up, that's the right answer. Basically, if it's safety of human life or protection of property, immediate safety of human life or protection of property, then it's okay to violate the rules. Mostly. What that really means is it's okay to violate the rules if there's no other way to do it. If you have a functioning cell phone and you don't have a ham license, but there's a ham radio right next to you and you could use the cell phone, you're going to get dinged. If you have a functioning ham radio and there's somebody on the other end and your radio can tune in to the fire department and you can send a signal out on the fire department frequencies and send it to them, but you could have sent it over the ham frequencies, you will get dinged. That actually happened a few years ago. A guy got a $35,000 fine for doing that. Basically, if there's no other way, you can do anything you need to. You have to just be able to verify, be able to justify. Amateur satellites. Okay, anything up in space means 50 kilometers up or higher, roughly 30 miles. Who can contact the International Space Station on VHF? Well, you have to know that VHF covers all of these bands up here, 6 meters, 2 meters, 1.25 meters. The uplink frequency is on the 2-meter band for the International Space Station, which means if you have a technician class or higher, you can talk to the ISS. A satellite operating in UV is UHF up and VHF down, 70 centimeters. We look up here. 70 centimeters is above 300 megahertz, so it's in UHF. So 70 centimeters up and 2 meters down would be UV. For satellites, they operate in single sideband and FM and CW, and they send data. If you transmit with too much power on the uplink, you can obliterate the receiver to the point where nobody else can use the satellite. So there's a beacon that comes down from the satellite, beep, 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 indicating what the satellite is, what its status and health is, how much power it's running, what mode it's in. If you are operating on a satellite, you should take the time to be able to take a second radio and listen to your own signal. There are a few reasons for doing that. One is to make sure that you're not stronger than the beacon signal, because if you are, then you're going to be obliterating the receiver up there in space. Another reason to be doing that is because satellites, as they are directly overhead, they're not really moving side to side at all. But when a satellite is down on the far horizon, either far horizon, it's going to be moving at about 17,000 miles an hour. That is actually enough for Doppler shift to take effect, which will take your frequency and move it. It will take the satellite's frequency and move it. It's actually moving fast enough that even given the speed of light, it will actually shift your radio frequency by 10 kilohertz on the 70 centimeter band. In which case, you have to be able to tune in your radio to make sure that you're on the right frequency and that you're listening to the right frequency. A LEO satellite is low Earth orbit. Telemetry information is health and status of a satellite. Anybody can receive telemetry information. Anybody can listen on the radio. A satellite tracking software program typically is going to give you, and actually these are very common on the phone. They're great little apps. They will tell you where a satellite is, what direction it's going, when it's going to be overhead, how high above the horizon it's going to be, whether or not the Doppler shift is going to be a significant impact. The inputs into a satellite tracking program are the Keplerian elements. Johannes Kepler came up with a series of elements that defines what an orbit looks like. You punch in the Keplerian elements, and the program will figure out when the satellite is going to make a pass near you. We covered Doppler shift. Doppler shift is changing frequency because of the velocity of one thing with relation to another. Spin fading. Satellites typically will be rotating to keep themselves stable in space. In doing so, an antenna that you're communicating with up there might actually be eclipsed by going behind the satellite, in which case it will disappear and your signal will fade. All right, everybody good for a 5-minute break?
Yes.
Oh, yeah.
Okay. Does anyone have any questions? I'm sure you've got some. Anyone? Well, think about it for the next 3 minutes, then ask your question.
I have a quick question regarding the satellite communication. What's the point of having 2 different bands for uplink and downlink?
Oh, that is an excellent question. Okay. That is an excellent question. So, so here's our satellite that I'm going to draw. And everybody can take a break. This will still be up by the time you get back. Okay, so here's our satellite. This actually applies to repeaters as well. So we're going to do a terrestrial system. So here's our TX and here's our RX. Okay, so on our, and we have our controller in the middle that connects the two and pumps information from one to the other. Okay, so our transmitting signal is going to typically be, let's say, 100 watts.
Scott, you're not sharing.
I am. Make sure that you have make sure you have it selected up top on your top of your screen. On the top, there should be a tab that says meeting and another one that says my screen. Okay, so let's say that you have this transmitter and receiver, and these are in close proximity frequency-wise to each other. Let's say this is 146.72 and this is 146.12. Those are actually pretty close to each other, right? Spectral purity of a signal says that it has to be like this, but you're going to have, diminishing signals at a certain number of decibels down. How sensitive is a receiver?
Oh, you'll desense.
And it might be that it'll work down to this many watts. Right?
Wow.
There's probably going to be, okay, so you have to do something to protect it.
Got it.
So what do you do to protect it?
You could put like a duplexer in place.
You put a duplexer. Hey, how'd you know? Okay, well, now the problem is, let's take a look at a duplexer. 2-meter duplexer. Okay, so let's bring up a picture of a 2-meter duplexer. All right, this is so you can use the same antenna or two very close spaced antennas right next to each other. That is a 2-meter duplexer. Those cans and those tuning slugs on top of the cans and all those cables are about 2.5 feet tall. If you're on a satellite, that's pretty heavy, isn't it?
Oh, yeah.
Right? That is what you'll find on a 2-meter repeater. And those are very, very, very tightly tuned band pass, band reject filters. And sometimes 4 cans is not enough. Sometimes you need more like 6. The one I had back in school, on the repeater system that we had, it was more of a 6 can system. I'm seeing if this is 4. Okay, that's 6 cavity. Yeah, so we had a 6 cavity a 6 cavity duplexer. So let me unshare this. Shoot. There we go. Okay, so there's our 6 cavity duplexer. Here's a 4 cavity duplexer, and they're 2.5 feet tall, and they weigh, I don't know, 50 pounds. If you're on a satellite, that's not really practical. If you have a repeater, it's a little more practical. But what happens if it gets a little bit warm outside, for instance, and these things like expand due to heat?
They could like untune.
And they can untune, yeah. So typically you'll get like 110 dB of isolation between these things. Notice this one says 90 dB of isolation. So that is 10 to the minus ninth, or 1/1000th of the transmitted power getting through to the receiver. So you add more cans, that increases your isolation even further. That's what it can take for a repeater system to work. So.
Makes sense. Thank you.
Yeah. Yeah, I didn't cover duplexers. Duplexers they're really expensive, and what do you think it takes to tune them?
Spectrum analyzer.
And typically
Expensive.
a really expensive spectrum analyzer. Signal injection, or I mean, I guess you could, in theory, use a nano VNA, but typically you're going to want it to be more accurate than that. So yeah, you're basically going to want to do some heavy-duty signal analysis stuff as far as signal going in, signal going out. And the tuning on those is very, very, very touchy. Each one of them is basically a hollow cavity filter. And that screw on top is the tuning device. So, all right, shall we continue? Let us continue. Okay, operating activities. One of my favorite things to do is called contesting. Contesting is radio sport. Get on the air, make as many contacts as you can in a specified time in a particular method. There could be like a Morse code contest, or a voice contest, or a RIDI contest, or an FT8 contest, or it could be specifically make as many contacts with Croatian stations in a 24-hour period as you possibly can, and then send in your logs, and we'll send out certificates to the winners. When contacting another station in a contest, you should really know what the exchange is. Typically signal report, 59, and your state, or 59 and whatever the exchange is. 5903, 59224. A grid locator. Okay, this is something that the entire world is broken up into grid squares, which are actually grid rectangles, so it's not completely accurate. But a grid locator is a letter number designator. And the entire world is broken up into 2 degree latitude, or 2 degree longitude by 1 degree latitude blocks. And everybody has a grid locator assigned with where they live. The nice thing about the grid locator is that it allows you to more accurately identify where somebody is rather than just in a particular state. So, for instance, my grid locator, let me see, grid square map. There we go, grid square map. Can everybody see that? Can everyone see?
Yep.
Okay, so here's our grid square locator just for the United States. So let's say that let's say somebody says they're in Montana. Well, from Oregon, Montana actually covers a whole bunch of beam headings because it's really big. California is enormous. From Nevada to California, you could be pointed northwest or you could be pointed southeast, depending on where you're looking. So your grid locator tells you exactly where to go. It's just basically a more granular way of looking at the map. Okay. So that's a grid map. Direction finding. This is where we use directional antennas to go find a hidden transmitter somewhere that has been, it's been hidden. A directional antenna is great for that because it allows you to get a beam heading. Now, if you have a beam heading, you know which way to walk. Okay, now we're into communications between radio and the internet. If there's an internet, there's going to be radio interface with the internet. IRLP is the Internet Radio Linking Project. VoIP is VoIP, or Voice over Internet Protocol. VoIP is the way to transfer digital voices or digitally converted voice over the internet. Echolink is a system that uses your cell phone or a computer application to connect you using an internet connection to a repeater or another operator somewhere over the internet. A lot of repeaters have an Echolink connection. And what's nice about that is when I'm traveling, for instance, if I want to, let's say I'm all the way across the country, we have a 2-meter repeater. Obviously, 2 meters is not going to cover 2,000 miles or 6,000 miles, but I can get on the internet if I have an internet connection on my phone, dial up our local repeater system, and pop up on RF and have a conversation with somebody and participate in a net or talk to a friend who happens to be driving around in a car somewhere on the radio. And that's called Echolink. In order to sign up for Echolink, because you're going to be on the air, you need to register your call sign and you have to send in a copy of your license. In order to open up an IRLP access on a repeater, you use DTMF. Every handheld radio has a keypad these days. Every mobile radio has a keypad these days. When you transmit and you push those numbers, they don't just dial in a frequency anymore, they do touch tones. Those touch tones are known as dual tone multi-frequency, or DTMF. The right code will allow you to open up access to the proper thing that you're looking for. A gateway is a station that connects other ham stations to the internet, very often using, again, DTMF tones. Okay, rules and regs. Rules and regs. The FCC is the boss with regard to your ham license. So, Federal Communications Commission. We looked at one of the first things we did, Part 97. Why do we exist? It's important to remember those things. Those are the reasons that we are allowed to use the frequencies that we are allowed to use for essentially no cost. You know, we have value. We have not monetary value to other people. We have an intrinsic value in that we make radio more current, we provide emergency communications, and we know what we're doing. The goal is that we are not a group of people that is going to take our radios and we're just going to do selfish stuff with it, or we're going to take our radios and throw it in a drawer, and when the time comes, we're going to be able to help. Our job is to get on the air and stay practiced to the point where if something goes wrong, we actually know what we're supposed to do to help out. A beacon is a one-way transmitting device used for observing propagation. A space station is anything more than how many kilometers up? I've said it how many times?
50.
50 kilometers is a space station. Okay, very good. You are never allowed to willfully interfere with somebody, even if they are really annoying you. You are never allowed to do willful interference. Okay, which of the following entities recommends transmit and receive channels and other parameters for auxiliary and repeater stations? This in Oregon is the ORRC, that is known as the Frequency Coordinator. Every state has a volunteer frequency coordinator. It is a largely thankless job, but somebody has to do it. The frequency coordinator is selected by local hams who are eligible to be repeater or auxiliary stations. Okay, so does everybody remember this band plan here? Does everybody have a copy of this now?
Yes.
Everyone? Okay. If you don't have a copy of it, ask for it and we'll stick it up. Somebody will stick it into the chat. This is exceedingly important because this is basically your park map. If you think of our frequencies as a park, this is a map to the park. This is the map of what you can do where and an idea of how much power you can run where. Okay. Okay, let me close that. Open up the right thing. Okay, so frequency in the 6-meter band. If you look at the chart, the 6-meter band covers 50 to 54 megahertz. Well, 52.525 falls right in the middle of it. That's actually the 6-meter FM calling frequency. 146.52 falls in the 2-meter band. This stuff is just stuff that you have to memorize. You have phone privileges as a technician on the 10-meter band only. It is designed as a way of you getting a taste to see what high-frequency operation looks like, with the hope that you will take the incentive and upgrade to general. You are allowed to operate on phone from 28.3 to 28.5. Every frequency band, 50 megahertz and up, has at least some area for single sideband and Morse code. Morse code only is allowed on these bands. We have this weird thing between 219 and 220 on the 1.25 meter band, also known as the 220 band, where we have fixed digital message forwarding systems only. Personally, I don't know a single person who has ever done that, but that's what we're allowed to do there. Okay, we talked about this one here a little while ago. Let's see if anyone remembers the answer. Why should you not set your transmit frequency to be exactly at the edge of an amateur band?
Because you can go over.
Okay, and what do the FCC rules say with regard to our allocations?
You can't go outside the limits.
You can't go outside the limits. You have to stay inside the goalposts. All right? So if you are right on the edge, what does every modulation technique create? Starts with the word side.
Sidebands. Yeah.
Sidebands, that's right. So if you put your radio right at the edge, where will one of your sidebands go?
The upper
outside the goalpost.
It's going to go outside. Right. If your radio is not quite accurate, Louita, I'm looking at you with the Kenwood 520S. They've been known to drift over time. Let's say your radio drifts by 2 kilohertz when it warms up. What you think is going to put you safely inside the band no longer is. So why should you not tune right to the edge? Because your radio might drift as it warms up. Typically not going to happen with some of the newer stuff, but on some of the older stuff, it will. Okay, bands where we are secondary. Primary means we're the primary users. Secondary means we are the secondary users. Somebody else was there first. If we hear someone else using it, we have to not interfere with them if we're the secondary users. How much power are you allowed to operate with? Anywhere above 30 megahertz, unless there's like specific restrictions, like you're within like 50 miles or 100 miles of the Canadian border, or there's some rules like that. The FCC rules allow you to transmit with 1,500 watts. And that right there alone is a really good reason for this licensing process to exist. We are legally allowed, even with a technician class license. Let's say that you're 6 years old and you passed your technician class license. How much power are you allowed to operate with?
1,500 watts.
1,500 watts, that's right. You can be 6 years old and legally running a 1,500 watt transmitter. So,
oh, wow.
Yep, there's no age limit. What is the maximum peak envelope power on the HF band segments as a technician? 200 watts.
I have a question, Scott.
Yep.
So, there's a lot to know to all this. So if someone really doesn't know what the heck they're doing and they get a radio and they start transmitting, who can someone just come and shut them down, or can they send a signal to shut their radio off? How do you prevent that?
I mean, did they have a license or not?
Oh, I don't know. I'm just thinking people do a lot of crazy stuff nowadays.
Well, okay. If somebody gets on the air and they don't have a license and you do have a license, you're going to know. You're going to know that they don't have a license, right? There's no license there. They don't know what they're doing. Are you allowed to talk to them and tell them?
Doesn't really help usually. It's better just to ignore.
Yeah, Gary, what do you think? Was it Gary? Gary, did you ask the question?
Yeah,
okay,
sorry.
so if I have a license and there's somebody on who obviously doesn't have a license, am I allowed to get on and chase them off? Am I allowed to legally? Am I allowed to legally talk to somebody without a license?
I don't think so. No.
No. Basically, you ignore, and if it really gets bad, you make recordings and you send it to a volunteer frequency monitor. And if it gets really bad, it'll get sent to the FCC, and the FCC will do direction finding and go after them. I mean, it's got to be pretty egregious.
That's a lot of wattage. 15. I mean, that's a lot of power.
Sure is.
You know, we've talked about today with just 2 watts what you can do and how far you can talk and travel. But
sure is.
It's a lot.
Yep. Yep. This is not even a technician license is a serious radio license. That's why there's an exam.
How bad do they frown upon crossing frequencies? Simply because I recently I transmitted on my GMSR RS, and I was speaking on a 2-meter band without realizing it. And I had a licensed operator on the other side that was telling me, "Hey, you're on a 2-meter band. I wouldn't broadcast here very often." And I told him, I said, "Well, it's just by mistake because it's what I programmed in my radio, and I was just testing for radio check." So he just told me, "Don't do that very often."
Don't do that. Yeah, don't do that. Easiest way to do that is to disable the transmitter.
I'm going to take that band out of my radio anyway.
Yeah.
Right, until I'm licensed for it.
Yeah. And, that's the thing. If you do something by accident and it doesn't cause any harm, probably nothing's going to happen. I mean, nothing's going to happen. Hopefully somebody will tell you. Hopefully you realize it. If you are a repeat offender, right, they'll find you and they'll come after you. There are people. People who've had their houses, who have had liens against their house. You do something often enough.
It seems to me like playground rules apply over much of this, like respect boundaries, like know when to use your outside voice. Someone will report you to the hall monitor if you're out of line.
Amateur radio, because the FCC really doesn't want to spend any money and resources on us. We are largely self-policing and have been for a very long time. So we're good at policing the playground. I don't want to ruin it for everyone. And if you listen to the airwaves, there are cesspools of bad behavior. I mean, there's
Oh, yeah.
one on 7.2 megahertz, and there's another. There used to be a one on 14.313, and there's one on 3.8 something with a bunch of people who think that the First Amendment trumps their, their need to agree to the FCC rules. And the FCC will quickly tell them after a while, hey, that's you may think that, but that's not how it works. So, all right, licenses available from the FCC: technician, general, amateur, extra. No, I don't know why it's called that. Normal term for a license is 10 years. After passing an exam, you are allowed to get on the air as soon as your license appears in the FCC license database. That is going to show up in a half dozen questions. FCC license database.
Mm-hmm.
You can have one license, period. That's it. You're allowed to operate when it appears in the FCC database. There it is again. You're allowed to pick a vanity call sign. Any licensed ham can apply for a vanity call sign, so long as it is within your operator class. As a technician or a general, the way call signs are set up, everyone has either one or two letters before the number. That's the prefix, and then the suffix is 1, 2, or 3 letters after the number. So W1XX, that is called a 1x2. That is an extra class call. KA1X, that's a 2x1, also an extra class call. KL7IZ is a 2x2, or sorry, KL4IZ is a 2x2. With the exception of Alaska and Hawaii, that is an advanced class or extra class call.
Oh, wow.
Yep. A 2x3 or a 1x3, any technician or general can apply for those. So KF1XXX is a valid technician class call sign. And when you get your license, your technician class license will be a sequential call of that format. Your license is good for 2 years in the grace period. If that expires, during that time, are you allowed to operate with it? Come on, while it's in the grace period. Nope, you got to wait until it shows up as active in the database.
Yes.
Okay, a club, the definition of a club is that it has to have 4 members. Any 4 hams can create a club and can request a call sign. If the FCC can't reach you by email, they can pull your license. That means make sure that your email doesn't bounce. You can transmit from anywhere in the United States or from any boat registered in the United States that's in international waters. You are not allowed to use obscene or prohibited language, indecent or obscene. Again, there's that First Amendment thing. So the First Amendment might allow you to do certain things on the air. Your FCC rules do not permit it, and they go beyond the First Amendment. That's one of the rules regarding transmitting. Manned spacecraft communications. We are not allowed to make money on the air. We are not allowed to broadcast music. In fact, I heard somebody mention broadcast. We do not ever broadcast. Do not use that word to describe what we do, ever. Because somebody will say, oh, there's a newbie, right? We never broadcast. We transmit. The reason being, broadcasting is a communications that is meant for the general public. We never do anything that is meant for the general public. Our transmissions are intended for the amateur community. So never use the word broadcast. Take it out of your lexicon because you're not going to use it because we don't do it. We are not allowed to transmit music unless we're trying to wake up astronauts on a space station. That came from the shuttle days. They used to retransmit shuttle broadcasts. They used to rebroadcast shuttle stuff, and it went out over the airwaves with music. So that created a loophole. We are never allowed to encode messages to obscure their meaning. That doesn't just mean encryption. So the only time you're allowed to is if you're, let's say you have a satellite. Yes, you are allowed to run, you are allowed to get your own satellite up into space. Yes, you're allowed to run remote control craft. You can use 6-meter band to do remote control craft of airplanes and boats and things like that. You are allowed to encrypt those signals so that your satellite doesn't get crashed or that your remote control craft doesn't get crashed. With the exception of that, this is a very important distinction. We are not allowed to obscure the meaning of any message. What if I said red 684 blue? What if I told somebody that over the air? They're just words, right? If that had a meaning to somebody else that was only one person, that would be a message encoded to obscure the meaning. That is not permitted. So encryption is one thing. We do encryption all the time. Encrypting things is okay so long as everybody has the decryption key. Right? We are not a service that exists to send secret messages, to send things that are, private. Right? That's why for instance, in Meshtastic, that's why there's a Meshtastic mode and an amateur mode. Amateur mode, you can run higher power, but you have to turn off the encryption. Any country that the FCC says that we are not allowed to talk to, we are not allowed to talk to. Any country that applies to the ITU, which is a part of the United Nations, that says we don't want the people from this country to talk to our hams, they send something in, and the ITU has to act on it. Under what circumstances can you get paid for running a ham station? And there's really only one. If you are a teacher, if you're a teacher and you receive a salary for teaching in a classroom, you can use amateur radio as part of your classroom instruction. You're allowed to use the ham bands to sell stuff, but it has to be occasional and it has to have something to do with radio. So you can't, in other words, you can't run a business. We're a non-commercial service. You can't run a business over the radio. Broadcasting, like I said, broadcasting is intended for the general public. We don't broadcast. Take it out of your lexicon because you're never going to say it with regard to ham radio. Under which circumstances are one-way transmissions? That would be similar to a broadcast, except that who is it intended for? It's intended for hams. We are not allowed to broadcast. There you go. We're allowed to send Morse code practice. We're allowed to do telemetry. We're allowed to do beacons and stuff like that. However, we are allowed to help broadcasters in an emergency situation by allowing for news gathering, sending information back that could be broadcast to the general public, but only when we have what again? Immediate safety of human life or protection of property. If that is part of the answer, that is going to be the right answer, because that kind of trumps everything. So, what are we allowed to talk about? You'll hear, I used to joke about this. I used to get, because I was licensed at 15, I used to hear people complain about, oh, my back, my sciatica is really acting out. Oh, how's that? I got an eye doctor appointment on Monday. I'm going to have that. I had a cataract taken out this year. I'm going to have that cataract taken out. You know, I used to laugh when I used to hear stuff like that, but now that I'm in my, mid to late 50s, I hear that a lot. I say that a lot. You're allowed to talk about stuff. That's basically the rule. You're allowed to talk about stuff. Your kids, your family, talk about radio, talk about cars, talk about cooking. Comments of a personal character, they call it. Control operator and control types. Okay, no station can operate without a control operator. This is a very important distinction. Okay, a control operator is the person who is responsible for what is coming out of a station. A control operator is the person who is in charge of a particular station. A club station license has no control operator listed. In other words, a club station is a station license only. There is no control operator. Therefore, could somebody who is unlicensed walk into a club station and use it?
No.
No, they cannot. I can, as a control operator, walk in and say, I'm going to be the control operator. And then it can be used. So there's two separate parts to your license. There's a control operator license, and a station license. The station license licenses the equipment. The control operator licenses the controller. That would be you. That being said, what privileges does that station, a club station, have?
Only what I have.
That's right. It has only what you have. So if you have a technician class license, what privileges can that club station operate with?
What I have.
That's right. Whoever the control operator is provides the privileges for doing it. If something goes wrong on a club station, both the control operator and the licensee of the station are responsible for what went wrong. Okay, so a repeater that inadvertently retransmits communications. It's kind of weird because you'd think in a repeater is automatic. I'm actually the control operator of a repeater up in the Coast Range. It is transmitting right now, and I'm not using it. I'm not listening to it. In theory, I try to listen to it as much as I can, and I am ultimately responsible for what comes out of it, unless it's operating in automatic mode, in which case somebody who, let's say, hops on our repeater without a license and starts cursing into it, I am not responsible for that. Now, I may be available to shut it down if somebody tells me. I have all the kill codes. I can do that. But ultimately, the originating station is responsible. Even if they're not licensed, they're still responsible. Okay.
Somebody who is licensed is on there spouting off inappropriate language. Are you responsible in that case, or
nope.
Is that falling them?
They're still responsible. If it's an automatically repeated system, they are responsible. You are ultimately responsible for what comes out of your mouth. Anyone who is allowed to operate on a satellite uplink frequency is allowed to use that satellite. Even if that signal is then shifted somewhere else where, let's say the 15-meter band, where you don't have privileges because you didn't put the signal there, it was moved somewhere else by somebody else, even if it has your voice on it, you're not responsible. Okay, the control point is the point from which a control operator controls the station. If it's a handheld radio, it's that little push-to-talk button. If you're operating remote, you're sitting at the keyboard, you're connected to another station over the internet, you're at the keyboard is the control point. That is known as remote operation.
So that's what you're doing with yours?
It depends. I mean, I'm not on it right now, but I do have over the internet, I do have my computer and radio upstairs in my shack outside that I can control using TeamViewer, in which case I am then a remote controller of my station. But like my station at home cannot just simply be operating automatically without me physically being there.
Right. No, I meant the one that you were in charge of.
That one's automatic. I'm not actually technically physically there at all. But my station in the garage, from this computer, I could control that station from this station in my downstairs, in which case I would be operating remotely. That would be remote control. You have to identify every 10 minutes. and at the end of communications. Notice you do not have to identify at the beginning. You do not, if you're using signals to transmit to a remote control craft, you do not have to give your call sign on the air. The transmitter actually has your name, call sign, and address on the transmitter. In the United States, you identify your call sign using English. You can also use Morse code to identify your call sign. If it's over a repeater, this is very common. You'll hear Morse ID in the background. Then it doesn't interfere with people talking. The phonetic alphabet, use of the phonetic alphabet is encouraged to eliminate ambiguity. If you're using tactical call signs, if you happen to go out into the field and do emergency communications or like public service stuff, you may be helping out race headquarters, aid station 2, emergency tent 1, logistics station A, whatever it happens to be. That's a tactical call sign. That is not a replacement for your FCC call sign. The rules about giving your call sign are you have to ID every 10 minutes and at the end of each communication, period, with your own actual call sign. So you are allowed to do self-assigned indicators when using phone and Morse code and whatever else it happens to be. To operate in another country, let's say that my call is N7JI. If I'm operating in another country, over in Europe, for instance, I would be like 9 alpha / stroke or slant N7JI. I can use any of those. In the United States, if you're operating in a different region, for instance, I would be N7JI / 4 or N7JI portable 4 when I'm operating in Alabama. That would be self-identified. Third-party communications. A third-party operator is somebody who is neither one of the licensed operators on either end of the contact. So a third-party person would be somebody who either handed a message to somebody else to pass for them. That would be a third-party communications. In other words, on behalf of somebody else, or it could actually be somebody sitting in the chair talking on the microphone. Who is ultimately responsible for what comes out of a third party's mouth?
The operator.
The control operator who is sitting right there. So if somebody gets on the air who's a third party, unlicensed, and starts communicating in a method that the control operator decides is inappropriate, what is the control operator's job?
To stop them.
Stop them from doing it, yeah. There is, even though hams can talk to other hams all over the world, third-party operators cannot necessarily talk to third parties in other places or to hams in other places. There are third-party agreements that exist.
Would that be the type of thing like in a disaster where, let's say, I was talking to somebody in Seattle and they said, hey, you're in Alaska. Could you give this message to a friend of ours and our family in Anchorage?
Yes, and within the United States and Canada, that is always okay. Third-party traffic is always okay to handle within the U.S. and Canada. But other countries where the U.S. does not have a third-party agreement, like there is no third-party agreement between the U.S. and Japan. So you cannot pass a message on behalf of a friend to somebody in Japan. So you just need to know those rules.
Where is that listed? What countries we do and don't?
Okay, last thing is that if the FCC comes a knocking, you got to let them in. So, okay, so the question is the U.S. third-party agreements. Okay, so ARRL, U.S. third-party agreements. Here we go, third-party operating agreements. I'm going to hopefully pull that up, and there we go. And now we're going to share it. Here we go. So if you get your license, I sincerely hope you join the American Radio Relay League, because the FCC is not going to go to bat for you, and for any reason. The ARRL is the national organization for ham radio in the United States. The FCC, the FCC does not care about most of these things. The ARRL does. The ARRL is the one who lobbies the FCC and and Congress to get things done, and maintains lists that are searchable, and does all kinds of services like the Teachers Institute and scholarships and stuff like that. So, and I'm also a section manager, which is a volunteer with the ARRL. So I strongly recommend that you become an ARRL member. You don't even have to be a ham to do it, at least not yet. The other thing is, if you're
about to ask you that.
Yeah, the other thing is, if you're under the age of 21, membership is free. If you're between 21 and 26, it's half price. So it is definitely looked upon with favor, especially when you're going for a scholarship. But yeah, so here's the list of stations with which we have third-party agreements. And I'll put that out in the chat if you're curious. There's our third-party agreements list. Okay, so how many people are sticking around for the general part?
I am.
Woohoo!
I would like, but I forgot to sign up.
Oh, you can stay. I don't care.
I might be there for part of it. I've got hay being delivered, so I might have to miss some.
Yeah, but once they start, they just unload, right?
I'll pay attention for at least a little bit.
I will
pretty much.
definitely be here.
All right. I am going to go grab something to drink, so give me just a sec.
Well, you folks have a good one. I'm going to bounce off of here for now. I'll catch you on another time.
Other time? Can you join some other time?
Join what?
This thing.
He's
What
doing the
time?
broadcast now, but he does have a schedule of classes.
Oh. Yeah, record this thing.
Well, actually, minimize that. Go into that. Go into my email.
Listening to, he does record it actually. If you check your email, he should have recorded last.
Okay.
You'll have last week's
Here's
recorded.
the recap from yesterday's. And there's a link, so I can get you all of yesterday's.
Oh, really?
It's right there.
Yeah, he'll send out today's recording later, either later today or first thing in the morning.
I don't think she can hear us.
We can play it another time, huh?
Mm-hmm.
But when you're not too busy with something comes up, and then you have to go someplace. It's still there. Okay.
All right, no, that's how I did it. Use that. There we go. Sorry.
Did we go on break?
Yeah.
Okay. I had to step out for a second. Thank you.
Okay. All right. So, no, Zed, we use Zed all the time. That's a Canadian thing. And Zed is, we use Zed all the time. I think it's just to distinguish it from the letter Z, which sounds a lot like C. QRZ. Can everybody hear me okay?
Yep.
Yeah,
Okay.
you did. I had a question.
Yeah.
Hey, when you were talking about the transmitting in other locations, the question, from any vessel or craft located in international waters, but you can also transmit from other.
Well, yeah, any part of the United States too.
What
like
about other countries?
Guam and well, you use your American call sign when you're transmitting from any part of the United States. It's the key. If you're anywhere else, then you're in somebody else's territory and you have to have their authority.
So, like, say you're in England and you're talking on the radio.
If you're in England, you're covered by CEPT.
Okay, see, I didn't even know this stuff. I just heard again. Okay, thanks.
Yep, you have to go look up the CEPT, agreement with the United States.
So my question is, you said a self-identifier, like it said, your call sign and then something
So let's
slash
say,
or this.
yeah. So let's say you're in California. You'd be KL4IZ/6.
Okay.
Because California's 6 land. Just to say, look, I'm not in Alaska right now. You don't have to do that, but it tells people that you're not in Alaska.
So /6 because I'm in California.
Right.
Or /4 if you're in Florida.
Or like when I go to Alabama, I'm N7JI Portable 4 or Stroke 4.
So you can look those up and see what they are.
Well, again, it's a self-identifier. Like I have in my logs, I have logs as N7JI/1/2/3/4/5/6/7 portable, and then I don't think I've been /9, but /8, and then I haven't been 0, but then I've been in VE1, no, VE2, VE3, VE4, 5, 6, and 7, which is all throughout all throughout Canada.
Okay.
My wife and I used to work a lot of maritime mobile when we were cruising.
Stroke MM.
That would be an MM.
Yep.
And where do you find those?
Well, MM is just maritime mobile.
Okay, but like the numbers you were using for Canada or...
So have you ever seen the big prefix list?
No, I guess I will have to do that.
No, haven't seen it.
ARRLDC, let's see. Country lists and prefixes. Again, another good reason to, let's see, text version, deleted entries, current entries, go now.
Wow.
Yep. And then you should always, on your map, have something like this.
Oh, wow.
If you work DX, oh wait, that's calling. No, I don't want calling codes. That's stupid.
That's a whole other class.
That's a whole different thing. Amateur Radio World Prefix Map. You can get a laminated one of these for like $15. There's all your prefixes. Every country has their own. Every territory has their own. If you get into DXing, that is essential.
Well, earlier today, when you had the frequency map up, I noticed something that said in red lettering about it being bordering the Canada border.
Mm-hmm.
So does that affect people like me I'm in way upstate New York near Lake Ontario, which is like 3 hours from Canada?
It's within
You
a
know what
certain it's within a certain distance, and I think it's Western Canada. I think it's
Okay.
specifically the 49th parallel. I think,
Okay.
but yeah,
I can research.
you got to take a
I'll
look at the
research.
rules.
Yeah, I will. Thanks.
All right. Any other questions? Did everybody like the first part? Was it
Yes.
worth doing, even if you're going as a refresher?
Yeah.
I learned so much that I didn't understand from before.
Good. Okay. So what I really want to know is if this next 3 hours or so, whatever it turns out to be, is really helpful. If it gives it short shrift, or it kind of requires that you do the first half. So when I sent out the note, I tried to cover the fact that, this is 3 hours of an addendum. If you're an expert in all the technician stuff, this is going to be great. But otherwise, you might want to do the whole thing. So, all right, here we go. So I'm going to close the technician class book. And no, I don't want to save anything. Okay. So what you will notice, does anyone have a copy of the general class thing that we downloaded? Did anyone download it?
Yeah, I bought it and downloaded it. Yeah.
Okay. It's actually not a bad book. I mean, it covers fairly briefly everything. I sort of use it as a guideline, and notice the stuff that's in it: electrical stuff, circuits, practical circuits, signals and emissions, antennas, feed lines, radio wave propagation. And if you just sat through the last day and a half, you might recognize that, wow, a lot of those things seem really similar, don't they?
You sent this to us in an email?
No, this was a link that you could go to from KB6NU's website.
Oh, the guy that you gave the free tech. Yes,
Right.
I downloaded the general. Yes.
Okay, good. You don't have to, but I think it's a pretty good book. And okay, so what we're going to start with is doing electrical stuff. And I want everybody to note that really what we did in the last day and a half, I covered a lot of this stuff already. And I want you all to notice for instance, what is reactance? You did not need to know that for the technician class, did you?
No.
But notice that it's in here, and we did cover it. Does everyone remember what reactance was?
Combination of capacitance and inductance.
Well, specifically, reactance is how something behaves in the presence of AC. So here's resistance. So you have two axes. You have the resistance axis, and then you have X, which is the reactance axis. The resistance is specifically to DC, and the reactance axis is specifically to AC. And the impedance is a combination of the resistance and the reactance, because these are actually perpendicular to each other. Most important to note is that you have an angle associated with it. So you can have positive reactance and you can have negative reactance. So notice which of the following is opposition to the flow of alternating current in an inductor? That's reactance. Which of the following is opposition to the flow of alternating current in a capacitor? What do you know? It's reactance. It's the letter X. It's measured in ohms. We covered all that ad infinitum, ad nauseum, I'll say. So, how does an inductor react to AC? We did that little formula there.
Right.
XL is equal to 2 pi FL. So, as the frequency goes up, what happens to the reactance? It goes up. What happens to a capacitor? Is equal to -1 over 2 pi FC. So as F gets bigger, it starts really big and it goes down, but never gets past 0. Okay. And look at that. They actually mention it. 1 over 2 pi fc and 2 pi fl. So we jumped the gun a little bit. We gave you a bit of a head start. So what is impedance? So what is impedance? Go back to Ohm's law. What's Ohm's law again?
E equals I times R.
And now we're going to go to the next step, which is to say that E is equal to the special case of I times Z. And Z, remember, is now our impedance. And impedance is, here's our resistance and here's our reactance. So here's our resistance and our reactance, and here is our impedance. Impedance now has a magnitude, which is the length of the vector, and an angle. We're going to take this and rearrange it and say Z is equal to E divided by I. So now we can see it is the ratio of the voltage to the current. And guess what? That says what it says right in the book. And let me make sure that's visible. Look what it says right there. Impedance is the ratio of voltage to current. Okay, so now notice we have this inverse of impedance. It's called admittance. I'll bet you can never guess what the units are. What's the unit of impedance? Everyone? How do we measure impedance?
Hertz.
Ohms. I'll bet you never guess what the unit of admittance is.
Ohms.
Amperes.
What?
Ohms.
Nope, it's not ohms because it's inverse.
Amperes?
Nope, remember it's inverse.
Wouldn't it be farad
Amperes?
because it'd be more like a capacitor?
Nope, because because remember you get things for both capacitors and inductors. Come on, if you were being really clever, what would you call it?
Current?
Well, it's inverse ohms. If you were being really clever, if you thought you were being really clever, what would you call it? Let's say you thought you were the cleverest person alive. What would you call it?
Iohms.
Close.
Voltage?
Nope.
Anti-ohms?
Close. That's really close.
Diome?
I love these answers.
Gnomes. I like that one.
Nope.
That's perfect. Gnomes.
Acceptance.
Nope.
How about acceptance?
There it is.
What?
What'd you call
You're
it?
joking.
What?
It's a mo.
Oh.
Mo. M-O-K.
Admittance is measured in mo's.
Oh my God.
It's true. It's really true.
This conversation has gone to heck.
Yeah. You know what the symbol is?
Upside down ohm symbol?
Yep.
Are you kidding me?
No, I'm not.
Oh.
But it now it also has a new name. Don't laugh.
Siemens.
You've ever heard of Siemens, Werner Siemens?
Yeah.
Yeah, that's the other name now for a mo. I guess somebody thought that mo was just too funny. Who says engineers don't have a sense of humor?
I mean, really?
Hey, Mo.
Hey, yeah, exactly. Okay, so that is an inverse ohm. It's an inverse ohm of impedance. It's called admittance. Well, look at that. In all my years of engineering and amateur radio, I've never had an occasion to use admittance. That is not true for me. I did admittance matrices in college. So, okay, the important thing to note also about impedance is that impedance, we're not gonna do Mohs anymore, but that is one of the best things ever. Okay, so here's our resistance and here's our reactance, and that causes impedance. So here's our R and here's our X, and here's our Z with an angle. Okay, so Z is equal to V divided by, or E divided by I. Voltage divided by current. Okay, but now, let's say that our Z is 5 ohms with an angle of positive 50 degrees is equal to E divided by I. So now E is equal to I times 5 times angle of 50 degrees. Well, this can actually be broken down into a sine and a cosine. The other way to think of it is that the voltage is 5 times the current, and it is rotated 50 degrees. So now, if I have a current graph, what this means is, remember we did phases? Remember we showed what phases look like?
Yes.
Okay, if I were to draw this, what I end up with is, so here's my current. My voltage is 5 times the size, and it is shifted forward 50 degrees.
So the I minus 5, that means I'm going to
I times 5. I times 5. Multiplied. It's 5 because it's 5 times, and it's shifted 50 degrees forward. So this is an inductor. Inductors have positive reactance. What this means is that in an inductor, the voltage leads the current through the inductor. The voltage is ahead of the current.
You said inductors have positive, say that again?
Inductors have positive reactance. Capacitors have negative reactance. See? And in fact, it says voltage across an inductor leads the current because of Lenz's law. Lenz's law resists the buildup of current, so it takes a finite time for an imposed voltage to force the buildup of current to its maximum. So there you go.
So I don't know if this is a stupid way to remember it, but when I hear of people that buy an induction stovetop, so you're putting the metal pan on top, and within seconds it's boiling the water. It's I don't know, speeding up the energy.
I don't know. I mean, I know there's some. Okay.
Voltage.
No. This is it. This is it. Eli, the Iceman. So voltage leads through an inductor, which is L. Voltage leads the current, and through a capacitor, current leads the voltage.
Okay.
Eli the Iceman. I knew there was something like that. It took a little while to remember that.
Say it again. Can you say it again?
Right there. Eli Iceman.
Oh, the last part.
Oh, just E is voltage and I is current. So through an inductor, which is L, the voltage is ahead of the current. Eli the Iceman. And in a capacitor, which is C, the current leads the voltage. Now, the question is, why is any of this important? I want to make sure that everybody can see that. Can everybody see that okay?
Yes.
Okay. So, why is this important? The reason it's important is because if I have voltage and current, let's say that they're shifted a certain angle so that at any given point, I have power, right? What's the formula for power?
B equals, I times E.
I times E. What if they are shifted with respect to each other? At some point, they might cancel each other out, right? So this is actually I times E times cosine of the phase angle, which in this case is 50 degrees. This is real power. This right here is what happens when you are in an industrial environment and you run a big electric motor. The power company still has to deliver current, but it's out of phase with the voltage.
Oh, three-phase, okay.
This is called the power factor. And the power factor, this is real power. There's also something called volt amps, which is just volts times amps. There's also something called VAR, which is volt amps reactive. I'll bet you can guess what that is. Because it's a function of the reactive power. The problem is that those volt amps reactive don't do actually any work in turning your motor. What they do is that they cost the power company time and energy trying to get that power to you. They still have to deliver the full current, even if you're not using it. So in order to limit this, what you end up doing is, let's say that I have my induction motor. Here's my current. And here's my voltage. You really want them to be overlaying each other. So what would I do with my inductor? What would I put after it? I would put a capacitor after it, which would add some of this, which is shifted the other way. And when I add the two together, they hopefully will be in phase, and then the power company doesn't have to deliver any significant additional reactive power to me.
But you need three, don't you? You need three of those. You
Yes.
need three transformers
Right.
on the pole.
Yes, because you have
Okay.
three phase.
Yeah. Okay.
So anyway, that is where we get our power factor from. Now, what's important about this is that this is also the basis for, if we draw our graph, I want to erase that. Okay, so if we draw our graph again and go like this, and we have our resistance and our reactance up here, and we have a resistance and a reactance, oops, XL, and then we put a capacitor after it, and it is XC and R, and they are completely equal and opposite from each other. What will happen to these guys when they add them together?
They're going to cancel out.
They cancel each other out. And this is why we get resonant circuits. Because this is the point at which we minimize our reactance, minimize the impact of the circuit at blocking AC. So that's why we can have a series circuit that is resonant at a given frequency. This is 2 pi FL, and this is minus 1 over 2 pi FC. You add them together and you get 0. So your reactance goes to 0, so it is most favorable at the frequency for which that's true. You select your values of C and L. That allows you to select your F, which allows you to select your resonant frequency, which allows you to basically tune your circuit. And we covered that before, and that's a little more detail. Does that make sense? Look at that. What occurs in an LC circuit at resonance? Everyone? We just proved it. Look at that. We just proved it. Okay, what happens when inductive and capacitance reactance are equal in a series LC circuit? Resonance causes impedance to be low. If they are in a parallel circuit, it causes it to be very high. So basically, it's a peak of one way or another, one thing or another. Okay, which of the following devices can be used for impedance matching at radio frequencies? A transformer. We know that one because we saw it before. A pi network. A pi network is an LCL or a CLC. If I were to draw a pi network, did it shift or did it not shift?
It shifted the other screen.
Okay.
Okay, there.
Yeah. Okay, so there's a couple ways to do this. Okay, so here's my unknown impedance out here. And to connect to this, I can do a network that looks like this. Oops, let's do it the other way. And I want to see 50 ohms. All right, so I have, this is a variable capacitor, variable inductor. These two are in series with each other, which is then in parallel with this, which is then in series with that. If I select those values, I can magically have a very wide range of frequencies that I can use to tune these guys. So this looks like a big letter T, does it not? Any guess what that network is called?
Pi network.
That's a T network.
T network.
That's a T. Okay, so I can make it another way. And so I'm going to draw it so that it looks like this. Any guess what that network would be called?
That's a pi.
That's a pi network. Yep. So these circuits are used for matching impedance. You can use a T network, you can use a pi network. The other tricky thing is that you can, and this is still to me one of the coolest things there is to do. Okay, I can take an impedance out here, and I can hook this up to a piece of coaxial cable which has a characteristic impedance. What is most coaxial cable out there? How many ohms? Do you guys remember?
50.
50 ohms, okay. And I'll call this ZL, which is Z of the load. And so this is Z input. I need to remember if I need to make sure I get it right. It's a quarter wave matching. There we go. Okay. Zn divided by Zo is equal to Zo over Zl. And this is for a quarter wave. So this is actually really profound, right? So if I have, let's say, 100 ohms and a 50 ohm piece of cable, and this is a quarter wave long at a given frequency, I can plug these in and say, what is my Zi? And that is, doing this, Zo squared divided by Zl, which is 2500 divided by 100, which is 25 ohms. I have basically just taken this 100 ohm impedance and magic, it looks like 25 ohms. This is a quarter wave matching transformer using a piece of coaxial cable. Why would I ever want to do this?
You're tuning a signal or adjusting. I
Yeah,
don't know.
yeah, exactly. Well, and how many different frequencies does it work for once I cut it to length? It has to be how long in order to do this? It has to be a quarter wave long. How many frequencies once I cut it to length does it work for? It works for exactly one frequency. That's it. But you can do a quarter wave matching network. You can do this for, let's say you want to feed two antennas with the same signal. If you put two antennas in parallel, it might not work very well.
So the 2500 is, you knew your wavelength. You knew.
No. Well, I cut it for the particular wavelength that I knew I was going to be doing. Yeah. And it's 50 ohms because that's what the characteristic impedance of that cable is.
I'm
That
just
is,
trying to understand how you got the Z out. That's
well, no, ZO right there. That's the characteristic impedance of the cable. That is 50 ohm cable. The fact that I used a quarter wavelength of it is what allows this to work. So really, it's not ZO, it's not Z out, it's Z naught, which is the characteristic impedance of the cable.
okay. So that would make ZI.
That's in.
50, right. That would make that equation ZI equals, and you've got ZO over ZL.
ZO
I
squared.
understand the
ZO squared. This ZO moves moves over there.
Oh, so, okay.
Because this is the equality right here. So to isolate ZI, we multiply both sides by ZO. That puts a ZO squared on the right side. So 50 squared is 2500 divided by 100 gives us 25.
I missed the squared. That's what I kept looking at that going, how did he get that? Now I get it.
So this is a quarter wave transformer. This is actually used a lot of places for antenna matching, especially if you're going to be feeding two antennas in parallel. Very useful tool.
So can you double if you wanted to put two in parallel, can you double the length of the wire? So instead of it being a quarter, it's a half?
Half wave doesn't work.
Okay.
When you get to a half wave, it goes back to the way it started.
Okay.
I know. Half wave basically looks like a nothing. A quarter wave is a magical length. And if you're curious as to where this, a tool that you can use to figure this stuff out, there is something called, has anyone ever heard of a Smith chart? Anyone? No?
No.
Okay. This looks imposing, but in reality, let me find a good picture of it. There we go. Okay. This is still, after all these years, one of the best tools that there is for figuring out what a piece of cable does to impedances. Like I said, it looks imposing. This is actually on the extra class exam. But it shows you what happens to the real and reactive parts of the impedance, and it shows you what happens to the magnitude based on the rings around the outside are the length of the matching network, the length of the matching cable that you're using, whether it's a quarter wave or a half wave. A half wave is one full trip around this circle.
And a quarter wave is half.
Is halfway
Can you
around.
kind of show what you would do, how this
Oh
works?
boy, this means I got to try to remember exactly how to use it. So you have a normalized impedance that gives you a circle, then you can basically rotate around based on what it is. So notice that on, let's see, notice that this is what point, if I were to draw a circle based on the center, the 2.0 ring is right across from the 0.5 ring. So here's the 2.0 ring right here, and here's the 0.5 ring.
Mm-hmm.
So by starting over on the 2.0 ring, for instance, if I draw a circle around and go halfway around it, I'll end up on the 0.5. And notice we went, during that example, I started with a 100 ohm impedance compared to 50. You normalize it based on the Z naught. Here's the 1.0. That would be our 50 ohms. We started at twice that over here, and we ended up at 25 ohms, which is half that. Depending on how far you go, you end up somewhere else in the woods. You notice all these intersections of lines? Let me see. Oh, I can't really draw on this too well, I don't think. But basically, it is an incredibly useful tool. You can do it mathematically, but it's a lot easier to do by using this chart. And that's why the chart exists, because somebody said, you know what, the formulas are a pain in the butt, and I'm going to make this chart. Does that help at all?
Mm-hmm.
Okay. I mean, it's not that complex once you get into it, and if you're going to be building antenna systems, it's actually very, very, very helpful. Okay, let's see. Decibels, I think we already did that. Current and voltage dividers. All right, so remember we mentioned the name Kirchhoff at one point? Kirchhoff's current law. That basically says that the sum of all the currents at any given point, called a node, the currents in have to be equal to the currents going out. So this is a current divider because the current in has to be equal to the sum of the currents going out. The currents that are going through these resistors in total have to be equal to this input current. And on top of that, the currents are inversely proportional to the sizes of the resistors. The bigger the resistor, if you want to think of it, let's say that this resistor right here, R2, didn't exist at all. If it wasn't there, how much resistance would there be? Let's say it was just a big open space. It'd be infinity. How much current would go through an infinity resistor?
Infinite.
No. How much current goes through an infinity resistor? You can't push hard enough. There'd be no current. There'd be no current. Right? So essentially, you get an inverse relationship between the amount of current and the resistance. Okay, and I avoided talking about this one because I knew we were going to be talking about it afterwards. Okay, does everybody see that nice little sine wave?
Mm-hmm.
Okay, here we go. I am going to draw something here, and I'm going to erase this. Here we go. There's our sine wave. Okay, so I'm going to call this 120 volts AC. There is something missing from that I wrote. Everybody see that? It says RMS. That means root mean square. Okay. Now, the tricky thing with this is that RMS is really, really important. The reason that RMS is really, really important is because I am going to now draw a DC circuit, or DC voltage, at 120 volts. All right. And this DC circuit, I'm going to pick a time, just kind of randomly. What is the voltage at that time? Come on,
120.
somebody tell me. How many volts? 120 volts.
120.
Okay, I'm going to pick another one. What's the voltage at that time?
120.
Okay, how about at this time?
120.
Okay, how about at this time?
It's going to always be 120
It's
right now.
always going to be 120. Okay, so over a long period of time, what is the average voltage that I'm going to see? How many volts? That's right. Okay, 120 volts. So if I look at a given resistor, and I'm going to call it R. Ohm's law says E is equal to IR, and P is equal to IE. Everyone agree with that?
Yeah.
Okay. So I'm going to do some substitution for I, and I'm going to find that power is equal to E squared over R. Right? I just did some substitution for the letter I and got power is equal to E squared divided by R. Okay, so now, what is my average power over any amount of time? It's E squared over R. Agreed?
Mm-hmm.
Which is, in this case, 120 times 120 squared is 14,400 over whatever R is. All right, so now we're going to look at this AC circuit. What's the voltage here at this time? Anyone?
Yeah, it's 120.
No, I don't know. What's the voltage right here? Yeah, what's the voltage here?
Oh, wait.
100.
Yeah, I don't know. Yeah, I don't know exactly. What's the voltage here?
120.
Okay. Well, we'll just call it at its.
Formula to calculate this.
Yeah, we'll just call it at its peak. What's the voltage right here? I don't know. I have no idea. What's the voltage here?
Negative.
At negative peak. Well, we know that. We're just going to call it negative peak. Right? Okay. So, if we know that, again, P is equal to E squared divided by R, does it matter if the voltage goes positive or negative? When we square it, what happens to the negative sign?
It becomes positive.
It becomes positive. Okay, well, at least there's that, right? Well, if we were to look at it right here, we're going to draw it with a red dot. And here, and here. What is my power when my voltage is nothing?
Nothing.
We get zero power. Uh-oh. Well, we get no power there, and no power there, and no power there. How about up here at the peak points? Up here and down here. What is our power at that point? We get V peak, whatever it happens to be, squared divided by R. Would everyone agree with that?
Yes.
Whatever that happens to be. How about all those intermediate points?
Well, it's going to be less than the peak.
Well, right. It's going to be less than the peak. All right. So, how much less? It's a sine. So, it's a sine wave. So, it's sine squared. You'd have to know what the sine is at every one of those points to be able to do sine squared. And then, to say, okay, well, What would we have to do to this to make it deliver as much power on average as that? That is what RMS is. That is what the definition of RMS is. And notice it's getting a little more complicated now. So basically we would have to sum up every power or every voltage and figure out what the power was at every given time, figure out what that happens to be, multiply it by a certain amount of time, and then average it out over the whole time to figure out what the average power was, and then set that equal to the DC. Well, it turns out that that becomes a calculus thing, because the power is v squared over r, so that would be v sine theta divided by r, like that, dt. So sine of t squared dt, and then we'd have to average it out by the big letter T, which is the whole period. And it gets really, really messy after that. We'd actually have to go through and do our calculus and our integration. And you know what? This is not a calculus class, so we're not going to do that. Well, what it turns out is that in order to have this RMS circuit and voltage develop as much average power as the DC circuit, the DC is really simple, isn't it? This peak voltage is equal to 120 times the square root of 2. Which is about 170 volts. Essentially, an RMS voltage is an AC voltage or any voltage that makes the equivalent amount of power averaged out as a DC voltage of the same voltage. Because the power drops down to 0 at these points and you have to make up for it somehow. So what you do is you boost the voltage even higher at the peaks, which means you need a bigger sine wave. So if you look at 120 volts VAC, this is what's in your wall, RMS. What you'll find is that your positive peak and your negative peak are about 170 volts. If you actually take this and put it on an oscilloscope, you will see peaks at plus and minus 170 volts. That is what you will find in order to make the same amount of voltage. Didn't know that was Did you know that was hiding in the wall?
No, but what if it's a 220?
Then it's the square root of 2 times 220.
Okay.
So it would be, what, 340 volts? Plus or minus 340? That actually really becomes very important if you're looking at something that you're plugging in or like trying to build a filter across your wall circuit, because let's say that you have a capacitor that you want to use to filter out noise or something, and it's rated at 150 volts. What'll happen to that what'll happen to that capacitor? Your capacitor will blow up because the peak voltage is actually what?
170.
170, yeah. So all this is happening inside the wall. Okay. So that is the basis of what is known as RMS. And again, the reason we use RMS is because we actually care about the amount of power that's being made over a period of time. Okay. There we go. What value of an AC signal produces the same power dissipation as in a resistor as a DC voltage of the same value? There it is. Okay, so what is the RMS voltage of a sine wave with a value of 17 volts peak? Well, if 120 volts RMS made 170 volts peak, it would make sense that 17 volts peak was made by 12 volts. It's that square root of 2 factor. Same thing with this. 120 volts RMS has a peak-to-peak voltage of about 340 volts because that's from the high peak to the low peak. Okay, so now the important thing to note here is if there is a DC power source or an AC RMS power source, they're going to make the same amount of power. That is the definition of RMS. So let's say that we have a power source that is, in this case, they say 400 volts DC. Across let's say 1,000 ohm resistor. Okay, what's Ohm's law? Everyone? Come on, don't be shy. What's Ohm's law? P equals I times E.
I squared R. Oh.
Yep. Well, P equals I times E, and E equals I times R. Okay. And in this case, what do I have? I have my E, and I have my R. So I could figure out what my current is. Equals 400 divided by 1,000. Whoops. .4 amps. And then my power is equal to 0.4 times 400 would be 160 watts. Okay, so if we were to change this to say my voltage was 400 volts VAC RMS, what can you say about it? The equation would be exactly the same, because that is the definition of this RMS thing. The RMS is the AC equivalent to a DC voltage that makes the same amount of power. Everybody good with that?
Sure.
I know there's a lot of stuff. This is some pretty heavy stuff, but okay, so there's electrical power. Okay, so RMS voltage across a 50 ohm dummy load dissipating 1,200 watts. Where would we start? Somebody walk me through it. And I don't mind taking a little while doing it. Somebody walk me through it. Come on, somebody walk me through it. Anyone? Tell me what things I know.
I know my resistance.
Okay, excellent. You know your resistance. Good. Okay, what else do you know?
I know my power.
You know your power. Okay. So, give me some formulas. What are the first things we always write down? P equals I times E. And E equals I times R. Agreed?
Mm-hmm.
Just write them down.
If I know my power and my resistance, couldn't I take the power divided by the resistance, and that would give me I squared?
Yeah, but that's skipping a step. I want people to go through the process. Okay, so what do we have? We have P equals I times E, E equals I times R. It's a good idea to write everything down. Resistance, R, is what? How many ohms?
50.
Okay, and power is 1200 watts. Agreed?
Yeah.
Yes.
Okay, good. Okay, so what do I know? I know P and R. What doesn't show up in either one of them? And what are they asking for? They're asking for the voltage, right? Okay, so they're asking for the voltage that generates that. Do they care what the current is?
No.
No. Okay. Well, so what we can do is we see this E here and we have an E here. We can substitute this E right there. So P is equal to I times R. We can do it like that. That doesn't really do us any good, so we're not going to do that. So instead, we're going to
P squared RMS equal P times R, so wouldn't that do it? To get the voltage, you take the square root?
Yep, that's where we're going. So we have an I here and an I here. We can take this one and rearrange it and say I is equal to E divided by R, and take that and substitute it into there. P is equal to E divided by R times E is equal to E squared R. Everyone agree with me so far?
Yep.
Divide both sides by R. E squared is equal to P divided by R. And then we take the square root to get E. E is equal to square root of P divided by R. Okay, so what is P divided by R? 1200 divided by 50, which is the square root of?
It's 20.
Square root of 60,000.
Wait, did I draw that wrong? Hold on. Yeah, PR, sorry, not P divided by R.
That's the square root of 24.
There we go. No,
Yeah.
There we go. It's P times R. Okay, so the square root of P times R.
Oh,
There we go. Sorry about that.
so whatever that is, sorry.
Square root of 60,000 is?
244.9489743.
Okay.
245.
245. Okay, 245 volts. And why don't I have to go any further? Because that is RMS, and RMS already takes into account all the power stuff. Now, if they were to then ask, what is my peak voltage? How would I find my peak voltage?
You would take the 245 volts and multiply it by the square root of 2?
Yep, that's it. And 245 times
340. It's 346.
346 volts. There you go. And that's how you do this stuff. Now, one thing to note, does it help to have a calculator handy? Yes, it does. When you get to this exam, it really helps to have a calculator handy. With the extra exam, if you're actually going to be doing the stuff instead of just memorizing it, it really helps to have the calculator handy. Okay, so here's another one. Peak envelope power, PEP. Okay, so peak envelope power is the largest amount of power made at any given point. So for an unmodulated carrier, this is one of those things just to memorize. It's 1. The ratio is 1. So if it's an unmodulated carrier, that just means it's a sine wave. For an unmodulated carrier, the ratio is 1 to 1. This is just another way of asking it. They said if the average power is some random value of 1060 watts, what's the output peak envelope power? 1060 watts. Okay, here's another one. What is the peak envelope power produced by 200 volts peak to peak across a 50 ohm dummy load? Does anybody want to walk me through this one? Who wants to go through this? Okay, so what does it mean 200 volts peak to peak? That's the first thing to identify.
So it's from the negative to the positive. So
Correct.
actually it's 100 from the baseline to the top, and then to the bottom is 100.
Correct. Okay, good start.
So let's see. So power equals I times R. So
no, do that one again.
I times E. Sorry, times volts. Sorry. So.
Okay.
So
okay.
I can't remember the numbers. Was it 50 and what was 50 and what was a?
Well, okay, so here's our voltage. It was 200 volts.
All right, so it's 200 total. So the voltage is so 50. So the E is 50. I mean, the E is 100. I'm sorry. E is 100.
No, hold on. It's 200 volts peak to peak.
Right.
Right? Okay, right. So if it's 200 volts peak to peak, what is V peak? How many volts?
100.
It's 100. What does that mean that the VRMS is?
It's 100 times, is it 1.1?
Divided by square root of 2.
Okay.
Which is about 70 volts.
Divided by
71 volts.
Okay.
Because this is V peak. Okay, so our VRMS is 71 volts. But now we can work with it. So what's our formula? P equals I times E. E equals I times R. And what do we have? We have our 50 ohm dummy load. They gave us that. Okay, they want to know what the power is. So we have an E and we have an R.
Right.
And they want to know what the power is.
So it's, you take the E is well, the power is, let's see, oh my gosh. So the E is 71 and the R, I is
R is 50.
71 divided by 50.
Right. So we could do this one and rearrange this one. E,
right.
I, R. And we don't know the I, so we cross it out. E divided by R is 71 divided by 50 is 1.4 amps. Good. Okay. So now we have our current is 1.4 amps. Okay.
So it's 1.4 times 71.
Yep. Okay. So now our P is equal to I times E is 1.4 times 71 is 100 watts. Ta-da! What does the book say? The book says 100 watts.
Okay.
So, none of this is magic, but, just application of whose law again?
Ohms.
With just a little bit of a twist thrown in, which is the understanding that peak voltage for a sine wave is different than RMS voltage. All right, let's see who remembers this from yesterday. A factor of 2 increase is how many dB?
3.
3 dB. Okay. This is one that I didn't know and don't usually use, but 1 decibel is about 20.6% loss.
Oh.
That's just memorization. Or you can use a calculator. Okay. Next thing, electronics. We have resistors and capacitors and stuff in series and parallel. Okay, here we go. Why is this doing that? My computer, my iPad's acting weird. Okay, so we're going to erase this, and we're going to have 2 resistors in series. Let's say we have 3 ohms and we have 4 ohms. What is the sum of those two?
300.
How many ohms?
7 ohms, because they're in series.
7 ohms. They just add. Okay.
Oh.
Now, we're going to replace this. We're going to do something else. We're going to say this is 3 millihenries, and this is 6 millihenries. What is the sum total of those coils?
9.
That is 9. Yes.
Is that the admittance, the MH?
No, that's millihenries.
Oh, okay. Thank you.
Otherwise, it would be a mo. We're not doing
Okay.
those. Okay, so the way to think of this is that if you have a resistor and another resistor, the way that you can look at this is in physical terms, that just makes a longer resistor. A coil followed by another coil would just be a bigger coil. It would have more inductance. So, resistors and inductors in series add. So now I'm going to do a capacitor. This is not intuitive. So let's say I have 3 picofarads and 5 picofarads. What would the sum be? This is a trick. This is a tricky one because that capacitor, one is sort of affecting the other one. This does not behave the same way. If you think of this, I'm going to erase this and I'm going to redraw this. Capacitance is a function of the amount of plate area that you have. How would I make this plate bigger? How would I physically make this plate bigger? I would put another one in parallel with it so that you had more capacitance, essentially more capacity to store stuff. So if I have 3 picofarads and 5 picofarads, if they are in parallel, I get 8 picofarads.
Oh, wow.
So capacitors in parallel add. Inductors and resistors in series add. Capacitors, because they are built differently, they function on a different plane almost. They operate opposite.
I lost your split screen. Can you give it back to me somehow?
Whoops. I can try. Like that?
Now I can see it. Thank you.
So capacitors in parallel add together. Because essentially if they're in parallel, how do I make a capacitor bigger? I just make the plate bigger. I can add more plates. Whoops. I can just keep adding plates and make the capacitor essentially look bigger and bigger and bigger. So I add capacitance by putting things in parallel. So that is how they add together. So now, thinking about resistance, sorry, I started drawing an inductor. Silly me. Okay, So if I have 3 ohms and another 3 ohm resistor here, when my current comes in, which way does my current go?
Both.
It goes both. It has a choice, right? So essentially now my pipe becomes bigger. There is actually less resistance than there was just by having one. As opposed to doing this, which added more resistance by having them have to go through both of them, I've now given them a choice. And it turns out if we go through the solutions, if we go through the solution of the Ohm's law equations, we get R total is equal to R1, R2 divided by R1 plus R2, which in this case is 3 times 3 divided by 3 plus 3, which is 1.5 ohms. So if you have 2 resistors in parallel, your end result is that you get half of the resistance. Interestingly, let's say I have a resistor that is 1 ohm and another one that is 10,000 ohms. The same formula works. R1, R2 over R1 plus R2 is equal to 1 times 10,000 divided by 10,001 because they added together. What is 10,000 divided by 10,001?
Almost
equal to 1. Almost equal to 1. Essentially, this big resistor does almost nothing. That high value resistor does almost nothing. And in fact, I could then take this resistor, if you want to think about it in the extreme, and replace this with that. What is that resistance? Sorry, I meant to not do that.
It's open air.
Open circuit.
Infinite.
Yep, infinite resistance, open circuit. Infinity ohms. Well, essentially, that becomes infinity divided by infinity, which is 1. So, inductors work the exact same way. But now how about if I do capacitors that way? I do a capacitor here and a capacitor here. Capacitors in series, let's say I have 3 picofarads. This one is not intuitive at all. If I have them in series, essentially I get C1, C2 over C1 plus C2 is 3 times 3 divided by 3 plus 3 is 1.5. They work like resistors in parallel. Again, the formula is not that complicated, but intuitively, capacitors are the weirder one to think about. And I think the easiest, the reason being that this one causes like pluses over here, and this causes minuses over here, but then the minuses migrate over here, and it gets a little confusing. But essentially, that's what happens. So just basic electrical stuff that it's important to remember. Okay, so you don't actually have to go through the calculation unless you really want to, but just to note, for instance, 100 and 200 in parallel, it's smaller, it's actually 67. Here's the math for it. 3 in parallel, a 10, a 20, and a 50. If they're all the same, the calculation is really easy. If they're not all the same, it's a little more complicated. This is just one of those. You can memorize it, or you can remember how the formula works. It's 1 over R1 plus 1 over R2 plus 1 over R3. In this particular case, you may someday need to know it, but probably not. Okay, what should you do to increase the inductance? You add an inductor in series. This is just an application of the same thing. 20 millihenries in series with 50, They just add together. If they're in parallel, they divide. If you have 3 of them, they divide by 3. Capacitors in series, they do the opposite. Capacitors in parallel add together. This is a bit of a trick question. Notice that 2 5 nanofarad capacitors and 1 750 picofarad capacitor. Why is that tricky? What do you have to know when you see that?
Convert them, or
Yep.
one of them.
Right.
One of them.
And you have to know that nano is 10 to the minus 9th and pico is 10 to the minus 12th. So a nanofarad is 1,000 picofarads, for instance. So you have to know that. You have to be able to convert it. What causes a voltage to appear on the secondary winding of a transformer when an AC voltage source is connected on its primary? Well, coils. They're inductive. They're mutually inductive because they're on a common core. We drew an inductor this morning. We drew a transformer, if I'm not mistaken. The transformer kind of looks like this. On a common core.
Got your food right here. You got food.
Look at that. What is the voltage output of a transformer with a 500 turn primary and 1500 turn secondary? Okay, so we talked about this. What is the, let me unshare this so we can all see it. Okay, what is the turns ratio that is being applied right here?
I don't know what that is.
What's the ratio of the number of turns?
3 to 1.
3 to 1, and it's bigger on the secondary. So if you apply 120 on the primary, what will you get on the secondary? 3 times that, because the turns ratio is proportional to the voltage. That is a step-up transformer. It increases the voltage. The output voltage of if an input signal is applied to the secondary winding of a step-down transformer, which means it's going backwards. So the voltage is proportional to the turns winding, or to the turns ratio. The current is inversely proportional to the turns ratio. And we can also use this to do a transformer, to do a transformation of impedance. And why is this thing acting this way? Share. Okay. So we have N1 and N2. And we have V1 and V2. So we're going to go through this derivation again because it's like really important. Can everybody see that okay?
Yes.
Yes.
Okay.
Yep.
So if we have this ratio and we have this formula, V1 over V2 is equal to N1 over N2. If we have, let's say, 10 turns over here and 1 turn over here, that is a 10 to 1 ratio. Agreed?
Yep.
Okay. So that would be 10 over 1 is 10. So if we have 120 volts over here, AC, how many volts will we have on the other side? We will have 12 volts. Okay, so voltage is proportional to the turns ratio. But now we're going to say that we have our power efficiency, so that our power, we're going to have 100% efficiency that our power is the same on both sides. In order to make that true, we have 120 times, because power is equal to I times E, and we have 12 times I2, we can say that these things have to be equal. So now 120 times I1 is equal to 12 times I2. So I1 divided by I2 is equal to 12 over 100, or 120, is 0.1. Well,
Wait a
that's the
minute.
inverse of
I1
that.
is 120.
No, we don't know what I1 is. We don't know what that is yet. We can make this easier if you want, and we can say that, okay, we're going to just say that we have some current, we have some resistor that draws a current of 1 amp. Why don't we do that? Let's just do that instead of parameterizing it. What's our power over here? Is I times E. How many watts?
12.
Yep, because it's 1 times 12 is 12 watts. Since we have 100% efficiency in this transformer, if we have 12 watts over here, how many watts have to be delivered on the other side?
120 because it's 10 times.
No. If we have 100% power efficiency,
Oh.
if we have
On the
12
other side
watts
is-
on, we have 12 watts on one side,
You have to have 12 watts in the
12
other.
watts on the other side.
Yeah.
E is equal to I times E is equal to 12. Okay, so that means that we have I times 120 volts is 12, and I is equal to 1/10 of an amp. Agreed? How many amps did we have on the other side?
1.
Okay, so our power is inverse to the turns ratio. Sorry, our current is inverse to the turns ratio. So if we have some magical resistor over here that is doing this, well, okay, we could actually figure out what it is, but let's just call it R. If our voltage over here is 10 times bigger and our current is 1/10 as big, what's our resistance? If the power is the same,
1.
R is equal to V divided by I
So 12.
is 100 times.
Oh.
So the turns ratio takes the impedance on the secondary side and raises it by the turns ratio squared.
You caught a kitty. What I found. You caught a kitty.
So that means that if we have, let's say, something over here that is 2400 ohms, and we have something that's 50 ohms over here, what would we need for a turns ratio to match those? What is the ratio of impedances?
48.
2400 divided by 50 is 48. Okay, we have the turns ratio squared is equal to 48. So what's the turns ratio? 6.8. We'll just call it 7. So that means that you get an impedance match. So that's another use of this transformer. So that would make at this 2400 ohms on the high turns number of side, we'll call this 700 turns and 100 turns. That'll make it look like 50 ohms on this side. There's an antenna called an N-fed half wave. This is the basis of how you feed power into an N-fed half wave.
So I have a question.
Yes.
No, can you leave that up?
Oh, yeah.
So when we were doing the other problem, you said V1 over V2 equals N1 over N2.
That is true.
And just now we did N2 over N1.
It's because it's higher on the other side. I could flip it around. The nice thing about transformers is that you can reverse them.
So then I can reverse the equation. Then I can say N2 over N1 is equal to V2 over V1.
Sure. It's math. You can do anything you want so long as it's legal.
Okay.
Okay. Let's see, moving on to circuit components. Okay, wire wound resistors and why you should never use them in an RF circuit. Well, okay, what is a wire wound resistor? Somebody tell me what's inside a wire wound resistor. The answer is in that description.
Wire.
Okay, and what in particular about it?
Copper.
Okay, and what else? Looks like that.
Yeah, it's wound around it.
It's wound around a core. Okay, so this has resistance, right? Okay, if that has resistance, so looking at it, what else does it have?
Inductance.
It has inductance because it's a
inductor.
It's an inductor, yeah. So that means that its impedance is its resistance plus its reactance because it's an inductor. If you designed it to be a 50 ohm resistor, is it 50 ohms anymore?
No.
No, and not only is it not 50 ohms, it's 50 ohms and it changes based on frequency. Doesn't it? Because your impedance, your reactance changes based on frequency because there's a frequency component in there. Okay, let's see. Low voltage ceramic capacitors are cheap. Ceramic is basically literally, ceramic. An electrolytic capacitor. Has anyone ever blown one up? I have. They make this mess of goo and stuff everywhere. So an electrolytic capacitor is a very, very, very high capacity capacitor. Very big values for a very small device. Unfortunately, they are polarized, which means they have a plus and a minus terminal. If you hook them up backwards, you will cause rapid heating and blow it up. And they go off like a little firecracker. If they're inside a piece of equipment, they will make just a huge mess. So it's important to try to avoid that. Okay, what's an advantage of using a ferrite core toroidal inductor? Remember we talked about those just a couple hours ago? What is a ferrite core? What is it?
It's iron.
Iron powder, and what else? Some manganese, some nickel, and what is special about a ferrite core?
Magnetic.
It is a magnetic device. That's right. It's a ferromagnetic device. It's typically made of powdered metal mixed with glue and baked into a shape, like a cookie. And what's good about it is that it is really, really, it's high susceptibility, as they say. It contains most of the field inside the core. You get really big values of inductance, and they're tuned for a specific range of frequencies. That tuning is caused by the composition, which is known as the mix. The mix, for instance, on that Ferrite website, sometimes it's mix 75, mix 31, mix 43. They all have different frequency. They all have different frequency response. Oh, we covered this one too. How does a ferrite bead reduce common mode RF current? It basically creates a place for power in the magnetic field to be dissipated by creating an impedance in the current's path. Okay, when an inductor is operated above its self-resonant frequency, it actually becomes capacitive. This is a little hard to explain. It's easier to just memorize it. Solid state. Okay, a silicon diode has a drop of 0.7 volts. A germanium diode has a drop of 0.3 volts. We briefly talked about this. I know I mentioned it yesterday, but now you gotta remember it for the general exam. Which is why I say when I teach the technician class, I think I really cover most of the stuff necessary for the general. What is a MOSFET? A MOSFET is a metal oxide semiconductor field effect transistor. The gate is separated from the channel by a thin insulating layer. Does everyone remember that picture that we drew of a MOSFET? Maybe not. If you
No.
weren't here, you wouldn't remember. Okay, so Okay, so this is a FET.
Is that the picture you made with the diodes yesterday?
Nope, this one.
Okay.
That is a FET. It has 3 terminals. There's a gate, and there's a drain, and a source. And it's a field effect transistor because what you basically have is a thin insulating layer right here in between the gate and the drain source channel. That thin insulating layer makes this look like what? What does that thing look like?
A capacitor.
That makes it look like a capacitor. So by placing a voltage here, that affects what happens on the other side. So a metal oxide semiconductor field effect transistor is basically a layer of insulating material right there, which makes it into a capacitor. That's why it's field effect. It creates an electric field, which allows one side to affect what's happening on the other. Okay. All right, so that's a MOSFET. What are the operating points for a bipolar junction transistor used as a switch? Remember these 2 things we talked about briefly, saturation and cutoff? There are 3 regions for a transistor, cutoff, linear, and saturation mode. If we were to draw these out, we would find that it looks like this. This is cutoff, this is saturation, and this is linear. This right here is used for, who remembers this? What type of thing is this section used for?
Oh yeah, when you make your adjustments on your amplifier.
That's linear amplification. And cutoff and saturation?
Where they stop and start.
That is
On,
used for
off.
digital stuff. This is
On,
this is 0, and this is 1. So linear amplification is the linear region in the center, and cutoff and saturation are used for on and off. So you basically slam it on or slam it off. That's why we use them for a switch. Oh, vacuum tubes. Okay, so this is something that we never talked about because we never had a reason to talk about it. Vacuum tubes. Okay, so a vacuum tube uses a heater which causes this piece of metal to boil off electrons when it gets hot. Those electrons, this is the negative terminal. This is the anode, which is the positive terminal. What would normally happen to these electrons? Where would they want to go? Remember that this is a vacuum.
Well, is this used in a television?
Yeah, but just looking at this, if we make electrons float around up down here, what is going on up at the other end? What's the charge?
Positive.
Positive. So where do the electrons want to go?
Out.
Towards the positive.
They want to go up to the positive. Okay. So we can alter this by doing this. By taking this, which we call a grid, and applying a plus or minus or somewhere in between voltage to it. If we make this negative, and this becomes negative, what do the electrons see first?
Negative.
They see negative. Do they want to go anywhere?
A mirror.
Well,
essentially.
right. They see electrons. Are they attracted or repelled?
Repelled.
Okay, so how much current flow is there? Remembering that what is current flow? Current is the flow of electrons. Well, okay, and since they are now seeing like charges up there, they are repelled and they basically float around down where they stay. Okay, so how can we make them more attracted to the other side?
By applying voltage.
By applying a positive voltage on the grid. Okay, once we do that, they get attracted, and then they get even more attracted to up here because they've already passed through. So when we do that, what happens to the current?
It flows.
It gets really big, right? Those electrons are completely attracted to the other side. So by taking the grid current, so here's the grid, or I should say the grid voltage, by going from minus to plus, here's my output current. Huh. Okay. What have I done? What does this look like? We just drew it a second ago.
Fire.
Yeah. Doesn't it look like that? Except that in this particular case, we changed the voltage from a negative, and at some point it becomes kind of neutral, and then it goes positive, and by doing that, we make a current flow that looks like a copy of what our grid voltage looks like. So, does that look not very much like what we just did with a transistor? Oh, there's a reason for that. What do we use? What's one of the main things we use tubes for? What do we use tubes for? Any audiophiles out there?
Yeah.
Yeah, have a tube amp?
I used to.
There you go. Okay, so what was the tube used for? Amplification. It's a voltage to current amplifier. Makes a big copy.
You take your tubes out and bring it to the drugstore to test them.
You could do that. Okay, so that's a control grid. Then there's also something called a screen grid, because if we just have a control grid, what we end up with is two metal plates. Two metal plates create a capacitor. So we add another grid called a screen, which reduces the grid to plate capacitance. All right, so that covers vacuum tubes completely. It doesn't really, but so how many elements are there inside a triode vacuum tube, everyone?
3.
3. Okay, how about in a tetrode? How many do you think?
In it.
4.
That would be 4. Yep. No, in a tetrode there are 4. How about in a pentode?
5.
That would be 5. Yeah. All right. So all of those, they all exist. They have different numbers of screens, and like a tetrode would have a single screen grid. A pentode would have 2 screen grids.
So vacuum tubes still exist?
Of course.
I don't know.
Oh yeah, for sure. In fact, they're extremely rugged. In fact, one of the most useful uses of a vacuum tube is these things are just great. Can everybody see that? Maybe not. I probably have to stop the share. Yeah, I have to stop the share. These are incredibly rugged. Everybody see that? And I think they're a thing of beauty too.
Oh wow.
Yeah. That's a 500 watt plate dissipation vacuum tube. $329. And it does say made in China. They used to be made in the US by iMac and several other companies. Then they shifted off to Russia, and from there they went to China. But yes, you can still get a 300 volt triode, 500 watt triode. And they are incredibly rugged. I mean, it is so hard to kill one of these tubes.
I still think it would be fun to have a test tube ham radio, the old ones.
Yeah, I mean, the only problem is that some of those tubes are kind of hard to replace these days. But the power tubes still find a lot of use. Okay, here we go. Batteries. Advantage of batteries with low internal resistance. Low internal resistance means they can deliver a lot of current because they have very little resistance. A 12-volt battery, you never want to take it below 10.5 volts. Integrated circuits. Okay, an operational amplifier is an analog amplifier. Just remember, operational amplifier is an analog circuit. MMIC stands for monolithic microwave integrated circuit. Those are used for power amplification at microwave ranges. Most devices don't work very well up in the microwave ranges. They require a special circuit called an MMIC, just because the frequencies are so high. CMOS is complementary metal oxide semiconductor. CMOS was developed in the 1970s. TTL was developed in the 1950s. CMOS is a much lower power consumption integrated circuit. It's just the most important thing to remember. An LED is a light emitting diode. When it's turned on, when it's forward biased, it emits light. We use them for all kinds of things. Okay, connectors. There are many, many different kinds of connectors out there. There is a PL259, there is an RCA connector, there's an N connector, there's an SMA connector. Most of the small handheld radios you buy these days will have an SMA connector. Those are actually good for into the gigahertz range. RCA connectors are useful for audio typically. A PL259 is also known as a UHF connector, which oddly enough is really, really bad for use at UHF frequencies. It was not named for UHF like ultra high frequency. It was named for universal high frequency. And in effect, it's really, really terrible for UHF use. So let's see, miscellaneous. RF connectors. Okay, so what I'm going to do is pop this up on the screen because I actually have one of these. It's so nice to have something like this. Okay, so hopefully it shows up. Okay, so this is a universal kit. On the right-hand side, you've got your UHF connectors. This is a PL239 and SO239. Right next to that, you've got like a TNC. Then these big ones up top, those are N connectors. They're good to like 6 gigahertz. They're also waterproof. Next to that are BNC connectors. And all the way on the left-hand side are SMA connectors. What's nice about a kit like that is that if you don't have to use too many of them, you can always like dummy one up. So, different connectors for lots of different purposes. Okay, so BNC connectors, SMA connectors are good into the gigahertz range. An N connector, notice 10 gigahertz and water resistant. Okay, here we go. Schematic symbols. And we're going to take a break in a couple minutes, by the way. Here we go, schematic symbols. G7-1, this right here in the middle. Number 1, that is a field effect transistor, not to be confused with number 2 on the right-hand side, which is a bipolar junction transistor. They're both used for amplification and switching. A Zener diode we covered in the other class. A Zener diode is number 5. That is a diode. A diode is a device that is a one-way street. When it is forward biased, the negative terminal is the flat line. Look at number 3. At the top of the triangle is the plus, and at the bottom of the triangle is a minus. When there's a positive voltage, voltage flows from the plus to the minus in that direction. If the voltage goes the other way, the voltage is blocked. A Zener diode is a backwards diode. It operates the other direction. A Zener diode is special when the voltage is positive up at the bar end up top. When it's above a certain voltage, it actually flows current backwards. So from the top to the bottom. And in doing so, it regulates the amount of voltage that is at the top. It is an important part of every power supply.
You cut out for a minute. It does what? When it...
Make sure. It is an important part of regulating the output voltage of every power supply in existence. It generates a reference voltage for a power supply.
Okay.
An NPN junction transistor, we can see number 2 over there is an NPN junction transistor. A solid core transformer. Well, okay, which thing looks like a transformer? Oh, I'd say over here. That looks like a transformer. The thing on the right-hand side at number 6. A tapped inductor. That would be like a variable inductor. Oh, okay, number 7. There's an inductor and it has a line coming out of it. So basically, it's been part of the inductance is being picked off of it. Power supplies. Okay, so we did a half-wave rectifier in the technician class. And now we're going to do a full-wave rectifier. Okay, so this is a diode. We're going to hook it up to an AC circuit. Here's a plus and here's a minus. And the way that a diode works is when the plus side goes for a silicon diode, 0.7 volts above the minus, or for germanium, 0.3 volts above the minus, the current flows in the forward direction, in the direction of the arrow.
I lost your blackboard again. I'm sorry, Scott.
Oh, whoops. Better?
Now I can see it.
Okay. Okay, so for an AC circuit, what ends up happening is that the current flows in the forward direction, and the current waveform, which would look like this previously, is now trimmed so it looks like this. The bottom part is cut off. We then take that and we run that through a capacitor. We filter it. The capacitor charges up during the peaks, and then when it drops down, it exhausts some of its capacity, and it takes the circuit and makes the voltage look like this with a little bit of ripple. We then take this and we put it across a Zener diode like that, and the Zener diode caps it off at a particular reference voltage and makes this happen. To anything above that, it sends down to ground so that the output voltage looks nice and smooth. This is a half-wave rectified power supply. So that's half-wave rectified, because only half of the wave is used. However, we can redraw this so that we have more devices. It's more complicated. Here's our power source. That's our AC power source. And we're going to now have 2 different paths. Here's our capacitor. We still have to have a capacitor, and we still have to have a Zener diode, and this goes out to the real world. Okay, so now we have something else in here, so that when the power goes plus and minus, we have to provide a path for this to follow. So we would go like this. And we're going to break that. And we're going to go like this. And we're going to go like that. And when it goes the other way, we're going to give it a different path. So we're going to switch this to minus and plus. We're going to have it go this way. Nope, other way. Like that. And we're going to follow this path around like that. And it goes like that. And it looks like, make sure I get this right. like that. Okay, so this is known as a diode bridge. And specifically, this is a full wave bridge. What happens is that when the voltage goes in one particular direction, two of the diodes are in play. When the voltage switches direction, the other two diodes are in play. And because of that, what the voltage at this point looks like, where it feeds the circuit, is that it looks like this. Instead of only using half of it, it uses all of it. It uses all the power, which makes this a more efficient device for creating power. So this is a full wave rectified power supply.
Are they all in the same direction though? So instead of being sinusoidal, they're all flipped up? Is that what you're saying?
It takes the stuff that was on the bottom
and
flips it up.
And what's this called?
It's a full wave rectified power supply.
Okay.
So this is known as a diode bridge.
Okay, full wave. Okay.
And you can actually do this with three-phase power as well. And instead of 4 diodes, you have 6. It's a much more efficient method of making a power supply. Because instead of only rectifying half of it, it rectifies the whole wave. So it's much more efficient as far. And they're really, you know, a bridge rectifier is really quite cheap. So it's a very efficient way to do this. And okay, let's see. Why is this behaving this way today? I'm just trying to cancel my share. There we go. Okay. Everybody doing okay?
Yeah.
A lot of material. I hope it's going all right. Lots of good questions.
Long days.
Long day. Yeah. Okay. So, AC cycle, a half-wave rectifier rectifies 180 degrees. For a full-wave rectifier, you get full 360. The waveform of a full-wave rectified thing, you get series of DC pulses at twice the frequency, blah, blah, blah. The following, which components are used in a power supply filter network? Oh, will you look at that? We talked about that. We've been talking about that all day. Capacitors and inductors are the basic units that go into a filter. A bleeder resistor.
Can you go back one?
Yep.
Before that one.
Right here?
Yes.
Okay. So if I have 60 hertz in my power and I rectify the whole thing and I flip the bottom part so that the bottom part is now on the top, I have twice as many pulses as I would have. So I have half-wave pulses that are at twice the frequency of the original.
Oh, okay. Okay.
So I get 120 pulses per second. If you have a noisy power supply, you'll often hear 120 hertz hum coming out of it. It's very distinctive. A bleeder resistor, this is typically placed across a big capacitor so that when you turn the power supply off, the stored energy has a place to go. And that when you later stick your hand in there, you don't get a big shock. A switch mode power supply, this is what is powering your computer. This is what is powering most of your radios, actually, because linear power supplies, all except for Luila, your power supply in there is a linear supply, and it weighs a ton.
Yes, it does.
A switch mode power supply would weigh about 20% as much. It operates at high frequency, so all the components are small. All right, digital circuits. Okay. Digital circuits are actually really easy compared to analog circuits. So if I think if this and this, then I'm going to clap my hands. If one of them is missing, I can't clap my hands. That's an AND circuit. If this and this, then my output turns on. I could also say if I have this or this, right? If either one is true, then do something. A binary counter, this is a binary counter. Most importantly, A binary counter has a 3-bit binary counter. This is just memorization. 2 to the third power is 8. So a 3-bit binary counter has 8 bits. A shift register is a clocked array of circuits that passes data in steps along the array. For those of us who've done a lot of digital logic, it's really easy. If you haven't, it's just memorization. Okay, oscillators and amplifiers. The basic components of a sine wave oscillator, a filter, and an amplifier operating in a feedback loop. So, how do we define the resonant? How do we define the frequency of a sine wave oscillator? Everybody? Remember that formula for resonant frequency? We're going to draw this. Here we go. We have a capacitor. We have an inductor and a capacitor. This has an impedance of 2 pi FL, and this is -1 for the capacitor over 2 pi FC. You want to make it so these are equal and opposite. So you say 2 pi FL is equal to -1 over 2 pi FC, and then you solve for F is equal to 1 over 2 pi square root of LC. By selecting your L and your C, that allows you to pick the resonant frequency of the circuit. You put that inside what's known as your tank circuit. You run it through an amplifier, which is a transistor. You take the output and feed it back in, and it oscillates. So here's your inductor, and here's your capacitor, and you feed it back into it, and the output becomes the frequency that you want. I'll use this. So that's an amplifier just running the output back into the input, making a copy of itself, and it naturally oscillates at the frequency that's defined by those devices right there. This is called the resonant frequency. In a Class A amplifier, okay, this is something that you just have to memorize. Class A. Does anyone have an audiophile Class A amplifier? Class A means that the amplifier is on 100% of the time. The way that amplifiers work is that you have this input-output diagram. So here's your in, and here's your out. This is the linear region. Yeah, you must be really tired, Tomislav. Thank you. So Class A, you bias it so that your 0 is right here, so that you shift this way, and that makes the output shift up and down. When there's 0, that means that your output is already turned on. That is a Class A amplifier, which means that it is incredibly inefficient and uses up a lot of heat. There's another way to do this, however, which is I can take 2 amplifiers and draw them like this, so that I can set it up so that my 0 is right here, and I can set them up to operate at different points. So at this point, here's my 0. This one is operating, and I decide that I'm not going to let this one operate, so that I get a longer linear range. And at this point, I still have an output. I can actually set my output point right there, so that one of them is operating some of the time and the other one is operating some of the time. And this is called Class AB. And then there's lots of other classes. There's B, there's Class C, Class D, Class E, Class F. There's all kinds of different classes of amplifiers, and they're all hinged on where the amplifier is operating when it's at off. So I could make it so that when it's off, it's over here, and when it's on, it's over here. That's a very efficient way of doing things. but it's not very good for, like making a good sounding stereo. It's really quite terrible for that. So, okay. How about a break, everybody? Is everyone doing okay?
Yeah, so this is a lot harder.
It is harder. Yes, it is harder. But you probably note that there's a lot of stuff that we did cover this morning.
Yeah.
Yeah, you're hearing it again. So
I mean, this is a good background, and obviously I'm going to have to read the book.
and you're going to have to take the exam. Yeah.
Well, that's true, but I have to read the
right,
book.
but I mean, you're going to have to study to take the exam. So
exactly, read the book and study. Get it.
Yeah.
But
all
this
right.
is a good background.
Yeah. All right. 5 minutes. All right.
I think my brain's about to explode.
Well, it's just kind of like going back to what we already covered, but yeah, that's a lot.
Yeah.
But think about how much stuff you've learned compared to yesterday, compared to where you started.
Oh, yeah.
All right. Well, I'm back. I'm ready. Is everybody ready?
Yep.
Okay. So, notice we're talking about amplifiers. A Class C amplifier, as we talked about this morning, is good for FM and CW. Class A and Class B and Class AB are good for voice. Class C amplifiers are very, very efficient because they're either on or off. That's good for FM and Morse code. Efficiency of an amplifier is output divided by input. We just talked about efficiency. Neutralizing an amplifier. Okay, so what is an oscillator? An oscillator is a tank circuit, which is an LC circuit that goes through an output and is fed back to the input. Well, an amplifier is really the same thing. There's a path back to the input. So if you have power that can get back to the input, it can actually cause this circuit to resonate and oscillate and make power at some frequency that you had no idea where it was going to be and didn't want it to be. So we go through a process called neutralization to make sure that doesn't happen. We make it undesirable for it to go into oscillation. Oscillation is bad for that. Okay, so now we're talking about filters. Oh, you look at that. All that time that we spent talking about filters, and here we are back again at filters. You get the idea that filters are kind of important? Everyone, you get the idea that filters are important? Filters allow us to have the ability to have...
never heard that.
Filters allow us the ability to have frequency selectivity. Okay, so here's a bandpass filter. This is a bandpass. Allows stuff inside the block to pass through. This is a band reject. This is a high pass. Whoop. And this is a low pass. So we can look at something called ultimate rejection. So let's look at just one of these filters. Ultimate rejection is outside of the passband, how much of the signal actually gets through. How attenuated is the signal really? Ultimate rejection gives us an idea of how much actually gets through. We also have this thing called a cutoff frequency. This is full power coming through, and this is 3 dB. 3 dB, you'll all remember, is how much of it? How much is 3 dB? How many times?
Double the power.
Double the power, or 3 dB lower is half the power. So this is known as the half power point. All right, that's the cutoff frequency. So if we have a bandpass filter that looks like this, we have a half power point here and a half power point here. This is known as the filter bandwidth. It's between the half power points, or the 3 dB points. That's known as the filter bandwidth. What term specifies a filter's attenuation inside its passband? Well, if without a filter, the signal were at, let's say, this level, and with the filter, the signal is at this level, this is called insertion loss. That is known as the insertion loss of the filter. You can make up for that by having a little more amplification. Okay. All right, a balanced modulator makes double sideband modulated RF. This is just memorization. The circuit used to select one of the sidebands from a balanced modulator is called a filter. Because if we take a look at what sidebands look like, here's our frequency carrier. Here's lower and upper sideband. These are mirror images of each other. A balanced modulator makes both of them. We can run this through a filter that looks like this. That would be a high-pass filter or a band-pass filter. That would block out the lower sideband and allow the upper sideband. That's how we select one of the two. Okay, let's see, a product detector. A product detector allows us to take a single sideband signal and allows us to extract the modulated signal. In other words, the voice. That's how we get the voice back. Sensitivity. There's lots of stuff that goes into sensitivity. If you have a poor amplifier, it's not going to be sensitive. The modulator stands, but this is basically just memorization. The answer to that is all of the above. Okay, a direct digital synthesizer. A synthesizer is used to synthesize or create a frequency. So one way to create a frequency, So one way to create a frequency is by using an inductor and a capacitor, right? That could be, you take the output of that, you run that through an amplifier, you get an oscillator. The other way to do this is by, instead, we sort of touched on this a little bit before, but now we're really going to dig into it a little more, is to use a computer and a lookup table to generate a voltage that looks like this. Piece by piece by piece. To make something that looks like a quantized version of a sine wave. And by doing this, what you do is then you can run this through a filter and hopefully smooth it out. And you basically generate something that mostly looks like a sine wave. And that's called direct digital synthesis, or DDS circuit.
Scott, I'm sorry, I didn't realize we weren't doing a half hour today, so in about 15 minutes I'm gonna run down and grab something I put in the oven and I'll be back, so if I'm not here, you'll know why.
Okay. What are you making?
Chicken curry, warming up chicken curry.
That sounds very good. I think it's a long, I'd come up to visit and have dinner, but it's a long trip.
That's okay, you can come up. I'll make Thai food for you the whole time you're here.
Okay. Okay, so that's a direct digital synthesis. Variable output frequency with the stability of a crystal oscillator. Okay, software-defined radio. In a software-defined radio, the computer does all the work, filtering, detection, and modulation, which makes it very flexible. There's no hardware to change. You want it to look different, you just change the program. Digital signal processing compared to an analog filter, it's digital. All you have to do is change the program and you can make it look like something totally different. I and Q signals, defining software-defined radio, the in-phase and quadrature signals, as they're called, allow you to basically generate all kinds of modulation with two different things. You start with I and Q, and there's some pretty heavy math. But the most important thing to remember is that these are 90 degrees out of phase, but with them you can make any modulation at all. It's very cool. Okay, signals, carriers, modulation, etc., etc. Okay, so this is amplitude modulation. We kind of tried to draw this before. We changed the power level of the RF signal. That is called AM. The modulation envelope is the outer shell that looks like the red dots here. The narrowest bandwidth form of AM is single sideband. By looking at amplitude modulation in the frequency domain, so we have two different domains. We have, oh, look at that. That's a time domain frequency. It's a time domain signal that looks like that. The frequency domain would go from 0 to infinity, and at this particular frequency there would be a single spike. By looking at this, then we have the lower sideband and the upper sideband, and this is known as the carrier. The carrier contains no information, and the upper and lower sidebands are mirror images of each other and contain the same information. So we don't need the carrier because we can re-inject it when it gets to the receiver. And we also don't need both sidebands. So by selecting just one sideband, we can reduce our bandwidth. This is about 3 kilohertz. Flat topping means you're pushing too much drive into a signal when you're amplifying it, and essentially instead of looking like this, it now looks like this. Come on, like that. And by doing that, you can imagine that the signal gets somewhat distorted, because that's not what your voice actually looks like. This is known as flat topping, also known as overmodulation. When you do that, you start to take up excess bandwidth and your voice gets all distorted. When we change our frequency instead of our amplitude, we're basically doing this. Here's our carrier wave. When we change our frequency, we make it tighter and longer. The amplitude stays the same. We change our frequency. That's called frequency modulation. Everybody still see okay? When we change our phase angle of our signal, that's called phase modulation. By using phase modulation with a reactance modulator, we create essentially phase modulated voice. This is also a basis for creating FM. Binary FSK. Okay, frequency shift keying. There's another thing we can do with our signal. We can change the frequency. So if we have a, you know what I'm going to do? I hope it's still open. If we have in the frequency domain a center frequency, we can have something called a mark and something else called a space. We can, in time, change the frequency based on data that comes in that we're trying to encode. And by moving back and forth in time, we basically make something that looks like this. Kind of like a player piano. This actually has a name.
Pluribus.
Radio teletype. That's teletype. Teletype is a 2 FSK. So 2 different tones, frequency shift keying. We typically operate that at 45.45 baud. For those of you who have some idea of how fast that is, what's 45 baud?
It's horribly slow. It's
horribly slow. That's right, horribly slow.
But what about can you do TTY communications through?
Yeah, that's what RIDI is. It's teletype.
Oh, okay.
Mm-hmm. It's incredibly slow. QPSK is quadrature phase shift keying. QPSK 31 is incredibly narrow bandwidth. FT8 is 8-tone FSK. Link margin is how much excess strength you have between the power level and the minimum power level. That's measured in decibels. So if you have a big link margin between two stations, that means that you're going to have an easy time getting signals through. Link budget, sum of transmit power and antenna gain minus system losses at the receiver. Essentially, it's very similar to link margin. Okay, mixing of two RF signals is called heterodyning. We use a mixer. A mixer, again, is a device that takes two RF signals, and it takes them and puts them through a nonlinear device that looks like this. I don't know why that keeps coming up. Whoop, whoop. Signal in, F1, F2, and puts out F1 plus F2 and lots of other things.
Is that a separate device, or is it part of radios?
This is a part of every radio that changes a frequency from one to another.
Oh, okay.
So this is a mixer. And the nice thing about a mixer is that it allows you to generate a frequency that you can then work with. You can put a filter afterwards and filter out just the frequency that you're looking for. It's also the heart of something, again, called a transverter, which allows you to convert one frequency to another. Okay. There's a sum and difference. Mixer input is varied to convert signals of different frequencies to an intermediate frequency. That's known as a local oscillator. You change the frequency on one of those signals. Interference from a signal at twice the IF frequency is known as an image response. Basically, it's a mathematical thing that happens in a mixer, and it can make a terrible mess. You basically hear a signal where there shouldn't be one. You're tuning around on your tuning dial, and something shows up that isn't real. That's known as an image response. Intermodulation is what happens in a nonlinear circuit like a mixer when you didn't intend for there to be one. Intermodulation is an undesirable result of mixing. My favorite intermodulation story was when I was in college and we had a repeater and we were also in line of sight of two very big AM radio stations. And sometimes we could hear on our repeater the squeal, as we called it, whenever we keyed down. And what would happen was in that squealing sound, we could hear what sounded like an AM radio station. So we had simultaneously these two frequencies, 1580 AM and 980 AM. Okay, and those are measured in kilohertz. What is the difference between those? .600 kilohertz. What is the repeater offset that is standard in the United States? How many kilohertz?
600.
600 kilohertz. Yeah. Okay. So do you see a problem there? So if we somehow managed to get 1580 and 980 to subtract from each other, we would generate a frequency that when it mixed with 145.49 megahertz would give us the input frequency to our own repeater. All we would have to do was take this signal and subtract it from the one that we were transmitting, and it would feed back into and lock up our repeater. But how in the world could that possibly happen, right? I mean, how is that even possible? So, any guesses? Because it took us a year to figure it out.
I'm guessing that your antenna where you were picked up the two of them and started to match it.
It did, but why?
Too long of a cable?
No, everything was shielded well. Any other guesses? Think non-linear devices, something that works sometimes and doesn't work other times. What's the most simple one you can think of? A device that turns on sometimes and doesn't work other times. It looks like this.
A diode?
A diode, okay. So it turns out that rust can make a very good diode.
Yes.
Yeah.
We had rust on the tower. That was serving as a mixer, which was mixing all those different frequencies together and picking up RF and generating enough signal back into our repeater input to lock it up. So what was the solution?
In rust.
Clean up the rust off the tower. Yeah, isn't that crazy? The longer you do something, the crazier the things you'll eventually see happen. Okay. Okay, so modulation and intermodulation. Odd order, you just have to memorize this. Intermodulation products closest to the original signal frequencies, odd order. Odd order intermodulation product, 2F1 minus F2. Again, it's just memorization. FM transmitters use multipliers to produce a VHF signal. Okay. FM signal in the 12 megahertz range and multiply that by 12 to make an FM signal in the ham band up there on 2 meters. So that being said, this is known as a frequency multiplier. And if you want a deviation of a frequency deviation for a let's say you want a 5 kilohertz deviation. That means that your center frequency plus or minus 5 kilohertz. What you're essentially doing with a frequency multiplier is that you're making a smaller copy, which you're then going to scale up by a factor of 12. So if you want this to be made and it's 5 kilohertz wide, when it's scaled down by a factor of 12, you start with it 12 times as small. So to make a 5 kilohertz deviation, you make it 416.7 hertz, so that when you multiply that spacing by 12, you get back up to 5. FM is really kind of weird in that regard. Total bandwidth of an FM phone transmission. This math you just sort of have to take with a grain of salt.
Scott?
Yep.
I apologize, but you completely lost me on the last one.
Okay, well, I'll do that one again.
Thank you.
Okay. So, the way that this... Okay, so I'm going to erase that diode. All right, so let's say that you have a frequency device that has a center frequency. This is FM. And you want the FM signal to be plus or minus 5 kilohertz.
Okay.
Going 5 kilohertz that way and 5 kilohertz that way. And it has a center frequency of 146 megahertz.
Okay.
It's hard to build an oscillator that makes that frequency. So what you do is you start with an oscillator that works at 12.2 megahertz. And you basically make it go back and forth. Then you run this whole thing through a frequency multiplier, which multiplies it by a factor of 12. It multiplies everything by a factor of 12. So if you want this to eventually look like plus or minus 5 kilohertz, it has to be 1/12 the size. Because you're going to scale everything, including how far it's moving back and forth, up by a factor of 12.
And where did you get the 12.2 from?
That's what is used.
Okay.
That's the most commonly used thing.
Okay.
So that your Deviation is plus or minus 416.7 hertz, which is 1/12 of 5 kilohertz.
Okay.
And that's a frequency multiplier circuit, which is commonly used in FM radios, like handhelds. That way it doesn't have to generate 146 megahertz frequency right off the bat. It starts
But
down
doesn't
here.
that end up making it so wide that you end up, if you were near the edge of a band, it would take you out of it?
What's 416.7 hertz, not kilohertz, times 5? Or sorry, times 12.
Okay, hertz. Okay.
Yeah. Is 5,000 hertz.
5,000.
Which is 5 kilohertz. That's exactly what you're looking for. It's just
Got it.
it's just a clever way of making a higher frequency signal.
Got it.
And
Thank you.
the next one is if you have 5 kilohertz of deviation and a 3 kilohertz modulating frequency, you add those two together to get 8, and then you have plus and minus 8, which gives you plus and minus 16. It's just math you got to memorize. Why is it important to know the duty cycle of the mode you're operating with? Because some duty cycles are 50%, some are 20%, some are 100%. Let's say you build a repeater and a repeater gets a lot of use. What's the duty cycle on that repeater if it gets constant use? How much of the time is it transmitting?
24/7.
100% of the time. So that repeater better be sized and set up to operate 100% of the time without getting burned up. Your radio in your car, for instance, your mobile radio or your handheld radio, is definitely not designed to run high power 100% of the time. The relationship between transmitted symbol rate and bandwidth, higher symbol rates. Symbol rate is data. The more data you have, the more information you have. The more information you have, the wider the bandwidth needed to send it. Why is it good to match receiver bandwidth to the bandwidth of the operating mode? It gives you the best signal to noise ratio. You basically block out the extraneous stuff. Okay, here we go. Digital emission modes. PSK31 is a phase shift keying mode. So, PSK31, phase shift keying looks like this. And then suddenly you'll get one of those. And then you'll get one of those. Those little hiccups indicate something happened. That's data. A shift of the phase of the signal. The phase goes from 0 again to 360 degrees. By moving it a certain amount, that suddenly causes it to indicate, oh, something happened. Oh, something happened there. So that would be data. Okay, so that's a phase shift keying signal. There are different ways to send data using phase shift keying. PSK31 is a binary phase shift keying, which means that it's either 0 or 180 degrees. There's only two choices. There's also quadrature. Quadrature means you have 4. There's also 8, which means you have 8 different places on a circle. So each has a 45-degree difference from all the others, from the adjacent ones. So you can have a 45-degree shift, you can have a 90-degree shift, or you can have a 180-degree shift. Those are all phase shift keying signals. PSK31 is the simplest one, and it uses an encoding technique called varicode. Varicode has different length characters, or different length signals for different characters. This is why when we're typing, it is a better idea to use lowercase. Lowercase characters are shorter than uppercase characters, it turns out. They're encoded with shorter characters. So if you type in all uppercase, you actually slow down. So a good reason to type in lowercase. Baudot code is a 5-bit code with start and stop bits. Baudot is what we use for radio teletype. How are the two separate frequencies of FSK identified? They're called mark and space. In standard RTTY, they are shifted 170 hertz apart. It's binary phase shift keying, or binary frequency shift keying. A low power beacon system for assessing propagation is known as WSPR. It's pronounced WSPR, WSPR. Narrowband digital modes that can use very low signal to noise ratios. It's FT8. FT8 was invented by Joe Taylor. The software package that runs it is called WSJTX. Joe Taylor is K1JT. He's a Nobel laureate in physics and radio astronomy, who happens to enjoy ham radio and doing moon bounce. So he created this mode to give him a way of doing weak signal moon bounce. It's a very, very slow data rate, but the moon doesn't move very fast. So he's got lots of time to aim his antennas at the moon and, maybe take a minute or two and get a couple of bits down. So he invented this, and I'm sure he had a team of graduate students help in the coding. It works great. We use it for terrestrially. It's a lot of, it's not fun, but it is interesting. I mean, it's not very interactive. Some say it's like watching paint dry, but it does work. FT8 signal report of +3 means that the equivalent signal to noise ratio is 3 dB in a 2.5 kilohertz bandwidth, which is an audio bandwidth for sideband. And let's see, a packet radio frame contains a header. The header has the routing and handling information of where the information is supposed to go. Packet radio uses something called AX.25. AX.25 is kind of a basis for how internet traffic works. ARQ. Okay, so we're going to just briefly touch on ARQ again. We did that this morning, but not everybody was here, and a refresher is always a good idea. Okay, so ARQ means automatic repeat request. So let's say that I have 5 bits, and I have 2 different words, and I have something called an odd an odd parity. So if I have an odd number, I'm going to add 1 additional bit. So if this has 3 ones, I'm going to add a 1 to make it even. In this one, I have 2 ones, I'm going to add a 0, so it's still even. I send this data through my network, and I get 1011111. And for this one, I get 011010. I said I'm never going to transmit anything other than even numbers, right? How many ones are in there?
5.
5. Is that valid or not?
No.
Don't know which way it went wrong, but that's not good. How about this one?
3.
That's
3.
bad.
Also not good. In both of those cases, I would say NAK, or no acknowledge, and my ARQ system, which is automatic repeat request, would send a message that said, oh man, I missed it. Please send it again. So it's self-correcting in that regard. It's not going to fix the problem, but it's going to know when there was a problem and say, please send it again.
Can you explain how you got from left to the right side on the numbers again? I'm sorry.
This is my channel. That's my data getting sent, getting corrupted as it travels through the channel.
And could you change, like you said, okay, I'm only sending even. Well, are there people that only send odd, or no? That's how it's set up.
Yeah, you can set it up.
Send...
You just choose the way it's set up, so long as the other person on the other end knows the same thing. But that's why when you set up, for instance, your data, you say 8N1 or 8E2 or 7E2. The number of bits, even or no parity, and the number of bits, number of parity bits. So by setting these, if those are wrong, if they don't match on both ends, the data is not going to be valid for anyone. And
so that would be 7. You'll always send 7 digits, basically
even parity and 2 parity bits. So I'll send 2.
So you'll add 2 if it's not up to 8 or up to 7 pieces. You'll add 2 to it.
Correct.
Okay, got it.
But yeah, so basically this is the corrupting channel as it gets sent through the void. Because you can't control what comes out the other end. You have absolutely no control over it. So if you have a connection with somebody else and you get too many dropped attempts, your connection gets dropped. Forward error correction transmits redundant data, and if you have enough redundancy, you're able to actually figure out what the mistake was, which is very, very cool. And then you can correct it instead of just knowing that it was a problem. Okay, so I'm going to open up WebSDR someday. And we'll open up this one, hopefully. Oh, stop it. Start audio. Okay, stop share. Okay. I heard that annoying sound?
Yeah. Static.
Okay, excellent. So this is known as a waterfall display. So this is a digital signal. This is a software-defined radio in the Netherlands at a university. And notice what I can do. I can change the bandwidth of the receiver. I can alter its position and change the pitch. What's happening when I'm moving this and altering the pitch is that I am basically changing the frequency of my local oscillator, which is changing the pitch of the received signal. The received signal is not moving at all. What's moving is me and how I'm perceiving it. So this is known as a waterfall display, and this is the effect of filtering. Notice I can make it really narrow. What that does is it increases my signal to noise ratio by narrowing up the bandwidth that I'm listening to. It also means, however, that if I'm trying to maybe listen to adjacent signals, I won't be able to hear anything. So that could be bad. That could also probably be very good. So, okay, so that's a waterfall display. We will keep coming back to that. A lot of radios today come with built-in waterfall displays for the high frequency bands. Notice frequency is horizontal. Essentially, that's a spectrum scope. Signal strength is intensity, and the time is vertical, known as a waterfall. Okay, if you see one or more vertical lines on either side, that is a sign of overmodulation of the signal. On 2.4 gigahertz, there's unlicensed Wi-Fi. We actually share the signals with the unlicensed Wi-Fi service. Mesh microwave nodes. Mesh is cool because it's self-healing. So if a node fails or becomes unusable, the signal will reroute itself so that it gets to where it's supposed to go by other means. Digital voice modes, DMR, D-Star, and Fusion are all modes that are digital. Okay, now we're into antennas and feed lines.
There we go.
All right, everybody ready for antennas and feed lines?
You ready?
Okay, so every feed line has a characteristic impedance. For coaxial cable, you remember that it was the spacing and size of the conductors that determined whether it was 50 ohm or 75 ohm or 90 ohm or whatever it happened to be. That is determined by the ratio of the actual stuff. So you can make a big cable, you can make a small cable. So long as the ratios are the same, the characteristic impedance Z0 doesn't change. The only thing that changes is the size and the expense and the power level that it can handle, and also the loss that it incurs. Now, what you can also do is, we briefly touched on this yesterday, is that you can run two parallel lines in the air that are spaced by a distance. The diameters of these wires, along with the space, determine the impedance of this line. This is called parallel line or ladder line. And these can be 300 ohm, 450 ohm, and 600 ohm typically. The reason to use something like this is because this is super low loss, even at all HF frequencies. Really, really low loss. Really low loss. So it's very forgiving to high SWR conditions. What causes reflected power at an antenna's feed point? Let me unshare this. That would be a difference between feed line impedance and the antenna feed point impedance. How do you prevent standing waves on a feed line? You match it to the characteristic impedance and it travels down the line forever and you never see it come back. Okay, to calculate standing wave ratio, you take the bigger impedance and divide it by the smaller one, and that gives you a ratio. So 200 to 50 would give you 200 to 50 divided by 50 is 4 to 1. Same thing with this one. If you have 50 ohms and 10 ohms, you take the bigger one and divide it by the smaller one. You get 5 over 1. It's 5, so you have an SWR of 5. Both of these conditions are very, very bad for a radio. If you tried to feed power into that antenna with this radio, you would either do damage to the radio or the radio would protect itself by saying, I'm not doing this, and shutting down the transmitter output, knocking it way down. So, what's a reason to use an impedance matching transformer? Well, if you have, let's say, 10 ohms, you want to match the impedance of the transmitter and feed line so you can deliver power to the antenna. That's what a matching transformer is for. A matching network like an antenna tuner does the same thing. If the SWR on an antenna feed line is 5 to 1 and a matching network at the transmitter end of the feed line is adjusted for a 1 to 1 SWR to the transmitter, what is the resulting SWR on the feed line? This is actually a very wordy question for asking a very important question. If you have a problem, let's say this is your problem. Okay, so here's your antenna. Okay, so here's your antenna, and your antenna has an impedance of 400 ohms, and you have a 50 ohm piece of cable. What is your SWR right there? Take the bigger one, divide it by the smaller one. What
8 to 1.
8 to 1. That is a severe mismatch. You get a little power out and a lot of it coming back. It reflects back and forth up and down the line. Then it gets to this thing called a tuner, which has this magical effect of here's your radio, and it looks like 50 ohms to your radio. Well, is your radio happy with that? Sure is. What's your problem at the antenna still? What's your SWR at the antenna? Did I do anything to it at all?
No.
No, I didn't fix my problem. What I did is I made sure my radio wouldn't blow up. So what that means is that I have power going up and down, bouncing up and down this feed line over and over and over and over. And every time it does that, it puts out a little bit of power, and then the power reflects back. And every time power goes through a feed line, it encounters a bit of loss, which means that it does what? Takes some of that power and turns it into heat. So how much of my power actually gets out? Not very much. Most of it goes to heating up my feed line, but at least I don't blow up my transmitter. Ideally, what do? I can replace that feed line with something that has very, very low loss, in which case my losses are greatly reduced, or I can do something up here and actually fix my problem.
So if you have a tuner in there, would you even be aware you had a problem?
Maybe. Maybe not. You might not care. I mean, my system, I knowingly have a problem at my antenna. I intentionally have a badly matched antenna because I use ladder line, so I don't really care because the loss is so low. I don't care if I have a 10 to 1 mismatch up there. Power goes up and down, but every time I lose a hundredth of or a thousandth of the power every time it goes up and down, let it bounce. It doesn't matter. But if I were using coax, yeah, it would make a really big difference.
If it's thunder or something.
So the design of your system makes a very big difference. So you have to take that into account. Okay, high SWR increases losses in a lossy transmission line. Yep, that's true, because it goes up and down multiple times. The attenuation of coaxial cables changes with increasing frequency. Attenuation goes up. We measure coax loss in decibels per 100 feet. Effective transmission line loss at the on SWR. If you have really lossy cable, you won't see power coming back as much because it got burned up as heat, which means you won't be able to measure it, which means that it might not look like you have as bad of a problem. So really bad coax can make it look even worse, like you don't have a problem at all.
What do you use if you don't use coax?
Ladder line. But I can't bury ladder line, right? You can't put it in the ground. It's separated by air.
But why would you want to bury it?
What if I had to go across my yard to the antenna? I wanted to dig a little trench so nobody cut it up when they mowed it. I didn't clothesline anybody in the middle of the night when they were out chasing the dogs. Real world solutions, right?
Right.
Window line, this is what I have, 450 ohm ladder line. Okay, approximate length for a half-wave dipole. Does everybody remember when we cut antennas and measured antennas and what they were supposed to be? Like way back in time, like yesterday. Remember when we talked about that? Or if you studied for your exam some other time, like way back in time when we had this equation. Does everybody remember that?
Oh, yeah.
Yeah.
Okay, so we have 3.55 megahertz. Okay, so that's our frequency, and we plug it in right here. So our wavelength at lambda is 300 divided by 3.55. And I have to go back to the calculator and get it. Calc 300 divided by 3.55.
84.5.
84.5. Which makes sense because it's the 80 meter band. Okay, so now that's a full wave. I want to make a half wave antenna, divide it by 2 is 42.25 meters for a half wave. And because every antenna is about 5% too long, I have to multiply that by 0.95. Shorten it by 5%. I get 40.14 meters times 3.3 feet per meter is 132 feet. And let's see what our book says. Did we get it close? Hey, will you look at that? 132 feet. Okay. How does the feed point impedance of a half-wave dipole change as the feed point is moved from the middle toward the ends? At the middle, it's about 72 ohms. At the ends, when you get to the very end, it's closer to 2,500 ohms. So it gets higher and higher. That is why when we do an end-fed half-wave antenna, we have to use a matching transformer to change the impedance to something we can feed. It's convenient in a lot of ways. Horizontally polarized versus vertically polarized antenna. So yesterday we talked about this, and we're going to talk about it again briefly. So here's our wave. Okay, so here's our wave. And we have this. This is our electric field. And this is our magnetic field. These are our two components of our wave that are at perpendicular angles, right angles to each other, and they're traveling with energy going in that direction. So this is the magnetic field, which is the B field, and this is the electric field of this wave. As this wave is traveling, the electric field defines the polarization of the wave. So in this particular case, the wave would be horizontally polarized. If it were rotated so that the electric field was going up and down, that would be vertically polarized. If we were to make an antenna that looked like this, where's the boom? That these are parallel to the ground. Here's the ground. This would be a horizontally polarized antenna. Horizontal polarization is better for ground losses than a vertically polarized antenna, which would look like this. That has an electric field that goes up and down. A horizontally polarized antenna has an electric field that goes side to side above the ground. Okay. Lower ground loss. What's the radiation pattern of a dipole antenna in free space? In a free space in a plane containing the conductor, it makes a donut shape. They say it's a figure 8. It's really a donut at right angles to the antenna. Some of that donut goes out in horizontal directions, some of it goes up and down. Basically, it just makes a donut. Or, if you know what a torus is, it makes the shape of a torus around the center of the antenna. And what do we measure the gain of an antenna in? What units? Decibels. Yes, the answer is always decibels. Okay. Antenna height. How does antenna height affect the azimuthal radiation of a horizontal dipole antenna at angles angles higher than about 45 degrees? So, if it's less than half a wavelength high, the pattern is about omnidirectional. So, what that means is we really want our antenna to be pretty high up in the air. If it's less than a half wavelength high, you're going to get an omnidirectional antenna pattern. If you want it to be directional, it's got to be higher than that. The feed point impedance of a horizontal half-wave antenna, as it gets down to 1/10 of a wavelength above the ground. Ooh. Well, it goes down and it's not 50 ohms anymore. It's not 75 and it's not 50. The closer it gets to the ground, the lower the feed point impedance goes. The other tricky thing is if it's that low to the ground, like 1/10 of a wavelength above the ground, most of the signal is going to go straight up to the sky. There is something called NVIS, which is near vertical incident skywave. It is used for very, very close-in communications. This is not a good DXing antenna. This is a good antenna for talking 150 miles away, if the conditions permit it. Quarter wave ground plane is omnidirectional in the azimuthal direction. A quarter wave monopole, well, that's a quarter wave antenna. How would we calculate that? Somebody take me through it really quick. How do we calculate the length of a quarter wave antenna?
20.
Gary, you look like you're ready to do this.
I don't know. I'm thinking about it.
Well, what's the first thing you do? What's the first thing you're going to write down? You got a frequency and you got what? Speed of light. What's the first thing you do?
Bye.
You're going to write that. That's the first thing you always do. The frequency is 28.5 megahertz. So what do? You need to know the wavelength.
300 is the speed of light. 28.5 megahertz is your frequency.
Right. That gives us about 10.5 meters. Okay, that's one wave. How long did they say they wanted it to be?
Quarter
wave. What do? Divide by 4.
42.
Nope.
Oh, wait.
Divide by 4.
Nope.
What, about 2.6 meters, roughly?
Yeah, 2.63.
Okay. And then we want to shorten it by 5%. So that would be
2 about 2.5, 2.5.
Okay, and then
2.4,
multiply
yeah.
that by 3.3 to get feet.
8.24.
Okay, 8.24 feet, and let's see what they actually have it in. What units? Do, 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 do. There we go. What do they say?
8 feet.
8 feet. Congratulations, you just made your first antenna. And it really is that straightforward. You just have to remember where to start. Where you always start is with the speed of light equation that translates between frequency and wavelength. Okay, let's see. Stop share. Whoop. Okay, continuing. Is everybody doing okay?
Yes.
Yeah, okay. I know it's a lot of material, but okay, the radial wires on a ground-mounted vertical should be on the ground or in the ground. How many radial wires do you really need to make a ground-mounted vertical? What do you think?
1.
4.
At least one, yeah, but really 4 is good. 4 is better than 2. 8 is better than 4.
Are you talking about the tower or the antenna?
No, if you're making a ground-mounted vertical, like your antenna's like, the center point of your antenna is basically on the ground, and you're putting out a field of radials in the grass. That makes the ground plane.
4.
At least 4. I've seen people do 120. Because 8 works better than 4, and 16 works better than 8, and 32 works better than 16.
And it'll never come down in our windstorms.
Well, remember, these are buried in the ground. You pulled up all the sod and put these down in the ground and put the sod back down.
And where are you attaching the grounds?
That's the bottom half of the antenna. The same way, remember we did a car? We showed a quarter wave vertical on a car roof.
Yes.
Well, let's say this is a 33-foot vertical. So your ground, basically your radials are buried in the grass. And they are 33 feet long.
Oh.
And so here's your feed point, the top part and the bottom part. And all of those bottom ones are connected to a single ground plate. So this is a quarter wave long. And these are also a quarter wave long. I've seen people use as many as 120 of them. It works. It's a lot to maintain. Okay, let's see.
So that's instead of putting it on a tower.
Correct.
Putting it on the ground. Okay.
Yep. A way to adjust the feed point impedance of an elevated quarter wave ground plane vertical is to take the ground legs and bend them down at about a 45-degree angle. Believe it or not, this is what I have on my house. A random HF wire antenna connected directly to a transmitter. Ooh, random length. That would mean that you typically get significant RF current flowing back into the antenna. It's not resonant. Okay, with regard to directional antennas, how are we doing? There's still a good amount of material in there, but we're covering a lot of it. And we're covering some of the really important stuff. Okay, is everybody doing okay?
Yes.
Yeah, okay. It's a lot of material. I know it's a lot of material. Okay.
I'm going to sign off. I told my family I'd be done at 7, so
okay.
Thank you very much, and I hope everybody does a great job.
Thank you, Gary. Thank you, family. Okay, so it's okay is it okay with everyone if we go till 5?
I'm good.
Okay.
Good.
I won't feel bad if anyone stops. So,
Keep going.
Okay, here we
I'm just
go.
gonna turn my volume up and go around the corner into the kitchen and make a fresh cup of coffee.
Okay. All right. Decibels. dBi is isotropic. dBd is with respect to a dipole. Your dBi, remember we talked about this briefly this morning, is compared to an isotropic radiator, which is imaginary, does not exist. So a dipole is instantly 2.2 dB better than an isotropic. So the differential is 2.15 dB. You have to take that with a grain of salt. Front to back ratio, measured in decibels, is the gain in the front direction compared to the gain in the back direction. The main lobe of a directional antenna is the maximum radiated field strength. Which way is it going? A Yagi, the central part of a Yagi is the stuff going forward. The central part of a Yagi is a half wavelength dipole. The way to make a Yagi is to take a longer element, stick it in the back, and shorter elements and stick them in the front. The longer element is called the reflector. The ones in the front are called the directors.
And what would you use that for? What would that be best for?
Ooh, well, okay. So let's say that I put up a dipole. Here's my dipole. Here's my dipole. This is going to have signal going that way, and then some of it up and some of it down. So what if I wanted to talk to somebody over there? Do I really want this stuff in the back?
No.
No. So what I would do then is I would take this antenna and I would put at least one element called a reflector behind it. So the energy that's going backwards is re-radiated forward, adding to the stuff that's already going forward, which gives me more gain in the forward direction.
So that's just another wire.
That's another wire that's 5% longer than the driven element, which is a half-wave dipole.
Okay.
I could then add to this by adding shorter elements in the front, which are 5% shorter, which also resonate at the same time and provide even more gain in the forward direction. So at that point, what I end up with is that my forward lobe looks like this, and my backward lobe is really small. So then if I can take this and put it on a rotator, I can direct my signal to where I want it to go. That's why you would put up a Yagi. You might be able to get 10 dB of forward gain. So that would mean that if normally I was operating with 100 watts, what would be the equivalent in the forward direction? What does 10 dB equate to? 10 times.
100.
So that would mean that instead of having an equivalent of 100 watts, I would have 1,000 watts going in the equivalent. So just by changing it from a dipole, by adding those extra elements, I have the equivalent in the forward direction of having a kilowatt. That's why people do it. And it also works on receive. I have that much gain in the for the receiver also.
What are you using to connect those pieces to each
Nothing. Nothing. They are connected by a single solid element. There is no electrical connection at all. They're parasitic. They're just floating in space.
So there's a wire.
Proper length wire at the proper spacing.
Okay.
Yeah, isn't that cool? They are basically, they're called parasitic elements. They are just floating there in space in the RF energy fields. And by being there and being spaced properly, they enhance the signal in the forward direction.
And how would you decide the spacing? If I wanted to build this, how would I know how far to put each one?
There has been a lot of computer modeling and optimization available.
Okay.
There's been, optimized Yagis. These have been around since the 1950s. And there are, if you really want to get into it, there's a lot of numerical modeling you can do with software with regard to antenna spacing, but there are a lot of optimized Yagi designs out there that people have come up with. Typically, it's about 2/10 to a quarter wave between elements.
Okay.
You can also have a longer boom. You can space them out even further. That gives you more gain. At some point, there's diminishing returns, but yeah, some people don't have room to put a longer boom out there. So the primary, there we go. Look at that. Reflector is longer, director is shorter. Increasing boom length and adding directors increases gain. Increasing the bandwidth, you use larger diameter elements. How do you optimize forward gain, front to back ratio, etc.? Physical length, number of elements, spacing of each element. Well, there we go. That just repeated what we just said. How does the gain of two 3-element horizontally polarized Yagis spaced halfway vertically apart? Well, it's double as good, twice as good. Twice as good is 3 dB. So you can actually stack your Yagis and feed them in parallel. It narrows the main lobe in elevation. That's true. You don't send as much signal into the sky. Okay, using a gamma match. A gamma match is a really weird thing. Okay. Notice it does not require the driven element to be insulated from the boom. Okay. This is actually, I would go right past this, except that I think this is a perfect indication of why it's important to understand how this radio stuff works. Okay, so here's my antenna. I'm going to draw everything but the driven element. Okay, are you ready for this? Yeah. Here we go. There's my driven element right there. It's not insulated. It's connected directly to the boom. You would think, given that this is the case, that what? Given that were the case, this is a short circuit, isn't it? Right? It's connected electrically directly to it. No insulation at all. Okay, how about if I take my shield of my cable there and my center conductor and put it right here? Doesn't that seem like that would be a short circuit?
Take the shield. Maybe I didn't understand.
So here's my cable as it's going up to the antenna. So this is the shield. And this is the center conductor.
Right.
I take my shield and run it to right here.
Oh.
And here's the center conductor. Isn't it all one big solid piece of metal?
Yes.
How come that's not a short circuit? Doesn't it seem like it should be?
Huh?
It's not. You know why it's not?
No.
See that distance? You see that distance right there? That spacing allows those different points, because what are the wavelengths we're talking about? Wavelengths are pretty, they're not zero, they're not infinitely long, are they? This is a significant enough part of a wavelength right here that these are not at the same voltage. And that causes current to flow in that element because they're at different voltages.
And how far apart do they have to be?
A foot.
A foot, okay.
This is why radio stuff is really weird, because things that we normally think about, right? Short circuits and connections and stuff like that, being a short circuit. If you have two wires connected to a piece of copper here and here, and you have like a voltage here and a minus voltage here, they're going to short out, aren't they?
Yes.
But at radio frequency, they don't. The rules don't apply because we're talking about wavelengths that allow them to not short out. They don't. The normal rules don't apply anymore. This is called a gamma match. It's used for feeding power into antennas, into Yagi antennas. And there are lots of other matches like that. There's a beta match. There's a hairpin match. There's all other kinds of awesome stuff. But this is the really weird one to me. Like the fact that you can take a tower and you can actually feed energy into it by, even though it's buried in the ground, you can put power on it a few feet off the ground and make that tower resonate and send energy off. Because it's not grounded. It's grounded, but it's not really. Yeah, stuff like that. It's like the rules don't exactly apply anymore. The rules that we know about electrical stuff just, they don't apply to RF. RF is its own thing. And it's cool to understand it. What's a beta or hairpin match? That's a quarter wavelength section of 75 ohm coax. No, it's a shorted transmission line stub based at the feed point to provide impedance matching. Yeah, here's another one. This is how we build a tape measure Yagi. Here's your reflector, driven elements like that. You take your coax and you go like this, and you connect one side here and the other side here. You ready for this? You short those out. Doesn't that look like that would be a short circuit? Yes. It does, right?
Yes.
Intuitively, that is a short circuit. At RF, that is not a short circuit. This is how we feed power into our 2 meter tape measure Yagi. This is called a hairpin match because it looks like a hairpin. I mean, intuitively, that doesn't make any sense. You have to sort of learn to think a little bit differently about this stuff to make it work right, to really understand it. And even then, it still doesn't make sense. You sort of have to just accept the fact that it works. I have a master's in electrical engineering, and I have to just accept the fact that these things work. All right, specialized antenna types. An inverted V is a dipole where the feed point is way up in the sky. So it's like an upside down letter V. It's typically an antenna that doesn't have a whole lot of gain, but it's easy to support because there's only one pole. A log periodic antenna, this is your old school TV antenna. So you have logarithmically related elements along the boom. They're all fed energy, and only 2 of them of the 11 or so are typically active at any given frequency. So low gain, but very, very wide bandwidth. NVIS antenna, a horizontal dipole placed really near the ground, will put up signals almost directly up into the sky. The military loves using these for strategic things because they want to talk to, helicopters. Helicopters are up in the air. So NVIS antennas are great for that. They're also great for like emergency communications if you want to talk to people within 200 miles of where you are on the low bands during the day. A beverage antenna, that's the guy's name, it's not a drink. That's directional receiving for low frequencies, medium frequency and low high frequency bands. Beverages are very, very inefficient. They are not used for transmitting, they're only for receiving. So when you hear the word beverage, that's what that means. Multiband antennas have poor harmonic rejection because they operate on multiple frequencies. They have no ability to selectively pick one band. An antenna trap. Okay, so we didn't really cover this too much. So there are two things we can do with antennas to modify them. Number one, we can take an antenna that is, let's say, a quarter wave long, and we can take some of it and coil it up so that electrically it's still the right length. But physically it's short. This is called loading. Okay, so that's a loaded antenna. It's still a quarter wave long, but it's electrically shorter. I mean, it's electrically the same length, but it's physically shorter. This is what's inside your handy-talkie antenna. Another thing we can do, however, is let's say that we have a single piece of, let's say we have a dipole antenna, and this is designed to be operated on 40 meters. Well, okay, so we draw our half wave, zero current at the endpoints. It looks like this. There's our current distribution. Now, if we had a desire to operate this antenna on 20 meters, we would find this, where we would be feeding our feed point. Oh, well, that doesn't work because we're feeding it at a current minimum where we basically are unable to feed power in because it's really high impedance. So that antenna doesn't work. What we can do at this point is we can basically put in a trap which does this. It's essentially a coil and a capacitor on both ends, a coil and a capacitor, which at a resonant frequency forms a very high impedance that says no current shall go past this point. We pick these lengths so that this part of the antenna is 20 meters long, or a half wave at 20 meters, and all of a sudden it becomes a functional antenna. So a trap allows us to essentially end an antenna prematurely so we can use it on a different frequency. They're not terribly efficient, but they are very useful.
So you could use the same antenna and just tune it up for different frequencies if you needed to.
Right. You tune the trap for a different frequency so that it shortens the antenna and makes it resonant on a different frequency at the same time. The first frequency will pass right through it like it's not even there. So, multi-band operation. The feed point impedance of an end-fed antenna is very high. We already established that. It's about 2,500 ohms. If you have an electrically small loop, the nulls in its radiation pattern are broadside. In other words, through the center of the loop. I have a mag loop that I take on trips, and it is actually quite directional. No power comes out through the middle. A screwdriver antenna, the reason it's called a screwdriver is because there's a motorized electric screwdriver in the base that cranks a coil up and down, changing the length of the antenna. So by changing the base loading inductance, it changes the length of the antenna, which changes its resonant point. UHF halo, also known as sometimes a squalo, is a horizontal loop antenna, a small loop that is omnidirectional in the plane of the halo. So it's a horizontal antenna that radiates horizontally in a horizontal plane. If you ever see one, you'll know it. Okay, radio wave propagation. This is really the meat and potatoes. And I hope there are still people still here. I know everybody has to leave. And I have a hard stop at 5 o'clock, so. Okay, radio wave propagation, sunspots, solar radiation, ionospheric disturbances, etc., etc., etc. High sunspot numbers indicate a greater probability of good propagation at higher frequencies because the sun generates more ionizing radiation at the peak of its 11-year cycle than at the bottom. The more ionizing radiation that comes out of it, that's ultraviolet and X-rays, the greater the amount of ionization that takes place up in the upper atmosphere. That upper atmosphere, when it gets ionized, generates large clouds of electrons during the day. Those clouds tend to create a reflective surface or a refractive surface, depending on which way you think about it, which depending on the frequency that you're sending up into it and depending on how dense it is, will take that energy and refract it back down to Earth. So solar flux, This is a measurement that's taken of how much stuff is coming out of the sun at this particular wavelength. This largely correlates to how much ionizing radiation is coming out of the sun. So it's the 2800 megahertz solar flux index. So when there's a high sunspot number and high solar flux, the 10 meter band, the 15 meter band, the 17, 12 meter bands, even sometimes the 6 meter band will start to work very well. That is a result of what we call the maximum usable frequency. A lot of solar radiation generates a high maximum usable frequency. 20 meter band is in that sweet spot where it is always usable during the daylight hours, any time of the sunspot cycle, any time of the year. During periods of low activity, notice that 15, 12, and 10 meters, the maximum usable frequency never gets up to the point where that becomes usable, and those bands are very, very sad. Propagation conditions in a 26 to 28 day cycle, the sun rotates around its axis, and all of the sunspots do the same thing. Solar flare, solar radiation goes in cycles along with the sun's rotation. If there's an ionospheric disturbance, bam! What happens is that you get lots of radiation hitting the D layer of the atmosphere. The D layer is the lowest altitude of the ionosphere, and what ends up happening then is we have, here's the Earth, and here's the D layer, and the E layer, and the F1, and the F2 layer. The D layer builds up very heavily, and signals that go up normally during the day, up to about 10 megahertz, get absorbed by the D layer. When there's an ionospheric disturbance, the sun basically throws a lot of particles at us. That can go up to 15 megahertz or even 20 megahertz. So even though the maximum usable frequency up here might be 25 megahertz, good luck getting a signal up to there because it just got absorbed right here. At night, however, all this mess goes away. And there's no absorption to speak of whatsoever. There's a lot of recombination of stuff. So even though this at night then goes down to, let's say, 12 megahertz, it's really easy to get those signals up into that area where they can be bounced down over very long distances. Once the sun throws a burp at us, how long does it take to get here? 8 minutes. It's the speed of light. When the sun has coronal holes, it greatly disturbs HF communication. It basically causes our atmosphere to shake and vibrate, and there's lots of energy thrown in. And notice 15 hours to several days for a coronal mass ejection, or CME, to hit the Earth. When that happens, it just basically makes tons and tons of noise. A geomagnetic storm is once that hits the Earth, once that hits the Earth's atmosphere, it causes it to shake and vibrate and distort. And when that happens, we get a disturbance in the geomagnetic field, and our propagation tends to go downhill very quickly. One interesting thing that does happen is that, for instance, during last year's solar storm that created a ton of auroras all over North America, we had really strong auroras, and you can bounce signals off the auroras for fun. And I did for the first time in my life. It was a blast. 6 meter band is great for aurora. The K-index is a 3-hour window measurement of how stable the Earth's geomagnetic field is. This is measured on a scale of 0 to 9. The A-index is a 24-hour aggregation of the K-index. So notice K-index is short-term, A-index is long-term. Questions before we go? Okay. So what I want to do is KC2G muff map.
Hey, Scott.
Yes.
Here's a quick question for you.
Uh-huh.
How do you know when it's the best solar flux time for 10 meters?
Peak of the sunspot cycle.
Okay.
And watch the solar flux index. So this map right here is actually a maximum usable frequency map based on ionosonde data all over the planet. So notice we've got values for maximum usable frequency. We've got lines. The higher the maximum usable frequency, if it's, let's say, right now over us is between 23 and 28 megahertz. As you go east into the darkness, notice it goes down until you're into Europe, at which point it's really low. This other one, FOF2, this is what the D layer is doing. This shows at what frequency the atmosphere is absorbing signals. So right above us, 7 megahertz, but then you go down toward the equator and it's down around 10, 12 megahertz, which basically means there is no path, let's say at 10 megahertz into South America or into Australia and New Zealand. Even though, wow, look at that, 28, 25, 34 megahertz. So what that means, like right now, is we should see significantly great conditions into, everyone can still see this, right? Okay. Great conditions into Australia and New Zealand. So what we're going to do is we're going to see if the real world is matching that. We're going to take 10 meters and we're going to look at signals sent by grid square CN87, which is Seattle. Hey, will you look at that? What do you see? So the prediction said that we should see good conditions into Australia, New Zealand, Japan, Asia. And what do we actually see on the 10-meter band?
It looks good.
It looks good. And we look at 12 meters, same thing. Look at 15 meters, same thing, I assume. Oh yeah, look at 15. Okay, but now we're going to look at 20, which is below that cutoff point. Let's see what 20 looks like. It's okay, but notice we have a lot more stuff down to South America. So the signals are getting attenuated going into Asia. And let's look at 30 meters. This is actually below that. And notice we have no window to Australia at all because the D layer at 10 megahertz is absorbing all the signals. I think it's cool. When you actually start to see the real world mimic the mathematical prediction. So sometimes it doesn't match.
So, quick question for you.
Uh-huh.
So I've been doing my best to keep pace with all these nifty websites you're going to, but would you be willing to drop links to these when you send out the video?
Sure, I can do that.
That would be wonderful. Thank you.
Yeah. Okay, lowest usable frequency. Well, okay, that's the lowest usable frequency for communications between 2 points. What affects the maximum usable frequency? Lots of different things. The sun, the season, the time of day. How does the ionosphere affect radio waves with frequencies below the muff and above the luff? Well, if they're below the muff and they are refracted back to Earth, that would mean a successful communication. Frequencies below the luff are attenuated. When the luff exceeds the muff, you basically have nothing. No conditions. Like, for instance, trying to get to Australia on that frequency just wouldn't work. The least attenuation is right below the maximum usable frequency. Okay. Long path is pointed the other way around the Earth. There are two ways to get to any other place on the Earth. One is the short way and one is the long way. And what might you hear if you have, and this is what we listened to yesterday, signals arriving by both directions. You could hear the short path and the long path, and you might hear an echo. And there was an audio that I played of that echo yesterday. I might just show it again. Lower high frequency, higher HF frequencies during the summer, because of all of the thunderstorms, you get tons of static during the summer. Signals are really, really bad. Okay, skip propagation by a F2. At the F2 layer is high up, like 500 miles. So that means that because it's so high in altitude, you can cover 2,500 miles. The E layer is lower, which maxes you out at about 1,200 miles. The D region is closest to Earth. The D region is absorptive up to about 10 megahertz. That is exactly why these bands, if you look at where they are on frequency, the 40-meter band is at 7 megahertz. During the day, those frequencies get absorbed by the D region. You know, it's interesting that this is on this exam because really it just comes down to memorization at this point. Once you're on HF, all this stuff will make sense. You'll try to do something and you'll find that it doesn't work or that it does work. And it is actually predicted by all of this same stuff. They have to ask something about this for the exam, but you know, that's why it's on it. But this is all stuff that you will learn in practical terms by using it. Critical angle is the highest takeoff angle that returns a radio wave without it bouncing off into space and never coming back. Critical frequency is the highest frequency that is refracted back to Earth. Anything above that, and it will not be able to come back. Scatter is when signals go up into the clouds, and instead of being completely refracted back in the forward direction, some of them get bounced backwards. That's known as scatter. And they're usually very weak, but every so often you can hear them. They also sound fluttery because they're unstable in the first place. So they also sound fluttery because it comes through several different paths on the way. So they go through constructive and destructive interference. Okay, NVIS is near vertical incident skywave. Those are signals that go almost straight up and almost straight down. Thus, near vertical, high elevation angles. Okay, so any idea what a notch filter would look like? What would a notch look like? It's used to cut out something that's interfering with you on your receiver. If you have a strong signal nearby, you can turn on the attenuator, which reduces the receiver's gain. A noise blanker takes a pulse noise and blocks it out by blanking the receiver when that's happening. Most receivers contain this thing called NR, or noise reduction. I personally don't like noise reduction because I know what noise sounds like and I can listen through it. Receivers do their best to try to figure out what noise is, and in the process they can distort the signals. An electronic keyer, instead of sending dits and dahs by hand, will send them by using a paddle. One finger sends dits and one finger sends dahs. Allows you to go a lot faster. Opposite or reverse sideband when receiving CW. If there's a nearby signal, by switching to the other sideband, it might allow you to ignore that other signal. A dual VFO allows you to listen on one and transmit on another. We call that split operation. ALC is automatic level control. If you're using too much ALC, that basically prevents your transmitter from going into a nonlinear situation and making distortion. If it's turned up, if it's operating too much, it will distort your signal. If you're sending digital signals, that's bad because then the other station won't be able to hear you. It won't be able to decode you. Correct adjustment for a load or coupling control of a vacuum tube amplifier. Desired power output without exceeding maximum allowable plate current. Plate current is what boils off electrons in a tube. If you have too much plate current, you're generating too much heat and you will melt your tube. That That is really the one only way to destroy a vacuum tube if you overheat it. Plate current. On the tune control, you'll see a pronounced dip. There's a tune and a load and a plate control. If you've never tuned a vacuum tube amplifier, it's a lot of fun. It requires both hands. ALC, you do use that to prevent excessive drive and driving your amplifier too hard, causing damage to it. The purpose of delaying RF output after activating a transmitter's keying line is to make sure that the antenna can switch between the transceiver and the amplifier output. You don't want to transmit into an open circuit that can cause damage. An antenna tuner allows you to increase your power transfer to the feed line. Okay, digital multimeter. Everybody doing okay? We're making good headway here.
Yep, we're doing all right.
Okay, is everybody ready to go take their general exam, hopefully? Or at least go practice on it?
Pretty close.
Yes.
Okay, that's excellent. Okay. I know there's a lot of material, but, there's a lot of material. The advantage of a digital multimeter compared to an analog multimeter is that it is more precise. The disadvantage is that it is hard to see something going up and down like this. This, as if you can see my Apple Pencil moving back and forth, can actually be very instructive compared to trying to interpret numbers going up and down. Voltmeters have high input impedance because it decreases the load on the circuits that are being measured. An analog multimeter, again, when adjusting for minimum or maximum values, sometimes it's really easy to see a needle as opposed to a value. Horizontal and vertical channel amplifiers, an oscilloscope does that. An oscilloscope allows you to visualize a waveform as opposed to just seeing numbers. If you want to see the waveform of a Morse code transmitter, you can look at an oscilloscope and see it go up and down. You can see it turn on and off. You can see how long it takes to go on and off. If you want to look at your transmitted signal, you take a small version, an attenuated output of the transmitter, and you plug it into the vertical input. So your time is on the horizontal axis. So here's your time, and here's your volts. This is what an oscilloscope does. It gives you a picture of what your voltage looks like through time, which can be very, very helpful. If you don't have an oscilloscope and never got to use one, they're incredibly helpful for that. An antenna analyzer is basically a fake low-power transmitter that can sweep through frequencies that a transceiver cannot legally do. You are not legally operated. You're not legally allowed to operate on 13.2 megahertz, are you? With a ham license. But an antenna analyzer, because it only transmits like a milliwatt, is perfectly okay to do that. So it sweeps across a bunch of frequencies and gives you a graph of what your system looks like at different frequencies. Antenna analyzer is a fabulous tool. You can use it to look at your coaxial cable. You can use it to look at your impedance, your resistance, your reactance, all kinds of cool stuff. Because
how much does a decent one of those go for?
I mean, you can get a used one. I just sold one for $35 it's about 25 years old. It works fine. It does what it's supposed to do. It measures SWR.
All right.
Yeah. A new one, an expensive one, can cost you $1,000.
Wow.
I mean, you can spend a lot of money, but you certainly don't have to. So
yeah, I'm operating off a preschool teacher salary.
Yeah.
So those $35 used ones are definitely what I'm aiming for.
So here's the thing. You get 90% of the functionality with the first 10% of the cost, just like in everything. 90% of the functionality is in the first 10% of the cost. Okay, let's see. What effect can strong signals from nearby transmitters have on antenna analyzers? An antenna analyzer is a transmitter and a very, very sensitive receiver. It's looking for very strong signals. If somebody nearby is transmitting, it can actually get into and confuse the analyzer. A directional watt meter is used to measure standing wave ratio by measuring forward and reflected power. Most antenna tuners have a directional watt meter built into them that will show forward energy and reflected energy. To test the linearity of a transmitter, a single sideband transmitter, you run a two-tone test with two non-harmonically related tones. You put them into it, and you will see you will see on an oscilloscope mixing products. So that measures linearity. Okay, interference, grounding, bonding. Yeah, we're just going to fly through this. RF interference from a SSB transmitter sounds distorted. From a CW transmitter, you'll hear a hum and a click. Audio frequency circuits, how do you eliminate the interference? You use a bypass capacitor, because a capacitor is a high pass device. So it will shunt all the high frequency energy through to ground. That's a bypass capacitor. Common mode current, you use a ferrite choke. So you can wrap your cable around a ferrite choke. If you have a ground loop, this is why we always have a single point of ground in our system. If you create a ground loop, you can have circulating energy in your ground. That can receive energy, that can also transmit energy. It can sound like hum on your signal.
So I thought with antennas where you have multiple legs touching the ground that each leg has to be grounded. But I hear you saying now that you should
I'm talking about inside your station.
Oh, okay.
You never want to have equipment grounded to two different places, or two different pieces of equipment grounded to different places, because then you'll have currents that are circulating.
Got it.
Remember, ground is not ground at RF. Ground is not ground. Okay, bond equipment enclosures together. There you go. How do you minimize ground loops? A resonant ground connection? High voltages, high RF voltages. That's what happened. That's what burned my lip that time. The ground wire has high impedance on that frequency. That's exactly what happened. All metal enclosures must be grounded to ensure that hazardous voltages don't appear. RF hotspots. In order to prevent RF hotspots, you bond your enclosures together. What could be a cause of interference at a wide range of frequencies? An arc generates a wide range of frequencies because it's basically a pulse. A pulse has all frequencies in it. So you'll hear a click or a pop, and it'll be on all frequencies.
Is bonding a particular method of connecting, or it has to do with materials?
It's really the whole grounding and bonding process. Like bonding one piece of equipment to another through a star washer and a grounding strap and things like that.
Okay.
So, bonding one part of your car to another. That's not grounding, but it's bonding things together, electrically bonding them. I think it's really two words for the same thing, but ground is specifically to earth ground. So, speech processors, S meters, and sideband operation near band edges. A speech processor, that's a system that increases, it essentially boosts certain pitches of your voice, making your signal sound louder. It increases average power. If your speech processor is over adjusted, well, you'll sound distorted. Excess intermodulation, excess background noise because it picks up everything. Okay, an S meter. S meter is a received signal strength meter. An S unit is roughly 6 decibels of loudness. So that means that you have 4 times the signal strength to get a 1 S unit improvement. So there we go. From S8 to S9, that is a 4 times increase in the signal because it's 6 dB. Not every S meter is calibrated the same, but that's kind of a general rule. Something that's 20 dB over S9 is 100 times bigger than something that's S9 because it's 20 dB. And every 10 dB is 10 times, so 20 dB is 100 times. Okay, everyone, how wide is the sideband signal in kilohertz?
3 kilohertz.
3 kilohertz, okay. So if you are on lower sideband, how many kilohertz away should you stay from the bottom edge?
At least 3.
3 kilohertz, yep. If you're on upper sideband, how far should you stay from the top edge?
3 kilohertz.
There you go. I was on 20 meters, and I heard somebody violating that simple rule just the other week. What frequency range is occupied by a 3 kilohertz lower sideband signal? Okay, that's pretty basic. Mobile and portable. Okay, why do you use heavy gauge wire? What's the point of using heavy gauge wire?
So that you don't generate a lot of heat.
That's right. You don't waste a lot of heat. You don't generate heat. You don't have significant voltage drop on your equipment. Why should you never connect to they call it auxiliary power socket. For those of us old enough, it is the cigarette lighter. Why should you not try to run a 100-watt transmitter out of your cigarette lighter?
Yeah. Because the wiring won't handle it.
That's right. Your transmitter is going to pull 22 amps. That circuit is typically only good for 8 to 10 amps or something. If you have an HF rig in the car and you're on single sideband, the battery charging system, the fuel pump, control computers, spark plugs, all of these things can generate noise. The most significant part of an antenna system in your car that limits its performance is the fact that the antenna, especially on the 75 meter band, is going to be really short. I've had good luck operating from a car before. I had a very, very big antenna, as big as I could put on my car legally, and I bonded all the panels of the car together using a strap. And I made a good ground plane, and I worked at least 100 countries from my car. But
sorry, keep going.
But it's still electrically short, which makes it a challenge.
So, question on mobile antennas.
Uh-huh.
Does driving a hybrid cause a lot of interference?
I don't know.
Well, I'll happily be someone more experienced lab rat on that one.
Yeah, I don't know the answer to that. My wife has a Highlander hybrid, but she won't let me put an antenna on it. What's a disadvantage to using a shortened mobile antenna? Operating bandwidth is very limited, not to mention the efficiency goes down. A capacitance hat. Okay, the capacitance hat is something that you stick on the top of the antenna on a short antenna to make it look a little bit longer and work a little bit better. It sort of replaces the missing piece of an antenna. A corona ball is a ball that you put on top of an antenna, usually made of metal. You can generate thousands of volts at the tip of an antenna, which can cause actual little lightning bolts to come off of it, generating a corona. A corona ball allows you to dissipate that energy. Apparently it looks really cool. A silicon cell for photovoltaics is a 0.5 volt. They're connected in series and parallel. A series diode should be connected between a solar panel and a storage battery to keep the battery from discharging through the panel. When connecting a solar panel to a lithium iron phosphate battery, you need to use a charge controller. Okay, and I think we're not quite going to finish, but we're going to, let's see, there's safety. We pretty much did safety, and you just got to memorize it anyway. And then, like this stuff right here, this is just me reciting stuff, which means when you study for it, you're just going to end up having to memorize it anyway. So, is everybody okay with that?
Yep.
Okay.
Yep.
All right. Y'all are troopers, and I really appreciate it. So let me, okay, we did that. We did that. We did that. We did that. Operating procedures. Okay. What mode of voice communications is most commonly used on HF? That would be single sideband. True. Which is true of single sideband? One sideband is transmitted, the other is suppressed. It's actually called single sideband suppressed carrier. There's also something called double sideband suppressed carrier, but nobody does that. An advantage of single sideband, less bandwidth used, greater power efficiency. Above, on 14 megahertz and up, we use upper sideband. On 17 and 12 meters, because those are above 10 megahertz, we use upper sideband. For VHF and UHF, we use upper sideband. So this is the one that you got to remember. 160, 75, and 40 meters uses lower sideband. And that comes from historically generating frequencies. It was easier to generate those frequencies on lower sideband. Now they say commonly accepted amateur practice, but that's not where it started. But yes, that is now you can certainly do it, but you don't. That's not why. ALC is automatic level control. What it does is it reduces your transmit gain so that you don't overdrive your amplifier. Vox. Anyone ever used Vox?
No.
I hate Vox.
Yeah, I hate it. Yeah.
You know why I hate Vox?
Comes on when you don't want it.
That's right, because sometimes I'm driving my car and I curse at somebody. Or sometimes I'm sitting at my station and I spill my coffee all over the place and I curse really loud. If I was using Vox, that would go out over the air. I don't want that to be sent out. It allows hands-free operation, but boy, can you get in trouble doing it.
Yeah, it also pick up your radio if you're listening to it.
Yeah, that's true. All right. Well, you know what? From now, it's all rules and regulations. There's ARIES and RACIES and volunteer monitoring and stuff that you got to remember. Just there's something about WinLink. I do WinLink. Commission's rules, power limits, and stuff like that, which you're gonna have to study anyway. You're gonna have to memorize it because it's all memorization. I think we've covered all the technical stuff. And we've knocked it down to 16. Oh, including me, 14 people. I think we've killed almost everybody else. I'm so sorry.
Thank you, Scott.
So tell me what you all really think. Was this worth the time?
Absolutely. I'm still here.
Well,
Yeah,
okay, but it just might mean that you have nothing better to do.
Yeah, I think of it in comparison to like a community college course. To get this many hours of instruction at a community college, this would have been 3 weeks worth of course time. So to be able to cram this and like saturate in it for 2 days, I really appreciate the saturated environment.
Well, cool.
I did gain some more understanding. Repeating things is just going to help solidify it.
And the thing is, if you have already taken practice exams, now having gone and suffered through this, go see if you do better. Just like right now, go see how much of it actually is still in there, and if it helps you do better instantly.
I am doing 90s in the practice exams.
Oh yeah, you're ready. But now let's see how close you can be to passing the general too.
Yeah,
you're ready for the tech.
Yeah.
Kurt, are you ready to take the general now? Uh-oh, can't hear you. Still can't hear you. So, Lueda, do you know Kurt?
No.
You're both in Alaska. I know
He's
Alaska's.
about 2 hours south of me.
I know Alaska's not a big place at all, right?
Right.
It's just almost as big as the lower 48. That's all. All right. Anyone else have any other questions or things they want discussed or mentioned or brought up or covered in excruciating detail? I'm happy to do that before I go.
Thanks, Scott, but we're going to go, okay? It'll
Thanks,
take
Shelby.
lot of
How
personal
about
study.
a class in antennas?
Oh, you know what? What do you want to know?
That would be so cool.
How to build, I don't quite understand. I mean, I've got the math now, but like when you physically say put this to this, what that looks like. When you say add this to your main boom, well, what's the main boom look like? And what are the wires and how am I cutting them? And
main boom is a well, let me ask you a question. Do you like building stuff?
Yes.
You do. Antennas are going to be fun because there are a lot of people who like to do building, and antennas are one of those places where there are so many plans out there. Like here,
But
let's
see,
see.
I want to ask things like, okay, because of where I am, I want to be able to not only figure out how to build the antenna, but like, let's say I say to you, okay, you know my radio, what kind of antenna can I use without putting up a tower to talk from Alaska to Nebraska? And you can say to me, oh, you need one of these.
Yeah,
And
but
then
see that's not really going to help. Okay, so what you really need to do is figure out what kind of excess signal gain you need. I mean, what you really need to do is figure out how much power you're going to be running and what the signal path looks like and how much loss you're going to have. That will determine, what you can do and what kind of antenna you need to do the job.
well, the power would be what my radio's rated
Well, that's
for,
100
correct?
watts. That's 100
Yeah.
watts. So so what we're going to do is we're going to look at VOACAP, and I'm going to share this. Okay, so there's VOACAP, and we're going to do, and we looked at this yesterday, but I'm going to bring it up again. So there's you. You're a little further north than that.
Yep.
Maybe a little further east. And then we're going to put right down here. And we're going to say we're running, let's say 50 watts, because you don't want to overtax that old radio. And you want to run single sideband. You want a little bit of, you want a little excess thrown in there. Here's the capacity wheel. And so this means that at that power level, you know what, let's change the antennas. Let's make it okay, that's fair. Dipole, 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 dipole. So we don't have any, okay, that's fair. We don't have any Yagis thrown in there. Let's say that you wanted to change this to a 2-element Yagi, right?
Okay.
Instead of a dipole. So you can, and you're going to put up a 50-foot tower or something. So we're going to change this to a 2-element Yagi at 15 meters. And let's say that this is a hex beam. Okay, so a hex beam at 50 feet.
So you're talking 50 feet in the air, correct?
Yeah. But so now we just changed it to that. And notice what that did. It didn't do anything for you on the lower bands, but it increased your upper band coverage, your high frequency band coverage. And that makes sense because we improved your antenna from coverage from 20 to 10 meters.
So I'm looking at putting up, regardless of what kind of antenna, whatever I put up is going to have to be quite high off the ground, or at least one of those that I can put up and down.
Not necessarily. So let's look at the antennas again. And instead, let's take that Yagi and put it 17 feet up. What you're probably going to find is that it doesn't make a whole lot of difference. Let's see. So we're going to do this and ready?
Yes.
made it a little worse, right? So it went from like 85% down to 70, 60%. But
Okay.
what it really means is look what you're going to have on 40 meters on this part of the circle. But now I want to also show you what happens if I go to CW. Ready?
Okay. Wow.
Why is that?
Because CW it takes a wider bandwidth.
No, quite just the opposite.
I mean,
Take such a
no,
narrow bandwidth, you can use a tiny amount of power and go huge distances.
Yep. And so here is, why is this doing that? I don't understand what this thing thinks it's doing. Okay, so here's something that we didn't really get to cover, but I'm going to draw it right now anyway. So let's say we have a center frequency, right?
Yes.
And you have available to you a bucket of power with a handle, right? So here's your gallon bucket, right? Okay, so you can either do this, or you know what? Let's make it on the other sideband. Okay, so this is single sideband. You can take that gallon bucket and fill that, or you can take that gallon bucket and fill this space. This is CW, okay. and the other one is single sideband. So you can take that gallon.
Golly.
We're done. We're done. So you can take that gallon and you can fill up single sideband, and you will get up to this.
Really getting into fascinating stuff.
You get up to this level, or you can take CW because it's narrow and fill it up to there. So if the conditions are really good, right, all these signal levels then get sent out into space, right? Whatever those signal strengths are. If the signal strengths are really good, when it gets there, let's say that the other person has a noise level and anything above that's not bad, and anything above this line is audible after all the attenuation of traveling through space, etc., etc.
Okay.
Right? Well, he's going to hear you, right? Let's say the conditions get a little bit worse, and the conditions are right here. Still going to hear you on sideband, right?
Yes.
Say conditions get a little bit worse, and the noise level comes up a little bit more. You've got all this excess on CW where you're still going to get through, and where's your sideband signal?
Well, it's that wide brown.
Yeah, but where is it? If the person's minimum signal level is down at this green line, where's your sideband signal?
Above that.
No, it's below it. Basically, that green line.
The green line that the little green squiggle, wasn't that? Never mind.
The green line is the minimum discernible signal at the other end. As noise goes
I see
up,
what you mean. Okay, now I got it.
As noise goes up and down, as conditions get better and worse, that noise or that minimum signal might actually come up to here. Well, now your single sideband signal is way down there. But where's your Morse code signal? Still getting through.
Yes.
That's why very narrow bandwidth signals are the last ones to go. So like when I take this and I go back to our VOACAP, and we're going to share, right? Okay, so here's single sideband, right? Let's go AM. AM's even worse. Why is AM worse? Because it's even wider, right?
Right.
So let's go to single sideband. That's a little bit better, right? Let's go to CW. That's a lot better. In fact, let's go to CW at 5 watts. It's still better, isn't it? You ready? Now we're going to switch to FT8 at 5 watts.
Wow.
And we're going to switch to Whisper at 5 watts. Whisper is a super, super slow, super narrow digital communications mode. You don't usually you don't actually really even use it to communicate with people. But like
or FT8, can you really communicate?
I mean, you can establish communications, but look, this is CW at half a watt. That is about equivalent to sideband at 50 watts. And that's because CW typically is about 13 dB better. 13 dB better is about, 20 times power? So that's actually not really surprising. Single sideband at CW. There we go.
5 watts versus 50 watts.
Oh, easily.
Wow.
Here's 5 watts CW. And here's 50 watts sideband.
Wow.
Yeah. 5 watts CW works better than 50 watts sideband. Okay. And having done that, I would agree. I mean,
I'm glad to see that. That makes me a lot happier about using sideband, actually.
Yeah. Well, like I'll be doing like a demonstration at the Eugene Science Center, and we're having trouble getting through to somebody at like 100 watts, and I'll switch over to CW and I'll work somebody at like half a watt because it just punches through that much better. There's that much extra gain thrown in because the bandwidth is so narrow.
Thank you.
Does that make some sense? But yeah, I mean, you know what you really need to do? You need to hook up with some people. You need to hook up with some people who really love antennas. And
yeah, once you get your license, you'll get on the air, and there's on the PXL repeater. A couple people have helped me build antennas on this.
Except she's in Alaska. She's in Alaska, but I tell you what, we do a TechNet every week, every Tuesday night, where the topic invariably falls to antennas. Always, it always comes down to antennas.